Hey guys, Andrew here, and welcome to Chapter 4 of our problem-solving series for physics. In this chapter, we're going to begin our introduction to forces and Newton's laws of motion. We're going to be talking about tensions and forces. So, if you can, take a look at the description below. I'm going to leave timestamps for all of the questions there, and I create little generalizations so in case you have a specific problem, you might be able to just scroll through that to find a very similar question that'll help you out. Also, I'm going to leave links for the prior chapters in case you missed them. All right? And if these videos help you out at all, please subscribe. All right? Hit the like button, tell your friends. It really makes a huge difference to us. And without further ado, pen, pencil, calculator, whatever you need, paper. Come on, let's go.
Number 1. A 63 kilogram sprinter starts a race with an acceleration of 4.2 meters per second squared. What is the net external force on him? All right, so here we have a little picture. Here's our sprinter, and his mass is 63 kilograms, and he's traveling, let's just say, in the x direction with an acceleration of 4.2 meters per second squared. So we need to find the net force on him. So take a look on the right-hand side. In order to find net force, one of the useful formulas is to know that the sum of the forces in the x direction will equal the mass of the particular object multiplied by the acceleration in that same direction. So there's only one object, right, and only one acceleration, so as far as the sum, it's really not going to really matter here, but I like to use the formula anyway. So all we basically have to do is just plug it in, right? So the sum of all the forces in the x direction, meaning the net force, right, that's what that represents, will equal 63.0 kilograms, I'll leave out the units, multiplied by 4.20 meters per second squared. Now the mass must be in kilograms, okay, and the acceleration must always be in meters per second squared. So the sum of all the forces in that x direction will simply be now, so 63 times 4.2, don't forget significant figures, so in considering significant figures, we would round to 265. All right, and that now is in, we could write it in kilogram, right, hold on. We can write a kilogram meter per second squared, okay, or this is the same thing as Newton, okay, so 65 newtons. And that would be the final answer. Number 2, if the sprinter from the previous problem accelerates at that rate for 20 meters, and then maintains that velocity for the remainder of the 100-meter dash, what will be his time for the race? All right, so to recall the last problem, number 1, the sprinter had an acceleration of 4.2 meters per second. Remember, that's squared. Let's not forget that. And he's going to accelerate at that rate for 20 meters, and in which case then he will attain a certain velocity at this point, right? So his velocity here could be considered the final velocity. If I consider, right, this frame of the problem as my first frame, okay, so if this is the final point here, then I must be referring to this as the initial point, all right, and then he's going to maintain his velocity, whatever final velocity he reaches for the first frame of the problem throughout the remainder of the problem, okay, and just a quick thing, right, if the total distance of the 100-meter race is 100 meters and he maintains that acceleration for 20 meters, then that means that the remaining, right, displacement here in which he has a constant velocity is 80 meters. All right, so first let's start trying to figure out some times and some times and velocities in this particular part of the problem. All right, so the initial velocity, I'm going to assume here that he is starting at 0 meters per second. He's accelerating at a rate of 4.20 meters per second squared. He's traveling for a distance, right, of 20 meters. 20 meters. We don't know the final velocity, all right, and we also don't know the time. So we're probably going to have to solve for both of these, okay? So first, it doesn't matter which one we choose here. Why don't we solve for the final velocity first? So pick a formula on the upper right-hand side that relates these four variables, and we find that it's going to be equation number 4. So the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is what we're looking for. The initial is 0, the acceleration at 4.20, and the displacement was 20. So let's just plug that into the calculator. So we have 2 times 4.2 times 20 is 168. And then simply take the square root of that. Right, just plug that into the calculator, no big deal. And it becomes, again, considering significant figures, this is 13.0. Right, and that's in meters per second. Now, the final, and this is important, all right? So now the final velocity at this location is 13.0 meters per second, all right? And remember, this is the velocity at this particular point is only the final velocity if I'm considering this part of the problem as my frame. But now, when I now change frames and I want to consider this part of the problem as my next part, right? This final velocity turns into now be the initial velocity, all right? Meaning that it is now the initial velocity of this frame over here, and therefore the velocity at the end would be considered my final, okay? So we actually know this velocity, right? We just calculated it, so I'm going to get rid of that question mark, and we can plug in now 13.0 meters per second, as well as then that initial velocity will be 13.0 meters per second. So that's great. All right, so we got that out of the way. Now, why don't we go back and solve for the time, okay, for this first frame of the problem. All right, so how do we want to do this? I mean, we could do this, let's use equation number 2, right? We could choose other equations, but I'd rather not use an equation that involves the final velocity because maybe I made a mistake. I don't want that mistake to propagate into the next part of the problem. So let's do change in x is equal to the initial velocity times time plus 1/2 at squared. So the displacement was 20, the initial velocity was 0, so that whole thing just goes to 0, plus 1/2 of the acceleration, which is 4.20, multiplied by time squared. So let's clean it up a bit. So we have half of this should be 2.10, right, t squared. Then just divide out the 2.10, 2.10. So now we're left with t squared being 20 divided by 2.1, so 9.52. So we get 9.52. And remember to solve, we got to take the square root. Okay, so the time, remember when you take the square root, you always get a positive and negative answer. However, we're only going to consider the positive value here because we're talking about time. All right, so square root of 9.52 and 3.09. So we get 3.09 seconds. So that's the time, I'll call it, for the first part. Okay, that's the time for the first part. So we found this out. All right, so the time since we're looking for time overall, I'm going to write that over here. So time for the first part here in the first frame was 3.09 seconds. All right, great. Now why don't we solve for time that it took to go from now this point in which he reached a velocity of 13 meters per second, and now he's going to travel at a constant velocity, the problem said, until he reaches the finish line. Okay, so the initial velocity here is constant, so that means the initial would be the same as the final over here, and it also means that it's the same as the average, right? So I can really just make this second part simple. In talking about the second frame of the problem, right, from here to here, we're going to be dealing with just the average velocity formula, is displacement over time. So his average velocity for the whole period was 13.0. He has to travel then in that second frame 80 meters. So how long is it going to take? So simply just do a cross multiplication. 80 divided by 13, we get a value of 6.15. So there's going to be 6.15, and that's in seconds. That's for the second frame of the problem, right? So let's put that here. So T2 would have been 6.15. And now how do we solve for the total time? Yeah, right? We just take time 1 here and time 2, right? Add them together, okay? So we get 3.09 plus 6.15. And we get 9.24. So we get 9.24 seconds total time. Number 3. A cleaner pushes a 4.5 kilogram laundry cart in such a way that the net external force on it is 60 newtons. Calculate the magnitude of its acceleration. All right, so here's our cart. It has a certain mass of 4.50 kilograms. There's a net force, and I just decided to put it in the x direction. All right, there's a net force acting on that particular object that has a value of 60.0 newtons. And what our job is now to find the acceleration. So we need to think of a formula that relates the mass here, right? That is the mass. So we need to find a formula that relates the mass, the sum of all the forces in a direction, meaning the net force, and acceleration. And we have one, right? It's over here on the right-hand side. So I have the sum of all the forces in the x direction should equal the mass of the object multiplied by the acceleration in that particular direction. So the net forces are 60, the mass is 4.50, and the acceleration is what we're looking to find, right? Remember that the force is in newtons or kilograms meter per second squared. The mass is always in kilograms, and the acceleration should be meters per second squared. So divide this out by 4.50 from both sides, and we get that the acceleration on the object should be 60 divided by 4.5. Then we get a nice value, well, not so nice, but it's kind of nice, 13.3 meters per second squared. And that is the acceleration. Number 4. Since astronauts in orbit are apparently weightless, a clever method of measuring their masses is needed to monitor their mass gains or losses to adjust diets. One way to do this is to exert a known force on an astronaut and measure the acceleration produced. Suppose a net external force of 50 newtons is exerted, and the astronaut's acceleration is measured to be 0.893 meters per second squared. Calculate her mass. Okay, so for letter A, we know simply that the force, right, the net external force on this astronaut, so let's call it a force in the x direction, right, that is equal to 50 newtons. Okay, we also know that her acceleration that she experienced, she must also experience that acceleration in the x direction. It should be 0.893 meters per second squared, and we're trying to calculate now the mass, all right? So in order to do so, let's see if we find an equation that relates those three variables, and we have one right here on the right-hand side. So we know that the sum of the forces in the x direction should equal the mass of the object multiplied by the acceleration in that same dimension. So we have the force being 50 newtons, the mass being in the unknown, and the acceleration being 0.893. Sound like Hell's Angels outside. So we have an acceleration of 0.893. So to find the mass, just divide out the 0.893 from both sides, 0.893. That cancels, and now the mass is, oh, there they go, Hell's Angels. 50 divided by 0.893. As long as they're not coming here, I'm fine with that. So we get a value of 56.0, and that's in kilograms. Oh, not kilometers, kilograms. All right, so that's the mass. Easy peasy. Now for part B, let's see. It says, by exerting a force on the astronaut, the vehicle in which they orbit experiences an equal but opposite force. So discuss how this would affect the measurement of the astronauts. Okay, so basically, just pretend you're in a space vehicle. That's an interesting space vehicle. I guess it'll have wings. Sure. Okay, so if the astronaut's in here, right, and they're both moving at the same velocity, both in some direction, okay, let's say now the astronaut is strapped right into the vehicle, and let's say now what the heck is this thing called? Whoops, little brain freeze. The oh my goodness, what the heck is the thing called? Spaceship. Man. So the spaceship, let's say now, will experience an acceleration, okay? And is going to propel it forward by some amount, by some known amount. So that's fine. And now if the astronaut is strapped in, she will also experience that same acceleration forward, right? But as far as now recoil, we're trying to figure out now if there's another particular way, instead of maybe doing it this way, is there another way to do it? Well, imagine she's still on that spaceship, okay? And here now, she's on the spaceship, and she has, let's say, a heavy object, right? So if she now, in terms of the spaceship, if this mass of this object is known, all right, and let's say she's holding it, what she can do is she can push, right, the mass, the object with a known mass in a certain direction, okay? And then by her pushing this object, let's say to the right, this object imparts an equal but opposite force on her. So it pushes her to the left. All right? And therefore now by measuring the distances, we can now find by measuring the change in distance over the change in time, right, and the velocity, we can then figure out the acceleration that this rock, all right, experienced. And if we know the acceleration and we know the mass of the rock, then we're able to find the force. And whatever force she imparted on the rock would have been the same as the force she imparted basically on herself. All right? So that would be a way around it. Number 5. In figure 4.7, the net external force on the 24 kilogram mower is stated to be 51 newtons. If the force of friction, right, opposing the motion is 24 newtons, what force in newtons is the person exerting on the mower? Suppose the mower is moving at 1.5 meters per second when the force F is removed. How far will the mower go? All right. So let's first draw a coordinate system. All right, so we have, according to our picture on the upper right, there's a net force pointing in the right-hand direction. Now what I'm going to do here is I'm going to place that on my coordinate system, but I'm going to place that above, meaning I'm going to place it up here, just knowing that the net has to be pointing forward. Okay, so in other words, I could call it F net, or I could say that the sum of the forces in this direction, which is the same as the net force, okay, is equal to 51 newtons. Pointing to the right. Now it says that the force of friction opposes this motion and is a value of 24 newtons. So in terms now of my coordinate system, right, that would represent a force pointing in this direction, okay, and it has a value of 24 newtons. All right, so this is the force of friction. And let me call it F sub little f, force of friction. And that has a value of 24 newtons. Now remember, that's going to be negative because it's pointing in the negative x direction. So it now says what force F is the person exerting. Well, obviously, if there's a net force in the positive x direction, but I don't have anything there yet, I'm missing something, right? So let me just label that as my unknown. Okay, so let me draw a little line above the axis here, and let's call this is F, right? That's the unknown. So how do we create an equation out of this? Well, it's fairly simple. Remember that the sum of all the forces, okay, in the x direction, all right, equals MA, right? That is true, MAX. But we can also expand this formula, okay, to mean instead of MAX, let me just erase that. I'm going to say it would be the sum, right, of F1 plus F2 plus F3, right, etc., obviously. So in this particular problem, we get the sum of all the forces in the x direction is equal to the sum of F, capital F, right here, plus, right, the force of friction. Okay, now the sum of all the forces in the x direction was 51 newtons. I'm looking for F, and I know that the force of friction, since it's pointing in the negative x direction, it was negative 24. Right, so how do I solve for this? So I just have to add, right, because this is really negative, so I just have to add the 24 to both sides. And now I get that the force applied to the lawnmower by the person is going to be 75 newtons. All right, that's probably what you may have figured out intuitively, but it's good to work with the calculations on this, especially when the problems are easy, so that you get used to it. All right, so that's fine. So we got that force, okay? Now it says, suppose the mower is moving at 1.5 meters per second when the force F is removed. Okay, so that means, right, let's say this little dot represents the lawnmower, and it's traveling this way with a certain velocity. And as soon as he releases it, we're going to call it the initial velocity. So 1.5 meters per second. It says, how far will he go, or the lawnmower go, right? So we've got to find this distance, let's just say. So we'll say that that is what we're looking for, until the mower comes to a stop. So what does that mean when the mower reaches this particular location? That means it stopped. So I'll consider that the final velocity, right? That would be 0 meters per second. Okay, now there's only one thing that I'm missing. I don't know anything about time, but what about, is there an acceleration? And if there is, what would it be? Well, let's think about it, okay? So as soon as he takes his hands off the mower, right, what force is left? Remember, the mower is still going to move forward because it has some velocity, right? But what's the force that's left? He's no longer applying the 75 newtons, right? So the only force that'll be left is the force of friction. Interesting. So now the only force acting on this lawnmower right now will be simply the force of friction. And remember that the force of friction was equal to negative 24 newtons. Okay, so how can we now relate this force maybe to an acceleration? So remember the formula that I wrote before on the upper right-hand side. The sum of the forces in the x direction should equal the mass of the object multiplied by the acceleration in that direction. So the sum of all the forces, it's only the frictional force, so that's negative 24. What's the mass of the lawnmower? It said 24 kilograms. 24 kilograms now multiplied by my acceleration. And notice beautifully how this works out. The acceleration then in the x direction is negative 1, right? Negative 1.0 meters per second squared. That's what we should have expected, right? If the lawnmower is moving with a velocity this way, but it's coming to a stop, there must be a force that opposes the motion. And the acceleration is part of the force that opposes that motion, and it's negative. So that makes sense. So here, including it along with my initial velocity of 1.5, final velocity of 0, I also know that the acceleration of this object is going to be negative 1.0 meters per second. Now, considering all the variables I have here and knowing that I need to calculate my displacement, what formula should we use? I like this one, right? The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is 0. The initial velocity was 1.5. The acceleration we said was negative 1.0. And now I can solve for x, right? So let's clean it up a little bit. So this is 0 is equal to, so 1.5 squared, what do we get? 2.25, great. 2.25, now this is minus 2.0x. Add the 2.0x to the other side. And now we simply get 2.0x is equal to 2.25. And then what do we got to do, guys? Divide out the 2, right? So now x, which is my displacement, will be 2.25 divided by 2. 1.13 when we consider significant figures. I might have added a significant figure in there. So maybe it's just 1.1. All right, and that'll be in meters. And that's now the displacement. That's how far it'll go before it comes to a stop. Number 6. The same rocket sled drawn in figure 4.30 is decelerated at a rate of 196 meters per second squared. What force is necessary to produce this deceleration? Assume the rockets are off and the mass of the system is 2,100 kilograms. All right, so let's just write down what we're given. So it says that there's a deceleration the object is experiencing. Now, if it's a deceleration, why don't we make that acceleration value negative? We'll assume it's moving to the right, okay? So that means that the acceleration in that x direction will be a negative 196 meters per second squared. Okay, wonderful. Now it says what force is necessary. So we're looking for the force value, or in other words, we're looking for the sum of the forces, right, in that x direction. And it also says that the mass of this object is going to be 2,100 kilograms. So it looks like we have everything we need. We got all the units appropriate, and we can use equation number 1 over here on the right-hand side. So the sum of all the forces in the x direction, should equal the mass multiplied by the acceleration in that x direction. So the sum of all the forces in the x should equal the mass of 2,100 kilograms multiplied by negative 196. All right, great. So simply take out your calculator now and plug that on in. So 2,100 times negative 1.96, 196. What am I talking about, guys? So we got negative 4.12 because we need, well, actually, should really be 2 significant figures. Yeah, so 4.1, negative 4.1 times 10 to the 5, it looks like, times 10 to the 5, and that'll be in newtons, all right? The sign makes sense. There should be a negative force because there's a negative acceleration. If you look back to this formula, the mass here will be sign less, right? It's not negative, it's positive, but it'll never be negative. So in order for, if A is negative, there must be a net external force in that same direction, also negative. Number 7, letter A. If the rocket sled shown in figure 4.31 starts with only one rocket burning, what is the magnitude of its acceleration? Assume that the mass of the system is 2,100 kilograms and the thrust is 2.4 times 10 to the 4 newtons, and the frictional force opposing the motion is known to be 650 newtons. All right, so let's just draw a simple diagram here. All right, so we know that the thrust of the engine, right, is going to be, where was it, 2.4 times 10 to the 4 newtons. So let's draw that in our diagram here. All right, so this vector will represent the thrust. I'll call it T. Now remember, since it's in newtons, maybe I'll just call it F. I'll call it F1. All right, if it's in newtons, it is a force. So don't get confused with the word thrust or force. It's the same thing. So this is going to be 2.4 times 10 to the 4 newtons, okay? And that there's a force of friction opposing this motion. Opposing meaning it's in the opposite direction. And the magnitude of that force, as they mentioned, which is the force of friction, is going to be equal to 650 newtons. Now remember, since it's pointing in the negative x direction, when we do our calculations, we would put a negative sign in there, okay? So if these are the two forces acting on the rocket, can we find the sum of the forces? Sure, of course we can, right? The sum of the forces in the x direction here should equal the sum of force 1, or should equal force 1 plus this force of friction, right? So the sum of the forces in the x direction should equal 2.4 times 10 to the 4th plus negative 650. Easy. So the sum of the forces now in the x direction will equal, so let's just do the math. So 2.4 times 10 to the 4 minus 650. We get a value of so I need 2 sig, well, it should only be 2 sig figs according to what they're giving me. So it should be 2.3 times 10 to the 4, and that's in newtons. So this is the sum of all the forces, okay? Now, knowing the sum of all the forces, can we now find the acceleration? Sure, right? How can we find that acceleration? Well, because remember, we have this formula. The sum of all the forces in the x direction is equal to the mass times the acceleration. So let me write it down. Sum of all the force in the x direction is equal to the mass of the object multiplied by the acceleration of that object in that same direction. So we have 2.3 times 10 to the 4 is equal to, what's the mass of the rocket? They told me it was 2100. So 2100 and times AX. So simply divide out the 2100 from both sides. And we realize that the acceleration is going to be, so 2.3 times 10 to the 4 divided by 2100. So it comes out to be 11 meters per second squared. And it's positive because the net force is positive as well. So that takes care of letter A. And then to letter B, why is the acceleration not 1/4 of what it was when all rockets were burning? So I guess, right, the acceleration, if you took this and multiplied it by 4, it wasn't equal to the value that they had in the problem. I didn't even review that, but we can just say something that we don't really have to. We could just say something like, well, I guess the frictional force doesn't increase or decrease linearly as the acceleration increases or decreases. Number 8. What is the deceleration of the rocket sled if it comes to rest in 1.1 seconds from a speed of 1,000 kilometers per hour? Such a deceleration caused one test subject to black out and have temporary blindness. Sounds like fun. So here's a picture. This dot here will represent the rocket ship. It's initially traveling at a velocity of 1,000 kilometers per hour. Eventually then, over a certain distance, whatever this is, it will come to rest, right? So its final velocity here will be 0 meters per second. And the time it takes to go from this velocity to this velocity is 1.1 seconds. So that sounds all fine and dandy. So I realized one thing before I even start thinking about formulas. I realized that this is a time in seconds. The time in the velocity here is in hours. So I don't like that. I got to have consistent units. So let me just convert this kilometer per hour into meter per second. All right, so to do that, let's get rid of the kilometers first. So they go on the bottom, meters on the top. There's 1,000 meters in 1 kilometer. So they go bye-bye. Next, so I'm going to leave meters alone. Now I'm going to focus on my hours. So in order to get rid of hours, I actually have to put them in the numerator, right? Because they're in the denominator currently. And I know the relationship between hours and minutes. So I'm going to write 60 minutes in 1 hour. So the hours cancel. I have minutes now, but remember I want to get rid of minutes, I want seconds. So I put minutes in the numerator so that they cancel, and there's 60 seconds in a minute. And that goes away. Okay, so now all we got to do is just calculate. So we'll take 1,000, multiply it by 1,000, and then divide it by 3,600, because that's 60 times 60. So we get, and we'll do three significant figures, all right? So we'll do 278 meters per second. Okay, so this is the value I'm going to use now in my calculations. So now we got to think, do we know a formula, all right, that relates the initial velocity, time, final velocity, and I am looking for my acceleration? Sure. Equation number 1 over here at the top, right? So it says that the final velocity should equal the initial velocity plus the acceleration multiplied by time. Okay, so the final velocity is 0. The initial velocity is 278, right? That's in meters per second. My acceleration I'm trying to find, and the time was 1.1 seconds. Okay, so I guess, right, we can do either one. Why don't we subtract the 278 on over? Subtract 278. So now we get negative 278 is equal to 1.1a, right? Just disregard the s here. That's just the time unit. I put it in, but I didn't mean to. All right, divide by 1.1 on both sides. So now my acceleration will be 278 divided by 1.1, and it is negative, right? So this is going to be negative 252. So this is negative 253 if I consider rounding. 253 meters per second squared. Now that should make sense. It should be negative, right? Because I assumed that the rocket was traveling to the right. Therefore, if it's slowing down, there must be an acceleration pointing to the left. And that would imply a negative sign here. Number 9. Suppose two children push horizontally but in exactly opposite directions, and on a third child in a wagon. The first child exerts a force of 75 newtons, the second a force of 90 newtons, friction is 12 newtons, and the mass of the third child plus the wagon is 23 kilograms. All right, letter A, what is the system of interest if the acceleration of the child in the wagon is to be calculated? Well, if that's what we want to calculate, then that is the system of interest. The child in the wagon, that is to be calculated. Okay, letter A is done. Letter B, draw a free body diagram. Okay, so let's just draw a little picture here. So it appears that we have a child in a lopsided cart. Okay, so here's the child, right? So this child in the cart, right, has a mass, as it said over here in the problem, mass of the third child plus the wagon is 23 kilograms. So this whole thing weighs 23 kilograms. Now there is a second child. Now it doesn't matter how I organize them, okay? But let's say there's a second child now pushing the wagon this way, okay? And the force that this child is exerting, it doesn't matter if I do 75 or 90. Let's just do 90. All right, so this is the 90 Newton child. And then there is a second child now on the opposite side of the cart, it says, pushing in the exact opposite direction, and they're applying a now 75.0 Newton force. Let me just leave all the point zeros out. Okay, so now, then it also tells me something about friction, but let me stop here for a second, okay? If I now had to consider, like let's say a free body diagram where I can use my axes, okay, to represent this, let me do it in black. All right, so here I have one child in red now pushing this way, right, on the cart, okay, applying 90 newtons. I have another child then pushing this way, right, with a value of 75 newtons. Now, if I ask you, forget about friction, which way is the cart going to move? Well, it's going to move to the right, correct? Why? Because there's a greater force. Okay, so since there's when I sum these two forces up, since there is a net positive force, that's the sum of all the forces in the x direction, I therefore then will have an acceleration in that same direction, in the positive x direction. All right, easy. Now we have to think that way in order to figure out where and how should I put now the force of friction, the 12 newtons. Because remember, friction, right? Friction opposes motion. It's relative, All right. So what I mean by that is you have to know what way the object is moving in order to place friction in appropriately. So if the object is moving to the right, that means friction will point to the left. Okay, so now I know how to plug this in. I'm just going to put it down here, all right, just below it so we can see. All right, but it's starting at the origin, right? And now that force, it told us, was 12 newtons. Okay, so now when I incorporate now the net force, right, how do I sum this up? Remember that everything pointing to the left here is going to be negative. Okay, so if I want to now talk about the sum of all of my forces in the x direction, right, I would have to then take, let's say, the force of child 1 plus the force of child 2, right, and then plus the force of friction, right, force of friction. Okay, so let's do that. So the sum of all the force in the x direction will equal, it'll be 90 newtons, plus negative 75, right? And then plus negative 12. So the sum of all the forces in the x direction now will be, just take out your calculator, 90 minus 75 minus 12 is equal to 3. So there's a net force of 3 newtons, and it's positive, so that means it's net force to the right, which we should have anticipated. Okay, so now that I know that, I can now calculate the acceleration. How? Well, I know this formula, remember? The sum of the force in the x direction will equal the mass of the object that's accelerating multiplied by the acceleration of that object in that direction. So this is 3 newtons. Okay, really I should have said probably 3.0 for significant figures. It doesn't matter. Doesn't matter. So then the mass, what's the mass of interest? As we talked about, the mass of interest that we're trying to find, or that we're trying to calculate the acceleration of, is the cart plus the child, which they told us was 23 kilograms. All right, so this is 23 kilograms, and now the acceleration is what I'm looking for. So simply divide out the 23. So the acceleration of that child in the cart is going to be 3 divided by 23, and 0.13. So we get 0.13 meters per second squared. That is the acceleration, and it's positive because it's pointing in the same direction as the net force. Okay, so that takes care of letter C. And they said, what would the acceleration be if the friction were 15? So let's not overthink this. Here's the force of friction, right? Pretend it's not there. The object is still moving to the right. Therefore, force of friction will oppose it to the left. Now, instead of this being 12, it's 15. So fine. What happens when we put 15 into the calculations here? What does the net force become? It becomes 0, right? So the sum of all the forces now are going to be 0. And then I have now 0 being equal to 23 times my acceleration. So what does acceleration have to be? Exactly 0. Okay, so that's what happens when the force of friction is 15 newtons. Number 10. A powerful motorcycle can produce an acceleration of 3.5 meters per second squared while traveling at 90 kilometers per hour. At that speed, the forces resisting motion, including friction and air resistance, total 400 newtons. Air resistance is analogous to air friction. It always opposes the motion of an object. What is the magnitude of the force the motorcycle exerts backward on the ground to produce its acceleration if the mass of the motorcycle and the rider is 245 kilograms? All right, so let's just take this apart, all right? So it says that the motorcycle, right, the engine can produce an acceleration of 3.5 meters per second squared. So let's write that. So the acceleration of this motorcycle, I'll just call it in the x direction, is 3.50 meters per second squared. Okay, so that's wonderful. Now, it also tells us that the mass of the motorcycle with the rider is 245. So let's write that down. So the mass is going to be 245 kilograms. Now, just from this information, if the mass of the motorcycle and the rider is 245, and that same motorcycle is experiencing an acceleration of 3.50 meters per second squared, then we will certainly be able to calculate the sum, the net sum of all the forces in the x direction. How? By using our formula over here on the right. So the sum of all the forces in the x direction, meaning the net force on this motorcycle, will be equal to 245 multiplied by 3.50. So the sum of all the forces in the x direction should equal, so let's just take out the calculator, 245 times 3.5. So we get 858, it looks like 858. And that is newtons. That is the net force. Okay, now, it doesn't ask us for the net force, it asks us for the magnitude of the force the motorcycle exerts backward on the ground. Oh, okay. So why don't we now just draw a little diagram here? All right. Now, the net force is positive and it's pointing to the right. Okay. So what I'm going to do is let me just put that net force up here at the top. Okay. So I know any and all forces that I'm going to put into this plane here, I know that they're going to have to sum up so that I get a net vector pointing to the right, and that net vector will be 858 newtons. Okay, so now let's read the problem carefully. So it says at this particular speed, the forces resisting motion, right, are 400 newtons. So if the motion is to the right, where would the forces be pointing that resist that motion? Obviously to the left. So let's draw that in here. So we have now the forces here resisting motion. I'll just call them frictional forces. Okay, that should equal 400 newtons. And we can always remember that that'll be negative, right, when we plug it into our calculations. So now, here's the thing, right? What's the missing force? Well, the missing force is then the force that is used to propel the motorcycle forward. Okay, so let me just draw that in the picture here. So I'll draw that with black. So I'll just put it above the line a little bit. It's a little too crooked for me. That's good. Okay, so here's the force of the motorcycle. All right, that's the part that's not being taken into account. Now remember that this thing is the sum of all the forces in that x direction. Okay, so if we think about it, right, the sum of all the forces in the x direction should equal force 1, right, plus force 2, plus force 3, etc. So the sum of all the force in the x direction should equal, well, let me actually plug in, right, because we know this value, we know the sum. It's 858 newtons. That'll equal, let's say, the force of the motorcycle plus the frictional forces, which are negative 400. Okay, so now how do I solve this? This is a negative, right, obviously, so just add the 400 on over. And this should make intuitive sense. So the force of the motorcycle, right, is 858 plus 400, which is 1258. So it's 1258, right? But let's round a little bit for sig fig, so it's really 1260. Okay, newtons. So this is the force of the motorcycle, but now I know you'll say, well, wait a minute, but that's pointing forward. That's not going backward on the ground. Right. That's the force that the motorcycle is experiencing, but how is the motorcycle producing that force? The motorcycle's tires are essentially pushing back, right, on the ground so that it propels itself forward. In other words, it's literally pushing the earth backwards relative to its motion. Right? The earth isn't really going to change much, but that's actually what's happening. All right? So the value here that we calculated would be the value that the motorcycle exerts backward on the ground. Number 11. The rocket sled shown in figure 4.32 accelerates at a rate of 49 meters per second squared. Its passenger has a mass of 75 kilograms. Letter A. Calculate the horizontal component of the force the seat exerts against his body. Compare this with his weight by using a ratio. All right, so here in the picture, the box will represent the spaceship and has an acceleration going in the positive x direction, we'll say, of 49 meters per second squared. Right? The individual here has a mass of 75 kilograms, and what we're trying to do is we're trying to figure out what's the force the seat exerts on the person. Now, the force should be in the same direction as the acceleration of the ship. Well, why? Well, think about it this way, right? As the ship accelerates forward, what happens to the person relative to the ship? They move backward, right? So they're going to be pushed into the seat, but they're not going to go through the seat, right? The seat's going to support them. So the seat then pushes back in an equal but opposite direction, all right? So this is really what we're trying to find. We're trying to find the force here, okay? So how do we do that? Well, let's consider our formula over here on the right-hand side, that the sum of all the forces in the x direction should equal the mass of the object multiplied by the acceleration in that same direction, meaning the x direction. So the sum of all the forces, the horizontal forces, right, in that x direction would equal the mass of the object we're talking about, so 75 kilograms, multiplied by its acceleration in meters per second squared, which is just 49. So now the sum of the forces in the x direction should simply be 75 times 49. And we'll do 3 sig figs, so we get a value of 3,680. Okay, and that's in newtons. All right, so this is the force that the seat exerts against his body. That's this vector. Okay, easy enough. Then it says compare this with his weight by using a ratio. Remember the weight formula over here on the right-hand side is W is equal to mg. So W is equal to mg. So to find his weight, we need to take his mass of 75.0 kilograms and multiply it by gravity, right? 9.80, but not negative because we're not considering its acceleration. We're using g. So the weight here is simply going to be 75 times 9.8, and we get a value of 735. So this is 735 newtons. All right, so now we just got to compare the two using a ratio. So I guess just take 3680 and divide it by the 735 to find a ratio. So 3680 over 735. And we get exactly 5, almost, right? So this is 5. So meaning it's 5 times greater the acceleration of the ship, or I should say the force of the ship on the person rather than his weight. Okay? So then that takes care of that. Now let's take a look at part B. It says calculate the direction and magnitude of the total force, aka the net force, aka the resultant force, that the seat exerts against his body. So consider the seat, okay? The seat is doing two things here, right? The seat is exerting a force in the forward direction that we just calculated before, and I'll write that down. It's 3,680 newtons. But the seat's also holding another mass, right? It's also holding the mass and the weight of the person. So the person is sitting down, but the person is not going through the chair. So the chair must be exerting a force upward on that person. How much? Well, it's equal but opposite in magnitude, right, of the weight of that person. So in terms of a free body diagram, let me do it in black. In terms of a free body diagram, right, we would have two forces here. We would have the horizontal force that the seat exerts on the person. That is the 3680 Newton force, and then there's another force, right, that the seat exerts on the person, and it's upward. It's directly upward. Let me make that a little straighter. It's directly upward. And that had a magnitude of, it's the same, remember, as the weight of the person. It's just in the opposite direction. So the weight of the person is pointing down, so therefore the seat is pointing up. So that is 735 newtons. Okay? So now how do I find the resultant of this? Well, easy, right? These are both x and y components. This is the x, this is the y, so we can simply remember our resultant formula, that the resultant is equal to the square root of the sum of all the x's squared plus the sum of all the y's squared. So the resultant vector here should be the square root of 3680 squared plus 735 squared. So the resultant vector here, which by the way is the total force, right? So I'll write F sub t for total force. Square root of 3680 squared plus 735 squared. And it comes out to be 3,750. And that'll be in terms of newtons. Okay, so that is the total force, the net force, the resultant force that the seat exerts on the person. And it says what direction is the net force that the seat is applying to this person, considering both x and y frames. We would simply then do tangent, right? Tan of theta is equal to the y value over the x, assuming this theta, by the way, is in reference to the x-axis. All right, so theta, so let me say tangent here will simply be 735 over 3680. So theta now would be, so simply do this, 735 divided by 3680, and then do the inverse tan of that number. So second tangent of 0.1, really 0.2 because we'd have to consider significant figures, 0.200. So it comes out to 11.3, 11.3. Okay, degrees. Where is this pointing? Well, when you do y over x, it's always an angle in reference to the x-axis. Okay, so therefore if I draw it in my picture, the magnitude of that net vector should be somewhere there, okay, where this is the theta. So this theta value will then be 11.3 degrees north of east. Okay, so that would be these two boxed answers right here would be a complete description of the magnitude and the direction of the total force the seat exerts. The total force is 3,750 newtons at 11.3 degrees north of east. Number 12. Repeat the previous problem for the situation in which the rocket sled decelerates at a rate of 201 meters per second squared. In this problem, the forces are exerted by the seat and the restraining belts. All right, so if you're unfamiliar with problem number 11, check out our video prior. We did number 11. But basically, so this box will represent the rocket ship. The rocket ship now is decelerating, therefore it has a negative acceleration relative to the positive x-axis, that is, and it will be slowing down. So think about this when you're in the car. What happens if you have a quick deceleration? You lurch forward, right? So the person is going to be traveling at a speed forward, okay? Now, obviously, well, unless the seatbelts break or whatever, you don't go flying through the windshield, okay? So we have to draw a seatbelt in here. Look at that. Now that's a safety feature. So that's going to protect this person from going too far forward, right? So this person's still accelerating or traveling at in the forward direction here, but the seatbelt now is going to apply the force so that he doesn't. It's going to apply it backward on him, right? So the force here is going to be the same as the force, since it's essentially part of the ship, right? It's going to be the same acceleration that the ship is experiencing, okay? It's pointing in the same direction. So now how can we calculate this arrow over here, this force arrow? Well, simple, right? Let's remember the sum of all the force in the x direction equal the mass of the object multiplied by the acceleration of that object in that dimension. So here we have the sum of all the forces, okay, is going to equal, in the x direction, because there's only one acceleration in that x direction, will equal the mass of the individual, so 75.0, multiplied by that acceleration of negative 201, okay, meters per second squared. So the sum of all the forces in that x direction will be simply, so 75 times 201, we get 15,000, I'll say 100, okay, 15,100 newtons. Okay, great, and it's negative, right? That should make sense. We mentioned that it's pointing to the left, makes intuitive sense, and the sign concurs. So now, that's great. That's the horizontal acceleration. Now remember, they want to talk about, since we're repeating problem number 11, they wanted to know the net force that the seat is acting on this individual. Now the seat has a seat belt, so that's part of its net force. And remember, the seat is also holding the person up. So the person has a certain certain weight, right? And that's pulling down, but the seat, he doesn't fall through the seat, so the seat is pushing back up on him. Okay? So how do we find that? Well, simple. Let's take a look at the weight formula. The weight of an object is equal to the mass multiplied by the gravitational value. So the weight is going to equal 75.0 kilograms multiplied by 9.80. So the weight of this individual is going to be 75 times 9.8. Now, technically, the weight of that individual, right, will be, so 735, and that's newtons. The weight, in terms of a vector, is pointing down, so therefore it's negative, okay? But remember, we're talking about it from the perspective of the seat, and the seat is actually pointing up, right? It's providing an equal but opposite force because the person is not accelerating anywhere. So these now would be, so essentially now the sum of all the forces in the y direction, okay, for the seat's perspective should be a positive 735 newtons. Okay, now if I had to draw a quick free body diagram, all right, so let's draw my axes here and here. Okay, let's detail the forces. So we have one force in the negative x direction, so it's pointing this way, right? That has a value of negative 15100, so 15,100 newtons. And then there is a positive force right in the positive y direction, so it's pointing up. Let me make that a little straighter, so it's pointing up. And that has a value of 735. By the way, this drawing isn't to scale. This line should have been much longer. All right. But now if we think about this, what is the total force? These are the two forces the seat is exerting on the person. Okay, so what would the total force be? Remember, whenever they're asking for total force here, they're really asking for the resultant force. Okay, so the resultant force, if I had to guess, right, if I had to draw it in this picture, it should be somewhere around here. It should lie closer to that x-axis than it does to the y-axis, because the x value, although I crossed it out partially, is significantly larger. Okay, so now to calculate this resultant vector, simply take the sum of all the x values squared plus the sum of all the y values squared, and then just square root them. Okay, so the square root of negative 15100 squared plus 735 squared. Okay, so just take out the calculator, plug that bad boy on in. So we get 15100 squared plus 735 squared. And it comes out to a value of 3 significant figures we're going to do. So well, it's so close, right, to the 151. All right, I'm going to go out a little more just so we can see the difference, all right? So 15118, let's call it. Even though that's not the right number of significant figures, it's fine. So that is in terms of newtons. Okay, that would be the total resultant force that the seatbelt imparts, all right, onto this individual. Now we would also then have to calculate this theta. Okay, so how do we do that? Simple, use tangent, right? Tan of theta. If my angle is in reference to the x-axis, then I can simply do the y value over the x value and just take the square root. So we don't need negatives and positives in here. So the tangent of theta will be equal to the 735 all over the 15100. So we'll calculate it like this. Take 735 divided by 15100 and then do the inverse tangent of that. So second tan of 0.0487, we'll call it. So 7.89, right? Excuse me, 2.79. 2.79, and that is degrees. Okay, so that's the angle. That does make sense, right? Because this x value is tremendous, much larger than that y value. I was even trying to show it in the picture that it's going to be small. Obviously, that's not to scale. Now, to finally give the, I guess, direction to the magnitude of that angle, I would then be calling it north of west, right? So the final answer here for the resultant vector, all right, should be 15118 newtons at 2.79 degrees north of west. The end. Number 13. The weight of an astronaut plus his spacesuit on the moon is only 250 newtons. How much do they weigh on Earth? All right, so let's come up with a couple of formulas, and we actually need an extra piece of information here. We also have to know that the G, or the gravitational force on the moon, so G sub m, is really 1/6 of the gravitational force on the Earth, or aka is equal to the gravitational force on Earth over 6. Okay, so just keep this in mind. We need that. So let's actually create two equations. So we have the weight of the astronaut on the moon should be equal to the mass of that astronaut multiplied by the gravitational force of the moon. Okay, and we can also write the weight of the astronaut on Earth should be equal to the mass of that astronaut multiplied by the gravitational force of Earth. Okay, solve both of these for m. So that means that we have the weight of the astronaut on the moon divided by the gravitational force of the moon would equal m. Okay, and here we're going to have the weight of the astronaut on Earth divided by the gravitational force of the Earth is equal to m. Now, since these two things are both equal to m, you can set these now equal to one another. All right, so let's do that. So we have the weight on the moon divided by the gravitational force of the moon will be equal to the weight on the Earth divided by the gravitational force on the Earth. Now, what do they tell us? Let's take it piece by piece, okay? First, the weight on the moon. Did they tell us that? Well, yeah, 250 newtons. That's a weight. That's in newtons. So that value, 250. Do we then know the gravitational force of the moon? Well, we don't know it, but we do know it in terms of a relationship. Well, we actually do know it, right? Because we're going to plug in the value for G sub E. But we do know it as a fraction of the gravitational force of the Earth, right? So remember that this should simply be, so all I'm going to do here is I'm going to substitute GE over 6, okay, in for that. So we got a gravitational force of the Earth over 6, okay, that should equal now the weight on Earth, we don't know, and then the gravitational force on Earth, we do know, right? But we could just even leave it GE, okay? Now, for some simple math here, all we have to do now is realize that we have 2 gravitational Earth constants here, right? So just cancel them. They will cancel. It's like saying 1 over 5 is equal to, I don't know, 1 over what? Well, obviously it's going to be 5, right? And if you cancel them, the equation is still true. 1 is equal to 1. All right, so that's basically what I just did. So now this math works out to be, so 250, right, 250 now equals, right, remember this is really divided by 1/6, okay, is equal to WE. So now simply solve. We can solve it, right? So the weight on Earth should be 250 divided by 1 divided by 6. 1,500. So we got a value of 1,500 newtons. That's the weight of this astronaut on Earth. Okay, that took care of that. Now it says, what is the mass on the moon? Well, guess what? Mass doesn't change, okay? The mass on the moon is the same as the mass on Earth, is the same as the mass everywhere, okay? Mass is not influenced by gravity, only weight is. So therefore, what I'll do, it doesn't really matter. I'll use this formula, okay, to help me solve for the mass. Although they're asking me it for the mass on the moon, it would be the same as the mass on Earth, okay? So the weight of this object on Earth should equal the mass of the object times the gravitational constant of Earth. All right, so here we have 1,500 is equal to m times 9.80. Easy, right? Divide out the 9.80. And now the mass of the object on Earth, on the moon, everywhere, is going to be 1,500 divided by 9.8. We'll do 3 sig figs, so 100 or 153, and that's in kilograms. That would be the answer. Number 14. Suppose the mass of a fully loaded module in which astronauts take off from the moon is 10,000 kilograms. The thrust of its engines is 30,000 newtons. Calculate the magnitude. I think that's an error. Calculate the magnitude of the acceleration in a vertical takeoff from the moon. All right. So here I have a little picture. The moon is in black. All right. The thrust from the engines, that's not the net force on the object. That's just the thrust from the engines, is 30,000 newtons. I have that here. And the mass of the spaceship is going to be 10,000 kilograms. All right. So remember, in order to figure out the acceleration, take a look at the formula on the right-hand side, I need to know the sum of all the forces in that particular direction, right? And let me use y for this problem, just because that's the dimension I have this in. So the sum of all the forces in the y direction should equal the mass times the acceleration in the y dimension. Fair. Easy enough. Figure out A, I got to know all the forces. But here's the thing. They only told us the thrust force. That's not the total force. Why? Because this thing has mass, right? It has a weight to it. The moon is also pulling down, right, on this object, okay? And that I didn't take into account yet. All right. So how do we do that? So remember, I can simply do that by, first let me do a free body diagram. All right, so let me just draw that over here. So we got the thrusters pulling up, right, with a certain thrust, and that's going to be 30,000 newtons. And then there's going to be the weight of the spaceship, right, the gravitational force of the moon pulling it down. And that I don't know what it is, but that's easy to find, right? Look at the formula. W is equal to mg. So let's write that. W is equal to mg. So the weight of this object is the mass, which is 10,000 pounds, or excuse me, kilograms, multiplied by the gravitational constant. Now remember, the gravitational constant, this is on the moon, okay? So there's the weight on the moon. So what that means is, remember, the moon's gravitational field will be 1/6 as strong as Earth. So therefore, it would be the gravitational force on Earth divided by, or the gravitational acceleration on Earth divided by 6, okay? So what is GE? We know what that is, 9.80, right? That's what you should have seen now about 10,000 times, considering how many problems you should be doing, right? So 9.80 over 6. Now just plug this thing into the calculator and let me know what you get. I won't be able to hear you, but you can still let me know. So 10,000 times 9.8 divided by 6. And we have, and we'll do 3 significant figures here. So we got 16,300. Okay, that's in newtons. So that is this force down here. It's 16,300 newtons. So what's the total forces, or what's the sum of everything? Well, I'm going to break this up now, right? And I can break up all the forces into being the force of the thrust plus the force of the weight should equal now the mass times the acceleration in the y dimension. So the force of thrust was a positive 30,000. The force of the weight was negative because it's pointing in the opposite direction, 16,300, is equal to the mass, right, which is 10,000, times the acceleration in the y direction. So what do we get here? So it's 30,000 minus 16,300. So this works out to be 13,700, right, is equal to 10,000 AY. So divide out now the 10,000. Divide out now the 10,000. And the acceleration in the y direction is now equal to 1.37 meters per second squared. That would be the acceleration of the ship. All right, so that is the acceleration. That's letter A. Now for letter B, it says, could it lift off from the Earth? If not, why not? And if it can, calculate it. So we have to go through the same free body diagram, okay? But this time, except it's going to be on Earth. So let's create it, okay? So the thrust is still the same. The engines haven't changed. What that means is that the upward thrust here is still going to be 30,000 newtons, okay? But now the mass, the mass hasn't changed. The weight of the object has changed. Why? Because it's in a stronger gravitational field. So that due to Earth, we got to find it. How do we find it? Same formula. The weight on the Earth is equal to the mass of the object multiplied by the gravitational acceleration due to gravity on Earth. So the weight on Earth will be 10,000 times 9.80. So what does that come out to be? So the weight on Earth, right, will be, let's see, what do we get? 10,000 times 9.8. We don't even need the calculator for it, right? 98,000. 98,000 newtons. This looks interesting, right? So the weight here is going to be 98,000 newtons. So we don't even need to go any further. Just take a look at your free body diagram. The net force is going to be pointing in which direction? It's going to be pointing down, right? The net force is pointing down. When you sum these two vectors, well, not at an angle, it's going to be pointing straight down, right? When you sum these two forces together, the sum or the F net, right, which is the same thing as the sum, okay, they're going to be negative, pointing down. If the force is pointing down, where's the acceleration? Also pointing down. Therefore, it can't lift off. It doesn't have a positive acceleration in the positive y direction. Guys, thanks for tuning in. Hopefully this helped. Please hit that subscribe button. That would be awesome. I would thank you very much, and I will see you in the next lesson. Number 15. What net external force is exerted on a 1,100 kilogram artillery shell fired from a battleship if the shell is accelerated at 2.4 times 10 to the 4 meters per second squared? All right, so let's first start with that. So let's list what we know. We do know the mass of this artillery shell, right? It's 1,100 kilograms. Okay, we also know the rate at which it is accelerating. Let's just assume it's going in the positive x direction. So it's 2.40 times 10 to the 4 meters per second squared. If I got to find now the net force on it, right, it means find the sum of the force. Okay, so do I have an equation that relates those three variables? Of course I do, right? It is this one. Sum of the forces in the x direction is equal to the mass of the object multiplied by the acceleration in that same direction. So the sum of all the forces in the x direction here should be the mass of 1,100 multiplied by 2.40 times 10 to the 4. Okay, all the units work out. So the sum of the forces here will be 1100 times 2.4 times 10 to the 4th. So we just add essentially 3 to that exponent, right? So it's going to be and then multiply by the 100. So it's going to be 2.64 times 10 to the, should be 7th. Let me just double check. 3, 6, 7. Great. And that is in newtons. Okay, so that's the net external force. Now it says for it's not even part B, but it says then what is the magnitude of the force exerted on the ship now by the artillery shell? So this is basically simply Newton's third law, right? Equal but opposite forces, okay? So if the artillery shell is fired from a battleship and it has a force of positive 264 times 10 to the 7 newtons, then the opposite force would be now the magnitude of the force exerted on the ship by the artillery shell. That should simply be just negative 2.64 times 10 to the 7th newtons. Number 16. A brave but inadequate rugby player is being pushed backward by an opposing player who is exerting a force of 800 newtons on him. The mass of the losing player plus his equipment is 90 kilograms, and he is accelerating at 1.2 meters per second squared backwards. Letter A. What is the force of friction between the losing player's feet and the grass? All right, so let's draw a very straightforward, just a little diagram here. This point will represent, I'll call that the losing player. This point will represent the winning player. They're in a match of rugby, right? They're playing the game of rugby, so therefore they're kind of mashed up in between, and they're both pushing on one another, and it appears that the winner is winning, okay? And the winner is exerting an 800 Newton force on the loser. So now, when I think about the forces, and I'm going to draw a little coordinate plane here, and this particular point will represent the loser. When I think about the forces acting on him, first thing I have to show is the 800 Newton force. Now that force is pointing backward. Okay, why? Because the winner is exerting that force on the loser. And also remember that they're accelerating backwards, right? So that would make sense. So here this particular force is 800 newtons. Okay, great. Now it also tells us that the acceleration right here is also backward. Okay, so what that means is the system is moving backwards. So I'll write acceleration is equal to 1.20 meters per second squared. And now it wants us to find the force of friction between the player's feet and the grass. So remember, friction always opposes the motion. So if the loser is accelerating backwards, then the force of friction must be pointing in the opposite direction. Okay? By the way, it's not drawn to scale. The arrow should definitely be smaller. Okay? Why? Because there's a net direction. There's a net force in the left-hand direction. Why do I know that? Because the acceleration is that way. So here's the force of friction. So this whole diagram now completely describes the forces acting on the loser and the acceleration of the loser. So let's now take a look at the force. Some of the forces in the x direction will be equal to the mass times the acceleration in that x direction. So what are the forces? Again, we spoke about this. The force of friction is positive. All right, why? Because of the direction it's pointing in. I know usually you might be used to seeing it being negative, but in this case he's being pushed backwards, so I have to appropriately represent that. So the 800 Newton force, all right, is the force that's backwards, so that's negative. The mass of this player plus his equipment was 90 kilograms, and then the acceleration, here's the thing, you got to plug in that negative sign, 1.20. Why? Because he's accelerating to the left. So to solve this, it's simple now, right? Just add the 800 on over to the right-hand side, and now let's just do the math. So it's 90 times negative 1.2 plus 800, and we get 692. So the force of friction on the loser is going to be 692 newtons. All right, so we took care of that. So that answers letter A. Okay, so now let's take a look at letter B. So it says, what force does the winning player exert on the ground to move forward if his mass plus the equipment is 110 kilograms? All right, and then C is just sketch the situation, but that's what I'm doing in each part anyway. So now let's take a look at a free body diagram from the winner's perspective. Okay, so this was all letter A. Sorry, this was all letter A. Now let's take a look at letter B. So let's draw a coordinate system for now the winner. Okay, so this represents the winner. All right, so here's our point right here. Now remember, not only is the loser being accelerated backward, right, but since it's rugby, they're kind of tied together, right, essentially, right? They're almost wrestling, and therefore the acceleration of the winner is also in the same direction. So I do know that. So let's write that here. So the acceleration here is 1.20 meters per second, meters per second squared. Okay, great. So now we have to figure out, well, what force does the winning player exert on the ground to move forward? Okay, so here's part of the trick here, all right? So the winning player will be exerting the force on the ground, but then the ground will be exerting the force on the winner, right, in order to propel him essentially forward. So what direction will that force be acting on the winner? Now remember, in order for the winner to move, in order for the winner to move to the left, there has to be a net force to the left, right? So what's happening is the winner's pushing backward, or meaning backward compared to the motion, okay, because he's moving to the left. So the winner is pushing backward on the ground, and then the ground is pushing forward, but in an equal but opposite right direction. That's Newton's whole third law there, okay? So what that means is that we should have a net force in the left-hand direction, okay? So let me detail that here in the diagram. So now here, this will represent now the force, right? This will represent the force the winning player exerts on the ground. So I'll say this F sub G. Okay, so that's the force that the winning player exerts on the ground. Okay, great. Now, also remember, if the winning player, right, and here's part of Newton's third law again, if the winning player was exerting an 800 Newton force on the losing player, right, but then what that means is that the losing player would be exerting the same but opposite force on the winning player, right? So that being the case, we would also have a vector here that would be pointing backwards, and that value is 800 newtons, okay? Remember, why is that the case? That is the case because since the winner is pushing on the loser with 800 newtons of force, according to 800 newtons, according to then Newton's third law, the loser must be pushing back on the winner with that same amount of force of 800 newtons. Okay, so that's this second part is where this vector comes from, right? You see how they're both pointing in the same direction? And then the first vector is where this one came from. Okay, so now we have everything we need. We also know the mass of the winner, so now we can just plug it all in. All right, again, we're going to use the summation of the forces in the x direction should be equal to mass of the object that is accelerating multiplied by the acceleration of that object. So what are the forces in the problem? Well, now it's a positive 800, right, minus the force that the player exerts on the ground, or in essence, that's really the force that the ground exerts on the player, right, technically. However, though, remember, the force that the ground exerts on the player here or on the winner would be the exact same as the force that the winner exerts on the ground, right? Newton's third law. Remember, it's always important to be thinking about what forces are acting on the system of interest, not by the system of interest. So the mass is 110, and then the acceleration, again, it's still negative 1.20. All right, be careful with the signs there. So now when we do the math here, right, let's subtract over this 800. All right, let's subtract the 800 here. That cancels. Now we have a negative FG. Okay, so now it should be 110 times negative 1.2 minus 800. And we get negative 932, right? Negative 932. Okay, so now taking care of these signs here, all we now need to consider here is going to be to just get rid of the negatives, right? So the force, Sorry, the force that the ground exerts on the player is going to be a positive 932 newtons. And that should take care of that. Number 17. 2 teams of 9 members each engage in a tug of war. Each of the first team's members has an average mass of 68 kilograms and exerts an average force of 1,350 newtons horizontally. Each of the second team's members has an average mass of 73 kilograms and exerts an average force of 1,365 newtons horizontally. Letter A. What is the magnitude of the acceleration of the 2 teams? Letter B. What is the tension in the section of the rope between the 2 teams? Okay, so here I have on the left-hand side, I kind of did a little math out prior, right? So here is team 2 I chose to place on the left and team 1 on the right. Doesn't matter if you have it flipped, all right? But the average mass per person was 73 kilograms. There's 9 people. Therefore, the total mass on the left-hand side is 657. And again, each has an average or exerts an average force of 1,365. Multiplied by 9, we get 12,290. And then the same thing for team 1. Okay, average was 68, multiply it by 9. And the average applied force is 1350 and multiply that by 9. All right. So now, question is a little tricky, but what is extremely important here is to have the correct free body diagram. Okay. Now, how you want to think about this tug of war is you want to think about the tug of war occurring at 2 ends of a particular rope. All right. So if we think about it that way, we're essentially going to have, we could create one free body diagram, but you really want to think about it as 2 free body diagrams, one here and one here. If you were to combine them, you're going to lose the subtlety of the tension that's created. Okay? Love it when there's a little tension, right? Anyway, so let's first take a look at the free body diagram for the red team. Okay? So let's draw our axes. So I'll draw it here and here. Now the applied force, now remember it's a tug of war, right? So the applied force that this team will be exerting will be to the left, okay? And that applied force is the total force that we calculated here at the bottom, the 12,290. So let's plug that into the chart, okay? So we can call this, it doesn't matter, F1, all right? So this is 12,290. I'm going to leave out the units, but they're in newtons, okay? So, great. Now, let's start drawing the free body diagram. There's something else I have to draw there, but let's start by drawing the free body diagram now of the second team. So we have a axis over here. Let me make it a little more centered. That's good. So now the second team, right, is exerting a force in the opposite direction here. And the total force that that team is exerting, call it F2, is going to be 12,150. 12,150 newtons. Okay, now, if I were to just have these 2 forces in the picture, okay, what does this imply? Well, this implies then that the rope in between connecting these 2 teams together is going to break, right? But the rope is not going to break, all right? There has to be some other force going on within the rope itself that's holding the rope together. All right, so in the reference to the whole problem, right, if I look at the whole problem, I know there will be an acceleration because the forces are not balanced. But within the rope itself that's connecting the 2 teams, there is an equilibrium relative to the entire problem. The rope is not breaking, right? The rope is moving with the system, but it's not breaking. It's being held together. So therefore, there must be some equilibrium force going on inside of this rope that's keeping it together. Guess what that's called? Tension, right? That's the tensional force. So the tensional force will oppose the applied force. So meaning if there's a force of 12,290 newtons to the left here, there's going to be a tensional force in the rope to the right-hand side, okay? Or another way to think about it is that since this team is pulling to the right, there should be a force being applied here to the right as well, but it's not this value, okay? It has to be, remember, they have to be balanced within the rope itself. If I place this value here, that means the rope is going to break, okay? So What force is it? What's the magnitude? Guess what? I have no idea. All right, so we're just going to call it T. But I do know that the tensional force that is being experienced on this side of the rope is the same, but opposite, as the tensional force experienced on the other side of the rope. So I'll call that T as well. Now, this is important. I'm taking it a little slower because this is an important idea to develop. This is basically Newton's third law going on in the rope. Okay? So, why don't we now create our equations? Okay? So, all right. So let's create the equation for this particular free body diagram. Right? So we have the sum of the forces. Right? Sum of the forces in the x direction should equal ma, x. Okay? I could put little 1 down here and 1 down here. Okay? And then a 1 for the mass. So what are the sum of the forces for number 1? Well, let's just take a look at these two. So it should be, right, negative 12,290 because it's pointing to the left, plus my tensional force should equal the mass of the whole team, right, of the whole team 1, which was 657, so 657 times A, right, X. And we could say 1, okay? So that's good. Now, why don't we develop the second equation for that team, for team 2? So for team 2, we're going to have sum of the forces, right, in the x direction of team 2 should equal the mass of team 2 multiplied by the acceleration in the x direction of team 2. Okay. Now, so the sum of the forces here, right, the force now is positive, the applied force, so that's going to be 12,150. Oop, I don't need the sum sign there. So 12,150 plus then, or I could put plus a negative tension, right, because it's pointing to the left. I'm just going to write minus T is equal to then the total mass of team 2, which is 612. So we've got 612 times then AX2, right? Okay, so does that make sense so far? So now here's the thing, all right? I know they asked question A first, but it's probably better we actually start with question B to find the tension, okay? Now, how do we do that? Well, we have two equations with two unknowns. So how do we solve that? Now, it really doesn't matter, honestly. If you set the tensions equal, right, that's fine, or you set the accelerations equal, it doesn't really matter, quite honestly. I don't know. What do you guys want to do? Yeah, you know what? Why don't we, let me first start by doing letter A. I changed my mind. So let's take this first equation, let's solve it for tension. Okay, so I just have to add this, right, on over. So plus the 12,290. Okay, that cancels. Now I have tension is going to equal 657 AX1 plus 12,290. Okay, now great. Now let's substitute this into my second equation for tension here. Okay, so let's do that. So now it's going to be 12,150 minus, careful with your parentheses here, 657 AX1 plus 12,290, close the parentheses, equals 612 AX2. Now you might say, well, wait a minute, Andrew, hold on. You said we only have two unknowns in the problem, but wait, I see a tension and tension, they look the same. But then I see AX1 and AX2, are they the same or are they different? They look different to me. Well, on the page they look different because one is AX1 and one is AX2. But remember, in a tug of war, okay, assuming the rope holds, which we are in this case, the acceleration experienced by Team 1 will be the same as the acceleration experienced by Team 2, right? Either the tug of war is going to move to the left, the whole system, or it's going to move to the right, accelerate to the right as a whole system. So I know that they're the same for that reason. So what I'm going to do now when I start cleaning this up, I'm just going to call it A. Okay? I could leave it as AX, but I'm just going to call it A for acceleration. All right? So why don't we start to now start cleaning things up a little bit here. So we got 12,150 minus 657 A. So basically I'm just distributing the negative here. Minus 12,290 is going to equal 612 A. Right, so now what am I going to do? Let me add this on over, 657A plus 657A. I combine these two like terms, right, in the numerator, not in the numerator, on the left-hand side. So we have 12,150 plus 12,290. So we get 24,440, so 24,400 and, made a mistake, and 40 is equal to now, so we just add those two together, right? So we get 1269A, right? 1269. So I'll just double check because I don't want to make a silly mistake. 1257. Oh, and I made a mistake in the calculator instead. So 612 plus 657. Yeah, 12. Yeah. Okay, so we're good there. Now how do we solve for A? Obviously just divide out the 1269. Divide out the 1269. Oops. I realized I made a mistake, guys, right? Because I'm constantly checking over my work. So I was just seeing if you guys were paying attention. I apologize about this. What's wrong? What's wrong with the math I did here? This should have been a subtraction. Instead, good old Andy did an addition. So, you gotta love this. I don't really have to erase too much. Just hit the back button. So I apologize, guys. So let's subtract the two, huh? So we have 12,150 minus 12,290. Oh man, been a long day. Negative 140. That should then equal what I had before, which was the 1269. So 1269A. Now divide out the 1269. Divide out the 1269. Okay, so now we're going to find our acceleration. So let's see what that is. So 140 divided by 1269. 1269. And that's going to be negative 0.11. Okay, negative 0.11 meters per second squared. All right, now how did I catch my mistake? Well, because when I did the math here, I realized that my answer was positive. But if I'm looking at the system overall, right, there's a greater force on the left-hand side than the right-hand side. So my acceleration should come out to be negative. Okay, so I realized once I got to the end and looking at it, I would get a positive answer. It doesn't make sense given how I set up the problem. Therefore, I know I made a mistake. And then my job there is to figure out where the mistake is. So that's kind of why also understanding the concepts behind this are important, because everybody's human. You're going to make a silly mistake. The only question is, are you going to catch it? All right. If you catch it, you get an A. If you don't, maybe you don't get the A. All right. So here's the acceleration, negative 0.11 meters per second squared. Easy peasy. Now, how do I find the tension? Well, you can now take either equation you like that we created first, right? Either this one, or you could take this one and simply plug in that acceleration. So why don't I just take, it doesn't matter, I'll just take this one. All right, so we got 12,150 minus t is equal to 612 times now the acceleration, which I found, which is negative 0.11. Okay, 12,150 minus t, let's clean it up. So we got 612, 612 times 0.11, 612 times 0.11, and it comes out to be negative 67 or so, 67.3. I probably should use 2 sig figs, right? It doesn't matter, whatever. It's so weird. At the end of this course, nobody cares about sig figs anymore. 67.3 plus 67.3. So here now I'm going to, let's see, what are we going to do? And then I have to add the t on over, right? Add the t on over to the right-hand side. So we get t, the tension will equal. So we got 12150 plus 67.3. So we get a value of 12,000, so approximately 12,200 or so. 200. Okay, and that would be in newtons. All right, scientific notation would be 1.2 times 10 to the 4 newtons. That would be the tension. All right, guys? So important problem to understand. A little confusing there with the tensional aspect, but if you notice, once we're able to wrap our head around the concept, I mean, the math is relatively straightforward. just a simple system of equations. Number 18. What force does a trampoline have to apply to a 45 kilogram gymnast to accelerate her straight up at 7.5 meters per second squared? Note that the answer is independent of the velocity. Okay, fine. So first thing, as in pretty much all problems, especially for force problems, free body diagram. All right, so draw a set of axes, x and y. Now, let's take this particular point right there in the middle to be the gymnast. And what are the forces acting on the gymnast? All right, there is actually going to be two forces, right? Why? Well, gravity's pulling, right, on the gymnast, okay, and the trampoline's going to be pushing her up. So if you think about it, the trampoline has to not only overcome the force of gravity pulling her down, but it also has to accelerate her then 7.5 meters per second squared. So the free body diagram here is an arrow straight down. That will represent the weight of this gymnast, right? So W is equal to mg. And then the force pointing straight up will represent the force that the trampoline applies. Now, I'm not drawing this to scale, right? I mean, really, if I were to even attempt to, this arrow should be a lot bigger, okay? But this would then be the force of the trampoline, I'll call it. That I don't know what that is. That's what the question's asking. So why don't we set up now an equation? It's an equation in the y direction. So let's use our sum of the force in the y direction is equal to MAY. So sum of the forces, right, in the y direction should be equal to MAY. So what are the forces in the y direction? Well, like I detailed on the left-hand side, there are two. The force of the trampoline, and that's positive because it's pointing up, and then the weight, right, of the gymnast, that's negative, okay, because it's pointing down. So instead of writing the W, I'm just going to write mg in here. Okay, they're the same thing. So that will equal MAY. Okay, let's start plugging some stuff in. So the force of the trampoline, I don't know. The mass of the gymnast, I do know. It's 45.0. Gravity is 9.81. Oh, well, it is in some books. This book, it's 8.0. I keep forgetting. The mass of the, again, same mass. It's still the gymnast here, so it's 45.0 kilograms, and then multiplied by the applied acceleration that the object is experiencing or will experience, 7.50. So now all it is just calculating, right? So we get the force. So we get, the force of the trampoline is equal to, so we get 45 times 9.8, and that's 441, minus 441 is equal to 45 times 7.5. So that is then 337, 338, I got a round there. Okay, and then I add this on over, right? And doesn't that make sense? Isn't that what we were kind of saying before? That not only does the trampoline have to overcome the force of gravity, right? So that's why we're adding it to this. I mean, that's why the math is telling us to add it to the right side. It not only has to overcome gravity, but also has to then impart an acceleration and a net force on this gymnast. Okay, so the answer does sound fairly reasonable here. Okay, so we get 338 plus the 441, so this looks like it's going to be 779 newtons. And that is the force that the trampoline needs to apply. All right, so not too hard, fairly straightforward, easy peasy. What else is easy peasy? Hitting that subscribe button. Number 19, letter A. Calculate the tension in a vertical strand of spider web if a spider of mass 8 times 10 to the minus 5 kilograms hangs motionless on it. All right, so let's detail a simple picture here. So let's pretend this is a spider web, and on the bottom of that, we're going to have this spider-looking thing, sure. So what are the forces now acting on the spider here? Well, there's one force due to gravity, right? The weight of this spider. So one force is pulling the spider down. And that's the force due to gravity, aka the weight of the spider, which is equal to mg, the formula over here on the right-hand side. Then there is another force, right? Since the spider is hanging on it, there's another force, and it's motionless, right? There's another force that's pulling it upwards then. Because otherwise, if I just had this one vector, right, it implies that there's an acceleration downward. right? So there has to be something, and the acceleration would be exactly gravity. But it says that it's motionless, so there must be an opposing force. So guess what that force is? That force is the tensional force, and that's T. Okay, so now, how do I do this? Well, it's a vertical problem, so I'm going to use the force is equal to ma in the y dimension. So some of the forces in the y dimension will equal the mass times the acceleration in the y. Now, so let's just set it up. What are the forces in the y direction here? Well, we have the tension that's pointing up, so it's positive. Then minus, because it's pointing down, the weight of the object, or aka mg. Great, so that should equal mass times ay. Okay, so what's the tension? We don't know it. Fine. What's the mass of the spider? They told it to us, 8.00 times, well, there it is, 10 to the minus 5. What's gravity? 9.80. What's the mass? Again, 8.00 times 10 to the minus 5. And what's the acceleration that the spider is experiencing? Zippo, right? It's motionless. Take a look at the top. It's motionless. So that's 0. So that whole thing goes away. So that's nice. So this then simply could be, right, once I do the math here, all I got to do is multiply it and then I add it across, right? So remember, that's gone. So the tension now is, oh, it almost looks like the Amazon smile. So but it might be backwards, or no. No, I don't know. My wife gets all the deliveries, not me. So we have 9.80 times 8 times 10 to the minus 5. So we have 7.84 times 10 to the negative 4th, right? And that is in newtons. So that's the tensional force. All right, not bad. Now let's take a look at letter B. So let me draw B over here and let's take a read. So now it says letter B, calculate the tension in a horizontal strand of spiderweb if the same spiderweb sits motionless in the middle of it, much like the tightrope walker in figure 4.17. The strand sags at an angle of 12 degrees below the horizontal. Compare it with the tension in the vertical strand. So here's the figure 4.17. So basically it's the same picture. Okay, the only difference is that instead of Johnny Boy standing on the rope, we have a spider here. Okay, but the picture is going to less be the same, and then the angle is different, right? Instead of 5 degrees, they told us it would be below the horizontal by 12 degrees. So what I'm going to do is I'm going to detail the free body diagram around this point. All right, so let's draw the axes. Now the center here, remember, the center here will represent the point that I circled up there. Okay, so what are the tensions? What are the forces? Well, again, the spider's on the spider web, right? So there's still the weight of the spider in the middle of the rope pointing straight down. So that hasn't changed. Okay, so that's still the weight of the spider, and that's equal to mg. Now, though, the string has changed, right, in direction. There is no exactly opposite vertical force here. Instead, the forces are now distributed to the left and to the right-hand side. So in other words, I have a tensional force pointing in that direction. That has to be pointing up, right, in the positive y direction somewhat, because, again, there's no acceleration. This thing is motionless, so something must be canceling the downward force here. Okay? And then there's another same vector on the other side. Okay? And they told us it sits 12 degrees below the horizontal. They might be saying, well, wait a minute. That looks like 12 degrees above, Andrew. So why is it there? Did you make a mistake? I didn't make a mistake because you have to think about it. Just take a look at this picture, right? If I were to draw my coordinates there, what would it look like? My coordinates would look like this. Right down the middle, and then right over here. Right? There it is. Now here, the angle of interest is this angle. Okay? And if you notice, right, if I have this line is parallel, right, remember a little geometry, right, I have two parallel lines here. What's that, alternate interior angles or whatever it was? Right, so whatever this angle is in here below the horizontal would be the same as the angle in here above the horizontal. Okay? So that should hopefully make sense. So now, what do we have to do? Well, again, we have to then take a look at the force formulas, okay? So I know, I don't really have to go through it, but let me just label this too. This is the tension, and this is tension. I don't know what they are, though, right? So let's think about this. the x components, right, of these two tensions, meaning this x component right here of the tension, let me draw it a little longer, right, and the x component of that tension will cancel. Why? Because it's the same tensional force. They're both T. We got the same angle, right? So they're the same triangle, basically. All right? So I'm not even going to bother calculating the x's. You guys should see that it's definitely going to cancel. But what I am interested in and what will add together is the y components here. Right? So for example, the y component of the triangle on the left, let me draw it a little straighter, would be that. Right? This is the y. This is the tension in the y direction. Same thing on the right-hand side. Right? That line now, that arrow, in terms of the y vector, that's the tension in the y direction of the second tension vector. Okay? So remember, we have to be consistent. All right? We can only talk about x and y frames here when we're adding things up. So since the weight, we have a pure weight in the y dimension, that has to be balanced by a pure y force in the upward direction in the y coordinate. All right, so I'm dealing with y, so some of the forces in the y direction is equal to MAY. Okay, again, there's no acceleration, so we can kind of skip this whole step, so that should just go to 0, right? So we have the sum of the forces in the y direction will equal 0. So what are the forces in the y direction? Well, so let me write this. So it's going to be tension in the y direction, right? What do we get here? Plus tension in the y dimension on the second triangle, right? Should equal, well, not equal yet, minus then, right? Let me set it up. So minus then the weight, right? Because that's the force pointing down, or mg. And that whole thing is now equal to 0, right? Because so these were the forces. These are the three forces going on. Okay? So what I want to do, though, now I can do this how I'm setting it up, but it probably would be better and easier if at this stage, remember, what we're trying to find is the tension, not the tension in the y direction, but the tension overall. So what I'm going to do is I'm going to do a little trigonometry here to find the tension. How do I do that? Well, look at this. Look at the pieces of the triangle you know. You know this angle. You're talking about the opposite side and the hypotenuse, so we're dealing with sine here, right? So watch what I'm going to do. We're going to do sine of theta is equal to opposite over hypotenuse. So the sine of 12 is equal to the opposite side, which is the tension in the y direction divided by the overall tension. Now solve this thing for t. Basically just switch the numerator and the denominator there. So t is equal to, well, no, excuse me. Let me solve it for, I have to solve it for ty. Apologize. Solve this for ty because that's the variable in my formula. So simply just cross multiply the t on up. So we get t sine of 12 is equal to ty. Now what you can do is take this and plug it on in, okay, in both places, because they're both going to be the same in terms of the triangles. So now what we have here is now we're going to have t, right, sine of 12 plus t sine of 12 is equal to, move the mg on over now, because again, I want to solve for t, is equal to mg. All right, now I can add, so now I can start adding stuff together, right? So do the sine of 12. So sine of 12, that works out to be 0.208, right? And then since there's two of them, you got to add them together. So take 0.208 and add 0.208 together. So we get 0.416. So this works out to be 0.416 T is equal to the mass of the spider, which was 8.00 times 10 to the minus 5 times gravity, which is 9.80. All right, now simply just divide out now the 0.416. Sorry guys, I'm running out of space. Divide out the 0.416. And I'm going to write the tension here, okay? So the tension here now is 8 times 10 to the minus 5 times 9.8 divided by 0.416. And we get a value now of, and I will convert this into scientific notation, so 1.88 times 10 to the, times 10 to the minus 3. And that's in newtons. Okay? So that is the tension now in that particular case. And now what they wanted us to do is compare this, right? Compare this value that we just found here with the tension in the vertical strand, meaning find their ratio. So why don't I call this T1, right, for the first part, or TA for the first part of the problem, and this is TB for part B. So if I then take TA, or let me do TB over TA because that's really what they're asking, right, that would simply be 7.84, and I'm writing it down right, but I'm not copying, okay, meaning I'm not just copying it from here appropriately over to there. All right, 1.88 times 10 to the minus 3 over 7.84 times 10 to the minus 4. So what do we get here, guys? 1.88 times 10 to the minus 3. Hold on. 1.88 times 10 to the minus 3 divided by 7.84 times 10 to the minus 4. And we get a value of about 2.4, okay? So 2.4. So that's really 2.4 over 1. In other words, the tension found in part B, because that's the numerator value, is 2.4 times larger than the tension found in part A. Number 20. Suppose a 60-kilogram gymnast climbs a rope. What is the tension in the rope if he climbs at a constant speed? All right, so first, a free body diagram. So let's draw a set of axes, okay? And this particular point in the middle, right, will represent the gymnast, okay? So what are the forces that are acting on the gymnast currently? Right? Remember, we can also think about this thing being the rope, okay? And this is just a particular point on the rope where he is. So one force is the force due to gravity, right? The weight of the gymnast himself. So how do we define that? Well, we define that as W is equal to mg. Now remember, it's going to be negative, all right, because it's pointing down. All right, so that's great. Now, if there's a force pointing down, right, then most likely climbing on the rope is experiencing well, it depends if it's in equilibrium or not, right? But the rope is probably experiencing an opposite force in the other way. All right, so we have now a vector going up. And this will represent the tension, okay, that's in the string. And that's what we're looking for. Okay, wonderful. Now, let's take that other piece of information. It says that he climbs at a constant speed. What does that mean? Well, it just means that his velocity doesn't change, right? So he's climbing up the rope here, right? So he's traveling upwards, okay? His velocity, his change in velocity, I should say, his change in velocity is 0, okay? But in terms of forces and whatnot, what's the important variable? Is it velocity or is it acceleration? It's acceleration, right? So although he is traveling with a certain velocity, his change in velocity is 0, and therefore, remember, the acceleration is 0. Okay, why? Because acceleration is defined as the change in velocity over the change in time. So 0 in the numerator gives you a 0 value overall. Okay, so now we have enough information we need in order to figure this out. Okay, so this is a y problem. Remember, all y problems are, assuming the object has mass, right? All problems in the y direction, you always want to consider the weight of the object. Okay, so some of the forces in the y direction should equal the mass times the acceleration in that y direction. So what are the forces in the y? Well, we detailed it in the picture, right? There's a tensional force pointing up, so it's positive. And then there's a weight, or mg, right? Because they're the same thing pointing down. So subtract mg here. And that should equal then the mass times the acceleration in the y. So let's start plugging some values in, right? So t, I don't know what it is. The mass of this gymnast is 60.0, right? Gravity is 9.80. And then over here, the mass is 60 again. But I mean, I don't even have to write that because what's the acceleration? It's 0, right? So that whole term goes to 0, okay? And then in order to solve for t, right, I would just be adding this term on over to that side, right? So t will equal, once I add it over, it becomes positive, and it's 60 times 9.8. So 588. So 588 newtons. That would be the tension. Over and done with. So part A is finished. Now part B. Okay, so let's go back and read part B. So it says, what is the tension in the rope if he accelerates upward at a rate of 1.5 meters per second squared. I sometimes feel if I pause a little bit on this question, it emphasizes a certain, thing there, and it'll click a little better, but it probably doesn't. So anyway, don't mind me. So here we have our free body diagram. Now, what's going on with this gymnast? Well, again, he's climbing up a rope, so he still has a weight. So that weight doesn't change, right? Your weight doesn't change if you're stationary or climbing up a rope. Otherwise, when I want to feel good about myself, I would climb up a rope and the scale would be less, right? But if you are accelerating upward, obviously there's less force pointing down on the scale, so I guess you would be a little less. But in terms of then, it's only relative, though. If the scale's moving with you, it's not at the same acceleration, it's not going to change. Anyway, okay. I'm sorry, guys. I'm losing it today. Okay, so the weight is equal to mg. Fair enough. Okay, same thing as before. And the rope still has a tensional force, right, pointing upward. That hasn't changed yet, or that hasn't changed at all. Okay, there's still an opposite force opposing the weight. The only difference here now is that there is an acceleration. Okay, so there is something going upwards or positive. All right, and that acceleration in that y direction, and I'm just going to write the little positive sign there just to make sure we don't forget that, is 1.50 meters per second squared. So guess what? We got enough that we need, right? We know what we need. I just got to label that T. That's what we're looking for. And now how do I relate these things together? Again, it's the same thing. Let's use the formula, right? Some of the forces are Newton's second law here. Some of the forces in the y direction will equal the mass times the acceleration in that y direction. So what are the forces? There's the tensional force, and then there's a negative mg. That will equal MAY. Let's start plugging some stuff in. So the tension minus the mass we said was 60. Gravity is 9.80. The mass, again, hasn't changed. It's still 60. And then the acceleration this time is not to 0, is a positive 1.50. Okay, so how do we solve? Simply just take this value, add it on over to this whole value. All right? So I'm just going to do that all in one step here. Save a little time. So we got 60 times 1.5 plus 60 times 9.8. 678. So we get 678 newtons. Okay? And that is now the tension in the rope when the gymnast accelerates upward. And that should make sense, right? I mean, if you think about it, it might make sense in one sense, but it might not in another. You might say, well, I'm accelerating up, so why is the force getting greater going up? Well, because how are you accelerating upwards? You're pulling down on the rope even harder, correct? If you're accelerating up, you got to pull down even harder on that rope. And therefore, there should be more tension in that rope. All right, that would be the proper way to think about it. Number 21. Show that, as stated in the text, a force F perpendicular exerted on a flexible medium at its center and perpendicular to its length, such as in the tightrope figure 4.17 gives rise to a tension of magnitude of this thing. Okay. If you understood that, you're better than me. So basically what they're trying to do, all right, is what we're trying to solve for is we're trying to figure out an equation in my free body diagram here that represents the tension. That's it. Okay? That's basically all that they're asking us to do. So my job here will be, so here's my free body diagram, right? I have an object, like in my figure over here on the top right. I have an object here, the mass pointing straight down. That's the perpendicular force that they're talking about. All right? Perpendicular to what? Perpendicular to the basically the axis of the tightrope. Okay, so all we have to do here is let's simply try to break this apart and let's see if we can solve what's going on. All right, so this is a y dimensional problem. Okay, so I'm going to use the sum of the forces in the y direction is equal to the mass multiplied by the acceleration in that y dimension. So now what are the forces all in the y direction? And by the way, why am I not caring about the x dimension here? Well, the reason why is because if you look at, let's say, this component over here, okay, the x component here would be some value, right, pointing to the left. And then the x component of the tension on the right-hand side, right, would be also some value pointing to the right. But they would be the same values, right? Because the t's are the same and the angles are the same. So therefore, the x value should also be the same. But they're pointing in opposite directions, so they cancel. Okay? That is not the case in the y direction here. Right? In the y direction, let me draw one of them in. In the y direction, we have one pointing up, right? I'll call that tension in the y. And then on the other one, we got the same thing, right? Tension in the y. But notice they're both pointing in the same direction. That's a v, that's not a t. Tension in the y. All right? So they're both pointing in the same direction. Therefore, they add to one another. They don't cancel. All right? So this is what we now need to consider when we're talking about the the y direction. We're talking about the forces purely in the y direction. So what would they be? Again, we have one tension in the y direction coming from one of the triangles. Another tension, right, coming from the other triangle in the y direction. And then a weight, okay, which is negative. So minus w is going to equal the mass times the acceleration in the y direction. Okay, so let's just manipulate two things here. So tension in the y plus tension in the y. Now this is minus w, but in terms of their formula, that w that they're talking about is really the force perpendicular, okay? Is the perpendicular force, right? Notice in the picture again, that's the axis of the tightrope, and his weight is perpendicular to that axis. Okay, so what I'm going to do here, instead of writing w, just so we can match it up, I'm just going to write F perpendicular. All right? Is equal to then MAY, but is there any acceleration in the problem? No. Right? So this becomes a big old fat 0. All right, great. So why don't we do this now? So let's combine the two terms. Okay, so we got 2ty, right? And then add over the force parallel to the right-hand side. So that should then equal F perpendicular. All right, so now we're almost there, but I don't want to find a formula that involves the tension in the y dimension fully. I want to get a formula that involves the tension overall. So how do I do that? How do I find an equation that relates the hypotenuse of the triangle? Right? Well, if I want to incorporate the hypotenuse and this angle, and I know the side opposite of that, sounds like I'm going to use sine. So let's do that. So sine of theta is equal to the opposite over the hypotenuse. So sine of the angle is equal to the opposite side, which was the tension in the y dimension, divided by the hypotenuse, which is strictly the tension overall, the resultant tension. Now solve this thing for tension in the y direction. So just cross multiply the tension on over, so we get t times the sine of theta is equal to tension in the y dimension. Why did I do that? Well, because like I said, I want to substitute this on into my equation for tension in the y direction. So I can just now simply plug it in. So now I get 2 times tension sine times the sine of theta is equal to F perpendicular. Okay, great. Now I take a look at the top, guys. Right here, I want to solve it now for just the tension. So that's my job. Okay? So notice the 2 and the sine of theta are multiplied to the tension, so therefore I can divide both of them out. Right? So I divide them both out of this, both sides. They cancel here on the left, so leaving me with t is equal to the force, the perpendicular force, which was just the weight of the object, divided by 2 sine of theta. And it is a thing of beauty. Number 22. Consider the baby being weighed in figure 4.33. Letter A. What is the mass of the child and basket if a scale reading of 55 newtons is observed? All right. So for letter A, they're talking about a scale reading 55 newtons. Now that is a force, right? So the force pointing down for the baby is going and the basket, right, is 55 newtons. Okay? And in other words, right, we could think of this as either a W is equal to mg problem or I mean, it's really the same thing, though, as some of the force in the y direction, right, is equal to ma, because the acceleration in the y direction, as far as weight is concerned, is gravity. Right, so it really doesn't matter how we view this. I could also call it W, 55 newtons, okay, because they're kind of asking for a weight here, all right, but they're the same thing. So, in other words, just considering the formula of W is equal to mg, and if the scale is showing a weight of 55 newtons, right, that should be equal to the mass of the child in the basket multiplied by gravity, 9.80. So just divide out the 9.80, 9.80, and the mass now should be fairly straightforward. So 55 divided by 9.8, and it comes out to 5.6. So we got 5.6 kilograms. Okay, so now letter B, let's take a look. What is the tension, T1, in the cord attaching the baby to the scale? All right, so in the picture, here's the scale, here's the baby. So we're looking for the tension in the middle, right? So basically, this is the system of the problem, the baby and the basket. Okay, so if I had to draw now for letter B a free body diagram, it would look something like this, where the baby's weight is pointing straight down. That's the weight as equal to mg, which they told us before was 55 newtons. And then the tension is pointing straight up, right? So we're going to have a tension vector pointing now straight up. So that's T. And that's the question. All right. So now this is a y dimension problem. So let's use our Newton's second law in the y direction. It's equal to may. Is there any acceleration in the problem? No, the baby's stationary, right? So this whole side goes to 0. So that means the sum of the forces in the y direction should equal 0. Now, what are the forces in the y direction? Well, it looks like we have a positive tension and a negative weight. So I could say T minus W is equal to 0. In other words, T is equal to W, and T is equal to then 55. So that's the tension. Not too bad. Letter now C. So what is the tension T2 in the cord attaching the scale to the ceiling if the scale has a mass of 0.500 kilograms? All right, so now the frame of the problem changes, and now we're looking at this tension up here, okay? So in order to understand now the frame of the problem, it's this whole thing that we're considering that's pulling down on this part of the rope. All right, so what that means now, when I draw my free body diagram for letter C, I'm going to have now two weights pointing straight down. Okay, one weight will be the baby's weight that we have detailed in the prior problems. So that would be W is equal to 55 newtons. And now we have another weight attributable to the scale itself here, which they told us has a mass of 0.5 kilograms. Right, so that's fine to find the force of that, right? Because remember that the weight of the scale here, I'll call it little s, would be equal to mg. What's the mass? Well, the mass is 0.5 kilograms, right? And g is gravity. So I could say W, the weight of the spring, should equal 0.500 multiplied by 9.80. So the weight of the spring there is going to be, so 0.5 times 9.8, so it's just half, right? Okay, so we get a value of 4.9. So this works out to be 4.9 newtons. That is the value of the weight of the scale. Okay, so now, what's the force that's opposing those weights? The tension, right? The tension up here. Okay, so let's detail that tension in our free body diagram. So here, pointing straight up, that's now the tension. Okay, and now again, we're going to use the y formula. So the sum of the forces in the y direction will equal mass times the acceleration in the y direction. But remember, there's no acceleration. This thing is stationary, or it's not moving. So therefore, this whole side goes to 0. So now let's break up. So now we can write the sum of the forces in the y direction should equal 0. Well, what are all the forces in the y direction? We have a positive tension, a negative weight of the scale, and a negative weight of the baby. and that should all equal 0. So in other words, the tension should equal the weight of the scale plus the weight of the baby. All right, so now all we got to do is just plug some stuff in. So the weight of the scale we found to be 4.9 newtons, and the weight of the baby was 55. So just adding those all together now, we get a tension of basically 59.9, so let's just call it 60 newtons. Okay? And that's letter C. Now let's take a look at letter D. So we have, it says, draw a sketch of the situation indicating the system of interest. Okay, so we did that. So I like to do that basically for every problem anyway. Okay, it's good habits to get into. It'll make it easier when the problems get a little more complex. Number 23. A 5 times 10 to the 5 kilogram rocket is accelerating straight up. Its engines produce 1.25 times 10 to the 7 newtons of thrust, and air resistance is 4.5 times 10 to the 6 newtons. What is the rocket's acceleration? Explicitly show how you follow steps. Okay. So, as in all these problems, first thing to do is to try to create a free body diagram that depicts all of the forces in the problem. All right. So first thing, a couple things are fairly straightforward, right? They tell us that the engines produce 1.25 times 10 to the 7 newtons of thrust. So if you're thinking about, right, a little spaceship here, right, that looks like the Voyager 7. If you're thinking about what direction the thrust points in, it would point up, right, because it has to apply a force up or in the positive y direction to get it off of the Earth. So I'm going to draw one of those vectors right here. So this is the thrust. I'll call it T. Sometimes T represents tension, but in this problem it'll be thrust. So 1.250 times 10 to the 7 newtons. Great. Now it also tells us that we have this air resistance, right? We got air resistance of 4.5 times 10 to the 6th. What direction does that point? If you're unsure, think about, does it impede the motion or does it enhance the motion? It's going to impede the motion, correct? Air resistance slows you down. It's a force that opposes motion. So therefore, if I have motion going up, that air resistance then, if it opposes it, must be going down. So that's great. So let's call this the force of air resistance, okay? That's going to be 4.50 times 10 to the 6 newtons. Now, it almost seems like we have everything we need, right? So we can just go about and calculate it. But there's one thing that's missing, okay? And this is what you really want to remember. When you're doing accelerations in the y direction and forces in the y direction, please do not forget the weight of the object itself. That is another force. So if you forget about that, you're going to be wrong. All right? So in addition, because you think of it this way, right? The thrust that the engines produce from the rocket not only have to overcome any air resistance that it experiences, it also has to overcome its own weight, right? So by me not putting the weight in here, it would definitely be incorrect. So I have to put another vector pointing down, because that's the way, right, gravity pulls. And this vector here I'll call the weight, all right? That's W is equal to mg. So we need to know the mass of the rocket. Well, fortunately, they gave that to us, right? So I'm just going to do the calculation over here. Weight is equal to 5.00 times 10 to the 5 multiplied by 9.80. So we got weight is equal to, so let's do 5 times 10 to the 5 times 9.8. So we get 4.9. 4.9 times 10 to the, should be 6. Let me just double check. So we got, yes, and I made a calculation mistake here, but it should be. Let me just double check. Sorry, guys. Yes, to the 6. Great. And that is in newtons again. All right. So that is the value over here. So we can write W is 4.9 times 10 to the 6. Okay. Now this picture is complete. All right. So now we have to select our formula. So we're talking about y direction. So let's choose the sum of the forces in the y. All right. So the sum of the forces in the y direction is equal to the mass times the acceleration in the y. So what are the forces in the problem? Positive tension, negative force of air resistance, and negative weight. right? Because these two are pointing down, so they're negative, is equal to the mass of the object that's being accelerated times that acceleration itself. So the T is thrust, right? I might have said tension before. I meant to say thrust if I did. I don't remember. But in any case, T will represent thrust in this problem. So 1.250 times 10 to the 7 minus 4.50 times 10 to the 6 minus 4.9 times 10 to the 6 equals, oh boy, 5.00 times 10 to the 5, and then finally times a sub y. So we got one equation with one unknown. Let's solve it. Okay, so 1.25 times 10 to the 7 minus 4.5 times 10 to the 6 minus 4.9 times 10 to the 6. And we get a value of 3.1 times 10 to the, looks like 6, right? Let me just make sure. 3, yes, great. And that will now equal 5.00 times 10 to the 5 times the acceleration. So divide out now the 5.00 times 10 to the 5 from both sides. Divide by 5.000 times 10 to the 5. So we get the acceleration in the y direction. So divide this by 5 times 10 to the 5. So 6.2. So we get an acceleration of 6.2 meters per second squared. That would be the acceleration of the spaceship. Okay? If you forgot to include the weight of the rocket, it would have been significantly higher. Number 24. The wheels of a mid-sized car exert a force of 2,100 newtons backward on the road to accelerate the car forward. If the force of friction, including air resistance, is 250 newtons and the acceleration of the car is 1.80 meters per second squared, what is the mass of the car plus its occupants? All right, so free body diagram. So let's draw the axes. Okay. Now it says that now the car is exerting a force right backward on the road. Okay, so what you might think is to say, okay, let me write the force in like this in my problem. Okay, now it really won't make too much of a difference if you do that. By the way, what I'm assuming is that we have a vehicle and it's accelerating this direction. So its wheels are pushing back on the road to accelerate itself forward. So if you drew this, in this direction here, it is wrong if you're talking about the car moving to the right side. Why? Well, because the force that's applied to this vehicle, if it is accelerating to the right-hand side, must also be applied to the right-hand side. So you might say, well, wait a minute, but they told me it's backward in the problem. Well, you have to remember that the car is pushing backward on the road, but the road is pushing forward on the car. So it is this force. It's the force that the road is exerting on the car. That's the important force, because we want to talk about what are the forces applied to the car. And the car is applying a force to the road. That's fine, and that's backwards. But that's not the force we need to describe this motion. We need the force that the road is applying to the car. And in Newton's third law, that force is equal but opposite. All right? It's a minor thing. You'll probably wind up getting the question right anyway, assuming that then you place the frictional force in the opposite direction. But I just want to be clear about that. So this is the 2,100 newtons. Then it says that there is an air resistance, right? A friction, whatever, blah, 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 of 250 newtons. So that opposes motion. Remember, friction always opposes the motion. So this is going to be 250 newtons. Okay, wonderful. And it says that the car is accelerating 1.80 meters per second. Now, given my diagram, there's a specific way that the car will accelerate and will be accelerating to the right, right? Because the net force will point in the same direction as that acceleration. And on this problem, it's fairly easy, but when the problems become more complex, it's important to keep these ideas in mind. Now, how can I put this all together? Well, I'm considering this in the x direction, so let's use now some of the forces in the x direction. So some of the forces in the x direction should equal the mass, the combined mass of everything that is, multiplied by the acceleration in that x direction. So what are the forces in the x direction for the problem? Well, we have the 2100 Newton force, right, that the road is applying to the car. And then we have the wind resistance or air resistance that the air is applying to the car, right? And that value is negative, right? Because take a look at the picture. This value pointing in the positive x, this value is pointing in the negative x. So that should be minus 250. And that should equal the total mass of the car and all of its occupants, because that's the thing that is accelerating, multiplied by its rate of acceleration of 1.80. So now this is fairly straightforward, right? To solve this, just divide out the 1.80, 1.80. So the mass now of the vehicle is going to be 2100 minus 250 divided by 1.8. And it comes out to 1,000. We'll do 1,030 for 3 sig figs, okay? And that's in kilograms, because that's what the mass is. In kilograms when you use F equals ma. 25. Calculate the force of a 70 kilogram high jumper must exert on the ground to produce an upward acceleration 4 times the acceleration due to gravity. All right, so let's detail it with a free body diagram. So we have a jumper, correct? And so let's just say this dot in the middle represents the jumper. Now, since we're talking about jumping off the ground, right, this is a problem in the y direction, and therefore you must always talk about the weight, the force due to gravity on the object itself when you're describing these problems. So let me do that first. Okay, so this jumper has a certain weight, right? The weight of that jumper is going to be equal to the mass multiplied by gravity. So let's just simply calculate that first. So the mass is 70, right? Kilograms, gravity is 9.80. So the weight of this jumper is simply going to be 70 times 9.8. So 686. So we have 686 newtons. Okay. Now, that's the weight of gravity pulling down, or the force of gravity pulling down on the jumper. Okay, but now it says that the jumper wants to accelerate upwards, right? An upward acceleration. So therefore, we're going to have an A in the positive y direction, right? That's going to be some number. Now remember that if I have an acceleration in the positive y direction, I must have a total net force also pointing up. Okay, so right now all I have is a force pointing down, and it's this value. So therefore, the force that's pointing up, we should anticipate, should be bigger, right, than this value. Okay, so just keep that in mind. Now, this force, right, so let me see, 4 times the acceleration due to gravity. Okay, so the force here, they want us to calculate. Okay, so that's the question mark. So just to go back, actually, when I said I don't know the acceleration, I do know it, I just have to read a little closer. Okay, it says the upward acceleration 4 times the acceleration due to gravity. So I actually do know this acceleration, right? The acceleration is going to be 4 times gravity. Simple enough. So the acceleration that this jumper wants to experience is going to be 4 times 9.8. In other words, 39.2 meters per second squared. So I know the acceleration. Okay? So now, what can I do? I can now set this problem up, right? These are all the forces that are acting on this jumper here. It's just the weight of the jumper, okay, and then the force that the jumper is going to apply to the ground so that he propels himself upward. Okay, so meaning the force that the ground is going to impart on him is in the upward direction. Okay, we only care about forces imparted to the jumper. The jumper exerts a force down on the ground, but then the ground exerts that equal but opposite force up on the jumper. So I'm only concerned about the force on the jumper, not on the ground. That's why it's pointing up. So, not to belabor the point, we're going to be using some of the forces in the y direction, okay, is equal to the mass of the object that's accelerating multiplied by the acceleration in the y direction. So what are the forces in the y direction? We got this force pointing up and the weight pointing down. And that shall equal the mass of the object, which was 70 kilograms, multiplied by the acceleration, which is 39.2, right? And I do know the weight, right? I calculated that before, so let me just actually simply plug that in here. Okay, so that's just going to be minus 686. Okay, so how do I solve it? Simply just take this 686 and add it to the product of those two numbers. All right, so the force is going to be 70 times 39.2 plus 686. Right, and this should make sense. The force is going to be 3,430 newtons. And if you look, I had to add the two forces together, right? I had to add the force to accelerate a 70 kilogram mass by this acceleration. And then not only did the object have to accelerate itself in that way, it also had to overcome the acceleration due to gravity. So that's why I had to add it then. The math is telling me to add it, but it should make sense. Number 26. When landing after a spectacular somersault, a 40-kilogram gymnast decelerates by pushing straight down on the mat. Calculate the force she must exert if her deceleration is 7 times the acceleration due to gravity. Explicitly show. Okay. So first let's detail a free body diagram. So she is falling, right? That's pretty apparent. So she's coming down from a somersault. Okay, so she has a certain mass, correct? And that mass being pulled by the acceleration due to gravity means that there's a force due to gravity, right? Always remember, in any Y problems, you always have to include the weight of the object. So the weight of the object is pointing down, and the object here is a gymnast. So here we have the weight is equal to his or her mass, and it's a her in the problem, so weight is equal to mg. Okay, so that's fine. Now, let's just calculate it now, okay? So her mass was 40.0 kilograms and gravity is 9.80. Let's just get it out of the way. So we got 40 times 9.8. So it's 392. Okay, so 392 newtons gravity is pulling down on her. Okay, so now she's falling, right? Here's the ground, and she's falling, and then she's going to push up, basically off the ground, right? Or she's pushing, I guess, straight. I mean, it says, hold on. So it says she's decelerating by pushing straight down on the mat. Yeah, she's pushing down on the mat. That is correct. But then the mat is pushing up, right, against her. Remember, this is all Newton's third law, okay? So when I think about this picture, okay, first let me detail one thing. It also says she must decelerate, right, at 7 times the acceleration due to gravity. Now let me ask you a question. What direction is that deceleration, or AKA what direction is that acceleration? Well, if she's coming down and she's slowing down, that must mean there's a force being applied upwards, correct? How else would she be slowing down? So what that means is that if there is a force pointing upwards, a net force pointing upwards, right? That means there must also be a net acceleration pointing upwards. And the acceleration, as they mentioned to us, is 7 times that of gravity. So just take 7 and multiply by 9.80. So the acceleration in the y direction in this problem is upwards, and it is 7 times 9.8. So 68.6. So we need 68.6 meters per second squared. Okay, so now here's the thing. If there is a net acceleration upward, remember I knew that because she was decelerating, but she was decelerating coming down. So if she's slowing down on the way down, there must be an acceleration upwards. Okay, so now, knowing that there is an acceleration upwards, I know for a fact now that there should be some force pointing up as well. And not only do I know that, but I know the net force overall, when I sum these two things, it should be pointing up. Okay, so that means that the force pointing up better be greater than the force pointing down. Okay, so this now arrow will represent the force of the mat, let's call it. Okay, force sub m. All right, but you might say, well, wait a minute, she pushes down on the mat, so why is the arrow up? This is always so confusing, and it is. It is, but you have to remember, she is pushing down on the mat. Okay, but what we need to describe in this free body diagram are the forces exerted on her, not by her. That's really important. Okay, she is exerting a force on the mat. That is a force by her, right? But it's not on her. So meaning she exerts a force down on the mat, and then that mat exerts an equal but opposite force up on her. Okay? So hopefully that clears it up a little bit. You got to really think about, if I'm trying to detail the acceleration of the gymnast, I'm thinking about the forces on the gymnast. Okay? Maybe I should write that down. Yeah, why not? So maybe I'll try to write that down over here. So let's see. If you're trying to find the acceleration, if you know the acceleration, right, of the gymnast, okay, you must consider forces acting on the gymnast, not by the gymnast. Okay? Important concept. All right. Let's keep going. So now this is a y-dimensional problem. So some of the forces in the y dimension, all right, will equal the mass times the acceleration in that y dimension. So what are the forces in the problem? Well, we detailed that, right? The force that the mat exerts on, right, the gymnast, and the force of gravity that the gravity exerts on the gymnast, right, which would be the weight. And that should equal her mass multiplied by the acceleration she experiences, which we found out already what that is. So I'll just write AY. Okay, so let's just plug it in. So F sub m, right, minus now 392 will equal the mass of the gymnast of 40.0 kilograms multiplied by her acceleration of 68.6. All just add now the 392 to the other side. And remember, that should make sense. Not only does she have to, or does the mat have to overcome the force she is exerting, but it also has to overcome the weight of gravity. All right, so here is F sub m. So it's going to equal now 40 times 68.6 plus 392. And it's 3,100, and we'll call it 40 newtons. Now, this is the force that the mat is exerting on the gymnast. However, though, we have to think about this. Remember, the question is asking us calculate the force she must exert if she wants her deceleration to be 7 times the acceleration due to gravity. All right. So when we consider this now, we have to think about, well, the force of the mat, right? The force that the mat is applying to the gymnast is going to overcome both the force due to gravity and the force that the gymnast is imparting on the mat. Okay? So, in other words, we have, I could come up with an equation like this, that the force of the mat must equal, okay, the force due to the weight of the gymnast plus then the force that the gymnast is exerting on the mat. Okay? So in order to then calculate this, which is the force that the gymnast is exerting, we have to simply plug our values in. So we have 3,140, right, is equal to the weight of 392 plus then the force that the gymnast exerts. So subtract the 392 from both sides, 392 from both sides, and we get that the force that the gymnast exerts on the mat, that will be equal to 3,140 minus 392. And we get 2748, and we're going to round to 2750, okay? So 2,750 50 newtons, okay? Just remember, and again, consider that the mat has to apply a force not only to overcome the force that the gymnast is pushing down on the mat, but it also has to overcome the force due to gravity that is being applied to the gymnast herself. Okay, so there's really two components locked up in this force that the mat is exerting. Number 27. A freight train consists of two 8 times 10 to the 4 kilogram engines and 45 cars with average masses of 5.5 times 10 to the 4 kilograms. Letter A. What force must each engine exert backward on the track to accelerate the train at a rate of 5 times 10 to the minus 2 meters per second if the force of friction is 7.5 times 10 to the 5 newtons, assuming the engines exert identical forces? Okay, so we have to find the force each engine must exert backwards. All right, so let's try to draw a free body diagram of this. So let's create our axes. All right, and we're going to basically, what's the right word here? We're going to basically aggregate, all right, all of the cars and the engines into a single point. All right. So I know the train, consists of a whole bunch of cars, et cetera, et cetera, et cetera. But we're going to sum everything up so that we make a single point. Went too far there. We make a single point out of the whole problem. Okay. So this point will represent the entirety of the train. All right. And now we have to describe what forces are acting on this entire train. Well, it says that the force of friction on the train is 7.5 times 10 to the 5 newtons. And I'm going to assume that the train is moving in the right-hand direction. Therefore, the force of friction opposes that motion, and it will be pointing in the left-hand direction. So this will be the force of friction, and that's going to be 7.5 times 10 to the 5, right, newtons. What else does it tell us? It also tells us that there is an acceleration, right, that the train is accelerating, and that acceleration is 5 times 10 to the minus 2. Okay, that's in the x direction. So 5.00 times 10 to the minus 2 meters per second squared. And what else do they tell us? And they give us a whole bunch of masses, right? So we can find the mass now of this whole train. So what is it? So we got two 8 times 10 to the 4 kilogram engines. Okay, so the mass of the engines is going to be 2 times 8.00 times 10 to the 4, right? 10 to the 4. So let's just do that first. Mass of the engines. So we get, this is straightforward. So this is 1.6 times 10 to the 5, right? That's in kilograms. I'm just leaving out the units. And then we have now the mass of all the cars, right? So the mass of all the cars, it told us that we have 45 of them. We have 45 cars, and they each weigh 5.50 times 10 to the 4. Okay, kilograms that is. So the mass of the cars now will equal 45 times 5.5, second e to the 4. So we get a total mass here of the car is going to be 2.48 times 10 to the 6. Okay, these are both in kilograms. So now to find the total mass, right, of the train, we would just add these two together, right? So let's add 1.6 times 10 to the 5 to that value. And we get a value of now 2.6, I'll call it 4. 2.64 times 10 to the 6, and that's kilograms. Okay, that's the total mass of the train. All right, so that is equal to m of the train. All right, so that sounds great. So now it sounds like we have enough information to basically solve, right? So since there is an acceleration here, right, in the right-hand direction, there must be a net force then pointing to the right as well. What that means is that there must be a force that's pulling the train, meaning the engines, right, that exceeds the force of friction by some amount, okay? And I don't know what that is yet. That's the point of the calculation. So let's do that now. So this is all in the x direction, so I'm going to choose the x formula. So here I'm going to do it over here on the bottom left. So the sum of the forces in the x direction should equal the mass of the object being accelerated multiplied by the acceleration in the x direction. So the sum of the forces in the x direction. So it looks like we have the force, I'll call it applied, so FA, all right, the applied force, minus then the force of friction, because it's pointing in the left-hand direction, and that should equal, again, the mass times the acceleration. So now let's start plugging in some numbers. All right, or, what we could do is I can already solve this algebraically and then just plug them in. It doesn't really matter. So the force applied minus 7.5 times 10 to the 5 should equal the mass, the total mass that is. So we have 2.64 times 10 to the 6 kilograms, and the acceleration of the train is 5.00 times 10 to the minus 2 meters per second squared. So just add this term on over, right? And then add it to the product of these, and let's see what we get. All right, let me save some space. So we get the force applied here to the train is going to be 2.64 times 10 to the 6th times 5 times 10 to the minus 2. Great, and then plus 7.5 times 10 to the 5. So the force applied is going to be 8.82, so 8.82 times 10 to the 5 times 10 to the 5 newtons. Now, don't stop there, right? That's not necessarily the answer, because look, it says what force, go back to the problem, what force must each engine exert? Right, backward. So whatever the force that the engine is exerting backward is equal to the force that the engines are pulling the train forward with, right? So, or I should say that the track is pushing the train forward with. So all I need to do now is basically take my force applied and just divide it by 2, right? To find then the force applied by each engine, okay? So that should just be about, right, 4.41. So that's 4.41 times 10 to the 5 newtons. So that would be the answer for letter, was that even a letter? Yeah, letter A. Okay, great. Now let's skip on over to letter B. All right, so letter B. What is the force, oops, let me get the highlighter. What is the force in the coupling between the 37th and 38th cars? This is the force each exerts on the other. Assuming all cars have the same mass, okay, they have the same mass, and that friction is evenly distributed among all the cars and engines. Okay, so just like how we aggregated the entire train to a single point in the prior part, I'm going to try to do some aggregation here as well, okay? And I think this, so we basically have 2 parts to the problem, although I'm only going to look at one part and I should be able to answer the question. So the way I want to look at it is this way. There's basically 2 units to this. I'm going to call this car, how many cars were there? 45. So this is car 38 through 45. Okay? And that whole group of cars is attached to car number 1 through 37 and the 2 engines. Okay, so there's basically 2 parts to this problem, okay? But I'm only going to analyze one of them and I should be okay to answer the question. So basically the engines on the front of the train right here are exerting some force forward, right? Okay, so that's fine. And what's happening now with this part of the problem, meaning that aggregate amount of trains? What's going on there? Let's try to detail a free body diagram that describes what's going on in this group of, I think it's actually 8 cars. It looks like it's 7, but it's 8. Okay, so how are we gonna, let's do that. Okay, so how do I know that there's 8? We'll simply count 38, that's 1, 39, 2, 40 is 3, etc. And you'll realize when you get to 45, that's 8 in total. So just be careful about that. It's not 7, so don't do a simple subtraction there. Okay, because the subtraction value is 7, but the actual number of cars there are 8. So what I need to do is I need to find the total mass of these cars. All right, so how do we find that? So I'll on the right-hand side, I'm going to do 38 through 45. Right there's 8 cars. Okay, now given that there's 8 cars, okay, and each car has a mass, that's an 8 by the way, each car has a mass of 5.5 times 10 to the 4 kilograms, I can find the total mass of all of those cars, right? So this would be just simply be 8 times 5.5 times 10 to the 4. So we get 4.4 times 10 to the, looks like 5, right? Times 10 to the 5, and that's in kilograms. Okay, so that's the total mass of all 8 of those cars. Okay, fine. So this whole group has a mass of 4.4 times 10 to the 5. Okay. Now, what forces are acting on this car? Well, remember, each car is experiencing a frictional force, and take a look at the problem. It says friction is evenly distributed among all cars and engines. All right? So, what's the total friction? The total friction is 7.5 times 10 to the 5. Okay? So let's now calculate the frictional force here for those 8 cars. So the frictional force will be the total frictional force, 7.5 times 10 to the 5, multiplied now by 8 cars, because there's 8 of them, but divided by the total number of cars there are, 47, right? Because remember, the frictional force here is evenly distributed over the 45 cars plus the 2 engines. Therefore, it's evenly distributed over 47 items. And of those 47 items, I only want to find the friction that's aggregated in 8. All right, so the math should work out here. So I get then the frictional force of those cars should be simply 7.5 times 10 to the 5 times 8 divided by 47. So this value works out to be something like 1.28 times 10 to the 5 times 10 to the 5 newtons. Now, where is this force in the picture? Well, this force is, remember, if I'm looking at it this way, I'm trying to keep it consistent. The train is being pulled to the right, therefore the frictional force opposes that motion, right? So it's pointing to the left. Okay, so remember, this dot right here represents the group of eight cars at the end. Okay, so the frictional force here is equal to 1.28 times 10 to the 5 newtons. Okay, wonderful. Now, that's the frictional force here, okay? Now, if I think about this, all I need to now really add to this problem is this thing I'll call it like tension or something. All right, I'll just call it T. Because, remember, this group now of cars are pulling, okay, the group of 8 cars in the back. All right, so the force or the tension in this coupling, okay, can be simply found by finding the total frictional force of all the 8 cars, and then solving for the tension or the force of pull in between these groups of cars, meaning in between the last 8 and the first 37 or 39, right, including the 2 engines. Okay, so now this is an x problem, meaning it's in the x direction, so I'm going to do the sum of the forces in the x direction should equal the mass of those items multiplied by the acceleration in that x direction. Remember, the acceleration hasn't changed, right? The acceleration of these cars is still the same as it was before, of 5.00 times 10 to the minus 2. So the sum of the forces in the x direction, what do I got? Well, I got a positive t because it's pointing to the right, minus then the total frictional force of 1.28 times 10 to the 5, right? That should then equal the total mass of those 8 cars, which we found up here, which was 4.4 times 10 to the 5. So I got 4.4 times 10 to the 5. I'm running out of space, so I'm just going to write the times the acceleration on the bottom here of 5.00 times 10 to the negative 2. Okay? Now to solve this, multiply these two together, and then add this value on over to the left-hand side. All right, and when we do that, we're going to get, let's see, 4.4 times 10 to the 5 times 10 to the minus 2 plus 1.28 times 10 to the 5. And we get a value of exactly 1.50 if you want. I think maybe we can use 3 sig figs. 1.50 times 10 to the 5, and that is in newtons. Number 28. Commercial airplanes are sometimes pushed out of the passenger loading area by a tractor. Letter A. An 1,800 kilogram tractor exerts a force of 1.75 times 10 to the 4 newtons backward on the pavement, and the system experiences forces resisting motion that total 2,400 newtons. If the acceleration is 0.150 meters per second squared, what is the mass of the airplane? All right, so first let's try to create a simple free body diagram here. Now, it's talking about the entire system here, right? Being the system experiences forces. All right, so meaning the system being the tractor and the airplane. Okay, so let's assume that this system is accelerating to the right. Okay, you could do it to the left too. Doesn't matter, but you're make sure you use then a negative acceleration. All right. So a is equal to 0.150 meters per second squared. We have if our acceleration's in the right-hand direction, then the frictional forces, right, have to be pointing in the opposite direction of the motion. So this is where the 2400 Newton force will be pointing. Now it also says that the only applied force in this problem is from the tractor, right, where it is applying a 1.75 times 10 to the 4 Newton force backward on the pavement. Now remember, what you may think is well, let me draw the arrow back, right, because it's exerting a force backward on the pavement. Yes, it is, but that's not how you're going to draw it in your free body diagram. Because what's important are the forces acting on the system of interest, not by the system of interest. What do I mean by that? The tractor, right, produces this force on the pavement. And then, by Newton's third law, that pavement produces a force equal but opposite on the tractor. So that's the one we're interested in, so that's why I'm going to draw that vector to the right. Okay? So this value is 1.75 times 10 to the fourth. All right, great. And looks like we got everything we need in order to start solving this. So let's take a look. It's in the x-axis, so we're going to use the sum of the forces in the x direction is equal to the mass of the system, all right, multiplied by the acceleration in that x direction. So what are the forces in the x direction? Well, simple. We detailed them already. So it's 1.5 times 10 to the fourth minus then 2400 will equal the mass of the system. What's the system? Well, the system consists of the tractor and the airplane. So what's the mass of the tractor? It's at 1800. What's the mass of the airplane? I don't know. So that's fine. That's what we're going to solve for. That's our variable. And then times the acceleration. So the whole system, it said, experiences a 0.150 acceleration. So let's clean it up. So 0.175 times 10 to the fourth minus 2400. We get a value of 15,100 will equal 1800 plus MA, all multiplied by 0.150. Divide out now that, right? Divide out that 0.150. So now we get, divide 0.15. I'm going to use scientific for this, 1.01, it looks like, times 10 to the, let's count, 3, 4, 5. Okay, great, is equal to 1800 plus the MA. So now simply just subtract the 1800, right? Subtract that 1800, that cancels. So finally, ta-da, we have the mass of the airplane. So we take that value, 1.01 times 10 to the 5, and subtract out the 1800. And we get a value of about 9.9, right? So here we have a value of 9.9 times 10 to the, what do we got? Looks like to the fourth. Okay, and that's in kilograms. All right, great. So that's the mass of the airplane. That's for letter A. All right, great. So there's letter A. Now, let's take a read over letter B. So it says, calculate the force exerted by the tractor on the airplane, assuming 2200 newtons of the friction is experienced by the airplane. All right, so let's draw a little sketch here. Now, there's a couple of ways you can actually do this problem. All right, let me detail the airplane here, all right, as a point, and let me detail the tractor here as a point. So let's talk about the points individually. All right, now, what forces are acting on the airplane? Well, it says that 2200 newtons, of the total 2400 newtons of the frictional force is acting on the airplane. So remember, that's going to oppose the motion, point to the left. And that will be 2200 newtons. Okay, great. What are the forces acting on the airplane? Well, the force of the tractor pulling on it, right? Okay, so what is that? Well, we don't know. Don't don't think it's this force, the 1.75 times 10 to the fourth. Remember, that's the force that the tractor exerts on the pavement, not directly on the airplane. So I don't know what that is. So that's my variable here. Okay, this is the force that I'm really looking for, right? That's what it's asking. Calculate the force exerted by the tractor. So I'll say this is the force of the tractor. Okay? And what else do we know about the problem? We do know that the airplane and the tractor, they're both accelerating with the same acceleration. So I'll write a little arrow up here, and it's A is equal to 0.150, right? Meters per second squared. And if we think just solely about the airplane, right, are there any other forces acting in the x direction? No, right? I mean, it's just the frictional force and then the force that the tractor is pulling on it. So guess what? We have everything we need, all right? Recall that we just found the mass of the airplane over here. So we do know the mass. So some of the forces in the x direction will equal mass times acceleration in that direction. So we have the force of the tractor, right, minus the 2200 should equal the mass of that airplane, which we calculated to be about 9.9 times 10 to the fourth, multiplied by the acceleration, which was 0.150. All right, and since I'm just running out of room, all right, I'm just going to solve it here. So it's going to be 9.9 times 10 to the fourth times 0.15, and then plus, right, because we got to bring the 2200 on over. So it looks like we get a value of 1.7. So 1.7 times 10 raised to the, looks like fourth, and that is in newtons, because it's the force. So there you go, guys. All right. That's how you would solve B. Let me give you another, even though the problem's over, let's take another look at how we might be able to do B. All right? To do B. Get it? Okay. So instead of looking at just the airplane, all right, we can look at the total system overall. All right, so what do I mean? So if you guys are interested in viewing it from another perspective, please continue on with me. If not, feel free to turn me down. All right, so here we have the airplane again, and here we have the tractor. Okay, so again, on the airplane, not much has changed. It's going to be the same. Okay, we got a force, the frictional force pulling back, it's 2200. We have the force of the tractor, right, pulling forward. This time I'm just going to call it F, all right? Even though it is the force of the tractor, let me just leave it as F. You'll see why in a minute. Now, that's great. Now let me look at the tractor, okay? So what's going on with the tractor? What forces are acting on the tractor? Well, remember, the pavement is pushing the tractor forward, essentially, all right? And that has a value. That's the value they gave us, right? That was a 1.75 times 10 to the fourth, okay? Also, remember, the total frictional forces were 2,400 newtons, and they told us that 2,200 of that was for the airplane. So then the leftover has to be for the tractor. So that was the that was the, 200, okay, Newton frictional force. And there's one other thing. And here's the part that sounds a little confusing, but I think it'll make sense. So this F, right, represents the force that the tractor is pulling on the airplane. However, remember Newton's third law, okay? If this is the force of the tractor pulling on the airplane, then there is an equal but opposite force that the airplane is pulling on the tractor with. All right, and actually, let me just color that with the same color. So there's an equal but opposite force here as well. So I'll call that F, all right, according to Newton's third law. I did a tug-of-war problem. I forgot the number, but it's early in this chapter. Maybe it was, 18, I don't really remember. In any case, though, I chose this particular method to solve that problem, all right? So this will look familiar to you guys. So I have now detailed fully, right, all the forces in the problem. Also remember that the whole system is moving to the right with an acceleration of 0.150 meters per second squared. All right, so now what I'm going to do is I'm going to look at each of those separately first. Okay, so let me create the force equations for each of them separate. All right, so I have the sum of the forces. I'm just going to use some of the forces in the x direction, okay? So I'm just going to start plugging in the values. You know what? I want to, but I can't. It's my OCD. I'm sorry, guys. I have to do this first. Okay, so now that I have this for the airplane, okay, this is purely for the airplane. The forces for the airplane is going to be the force, right, that the tractor is pulling on the airplane with, minus the 2200 frictional force, should equal then the mass of that airplane, which was 9.9 times 10 to the fourth, and then multiplied by the acceleration of that airplane in the x direction. Fair enough. Now, let's do it for the tractor, okay? So the sum of the forces in the x direction for the tractor will be equal to the mass of the tractor, right, times the acceleration in the x direction for the tractor. So what are the forces on the tractor here? Let me just draw a little line. Oop. So we don't, okay. So, well, we have the positive, right, 1.75 times 10 to the fourth. We also have that, I'm just going to write it underneath. We also have the negative 200 frictional force and also the negative force, right, that the airplane is pulling on the tractor with, which is the same force as the tractor is pulling on the airplane with. That whole thing should be equal to the mass of the tractor, which they told us was 1800, multiplied by the acceleration of that tractor. Okay, cool. So now where do we go from here? So let me simplify a couple of things, and what I'm going to do is I'm going to solve both of them for the acceleration. All right, why am I going to do that? Think about it, follow me here, and then let me know what your answer is, although I can't hear you. You'll see if you're right, all right? I'll let you know why in a second. So let's just solve both of these for acceleration, and we'll clean it up a little bit, combine some like terms if possible. So here we have f minus 2200 all over 9.9 times 10 to the fourth. That's equal to ax for the airplane. And then on the right-hand side, we combine the 1.75 times 10 to the fourth minus 200. That'll barely make a difference. So we get 1.7. So this is 1.73 times 10 to the fourth. That's minus f, right? Minus f. And that is then over 1800. Okay, and that whole thing, let me erase this a little bit, sorry. That whole thing is equal to now ax of the tractor. Okay, so why did I do this? Remember, the whole system is moving with the same acceleration. So guess what these values are to one another? Those values of acceleration are equal. And therefore, what can I do? I can now make these equal to one another. So let's do that. All right, so here's my new equation. I have f minus 2200 all over 9.9 times 10 to the fourth is equal to 1.73 times 10 to the fourth minus f all over 1800. Okay, now if I just do a little math, you'll see that the force comes out to be the same. So what I'm going to do, I'm just going to bring the 1800 up to the numerator there and then divide the 1800 by the 9.9 times 10 to the fourth. So 1800 divided by 9.9 times 10 to the fourth. So I get a value of 0.0182, it looks like about. And that's going to be multiplied then by the force minus 2200. And that equals 1.73 times 10 to the fourth, minus f. Just distribute now the decimal here, so 0.0182f minus, so 0.0182 times 2200 works out to be about 40, right? 40.0 equals 1.73 times 10 to the fourth minus f. So now bring this f, add it on over to the left-hand side, okay? And then take this value and add it on over to the right-hand side. And let's see what we get. So now we should get 1.0. Now I have to have three significant figures here. So, well, actually, no, that's an exact one. So I'll go all the way out. 182 f, that will equal now. So we had 1.73, second e to the fourth minus 40, or excuse me, plus 40. Apologies. Plus 40. So again, it really doesn't change it. Actually, in terms of significant figures, it won't change it at all. So 1.73 times 10 to the fourth. So that's not a mistake, but considering significant figures there, we wouldn't move any of the decimals. So now we just divide out the 0.0182 from both sides. 0.0182. My handwriting is getting terrible here. All right, and now 1.73 times 10 to the fourth divided by 1.0182. And would you look at that? We get a value of 1.7 when we round, right? Exactly. Times 10 to the 4th newtons. Isn't that a thing of absolute beauty? Right? They are the same. So why did I do this? I didn't do this to torture you. Why I did this was I did this to show you that you can look at these problems in different ways. Right? There's different ways to frame the problems. Depending upon what frame you choose, how you decide to frame it, will influence then the math. All right, and how you go about solving it. Obviously, one way was easier than the other, but it doesn't matter. If you see one way over the other, go for it. All right, whichever way you feel comfortable, but you should be able to do both. Number 29. An 1,100 kilogram car pulls a boat on a trailer. Letter A. What total force resists the motion of the car, boat, and trailer if the car exerts a 1,900 Newton force on the road and produces an acceleration of 0.55 meters per second squared? The mass of the boat plus the trailer is 700 kilograms. All right, so take a look over here, guys. I draw a little picture. Here's the car. All right, it weighs 1,100 kilograms. Here's the trailer and the boat. All right, and the total mass of them is 700 kilograms. So this system, the overall system, right, is experiencing an acceleration. Let's assume that it's in the right-handed direction. All right, so I'll put a little arrow up here. So the acceleration they told us is going to be 0.550 meters per second squared. And it now asks us, right, to what's the total force that resists this whole system, right? It's asking what force resists the motion of the car, boat, and trailer. So since it told me all of that, I'm looking at this whole thing as one whole system, okay? So what that means is I have to look at everything as a whole and take the masses into account as a whole as well, okay? So let's draw a little free body diagram here. I'll label this letter A, all right? So pretend that this point right here in the middle is detailing the entire system, all right? Now it says that the car is producing a force right on the road of 1,900 newtons. Now remember that force, the wheels of the car here are pushing back on the road. Okay, but don't draw your vector pointing backwards because that would be incorrect. The way you have to think about it is the car is exerting a force on the road backwards. But that's the force imparted to the road by the car. I'm interested in the forces on the car or on the system, right? So, since the car pushes back on the road with 1,900 newtons of force, according to Newton's third law, the road then pushes back on the car in the equal but opposite direction. And that's the force I'm concerned about, the force on the system. So the road is producing the force on the system. All right? So the 1,900 newtons is pointed to the right. So that's 1,900. All right, there's some force resisting the motion, it tells us. So obviously, remember, forces resisting motion always point in the opposite direction. The vector should be smaller, right? I'll call this the force of friction. How do I know that? Because remember, there's a net acceleration pointing to the right here. Okay, so just to reiterate, this acceleration is 0.550 meters per second squared. Wonderful. And now we have to take the total mass into account, right? So let's just start plugging this into our formula. So the sum of the force in the x direction should equal the mass of the entire system multiplied by the acceleration in the x direction. So we have 1,900, that's positive because it's pointing to the right, then minus, right, because the force of friction is pointing to the left, minus F sub F, is equal to now the total mass. So the total mass would be 1,100 kilograms for the car, excuse me, and then 700 kilograms for the bolt and the trailer, all multiplied by 0.550. All right, so let's just clean it up. So we're going to have 1900. Right? I'll just do this in steps. Minus the force of friction. This will now equal, obviously, 1800, right, times 0.55. And now, all I'm going to do here is subtract this on over, minus 1900. Okay, so that would be the negative force of friction is going to equal 1800 times 0.55, then minus 1900. And it comes out to negative 910, right, negative 910. And now, right, the double negatives would cancel, so now it would just be the force of friction is equal to 910 newtons. And there's your force of friction. Now I might say, wait a minute, Andrew. This value is positive here, but the vector is pointing to the left-hand side. Did you make a sign mistake somewhere? No, I didn't. It should come out positive here. Do you know the reason why? Well, the reason why is because if you look at how I plugged in my force of friction here in the equation, how did I plug it in? I plugged it in as a negative already, right? Because I know it's pointing to the left. So what that means is since I already took its sign into account, the force of friction itself here, not including the sign, should be positive, right? Because the negative, well, I almost looks like an equal sign, but the negative here of a positive number would be negative overall. Okay, so just keep that in mind. If you instead added this in the problem, you would have found then that your force would have come out to be negative. That might have made them more sense in terms of the picture, but it really doesn't matter. All right, if you do it that way, you're saving the negative for the end, and this particular way, I'm taking it into account at the beginning. All right, so now that's it for A. So let's go on to B. So letter B, let's take a read. So it says, what is the force in the hitch between the car and the trailer? Okay, if 80% of the resisting forces are experienced by the boat and the trailer. So basically, what are they talking about? They want us to focus on this hitch between the car and the trailer. All right. Now you can approach this problem in one of two ways. Okay, it depends on how you outline the system of interest. How I'm going to take this, and it's a little bit of a faster way, is I'm only going to look at it from the perspective of the trailer and the boat. That's it. Another way to take it is to look at the system as a whole and detail each of these two parts of the system individually. Okay? So let me first take the former approach. So we have our axis, and this little dot here will represent the boat and the trailer. So first, it tells me that 80% of the forces that are resisting the motion, right, are experienced by the boat and the trailer. Okay, so if I had to find that value, how do we do that? Well, it's simply the total resistive forces that we just found, the 910, right? So 910 multiplied by 80%, or 0.80. Okay, and what does that work out to be? So 910 times 0.8 is 728. So this would be 728 newtons pointing to the left, resisting the motion. Now, there is some tension, right? There's a hitch here, okay? And there's a car here that's pulling the trailer and the boat to the right. So there's some tension or some force applied, whatever the heck you want to call it. It doesn't matter. You could call it the applied force. You could call it tension because we're talking about a hitch here. It's kind of like a string, right? I mean, it's not a string, it's a chain, but you understand what I'm saying. So what I'm going to do is I'm just going to call it the tension force, okay? Now that should be, if you think about it, this should be greater, right? I'll call it T. It should be greater, though, than the resistive force. How do I know that? Well, the darn thing is moving to the right, correct? Remember, this trailer and boat are still experiencing an acceleration in the right-handed direction of that value. So I know this should be larger, okay? So again, if I get a number that's smaller, that's a problem. If I get a number that's larger, doesn't mean I'm right, but it means I'm on the right track. Then you just got to make sure you didn't make a silly mistake with your math. So, looks like, did I miss anything? Oh, and then I really didn't, but in terms of then I would just have to detail the mass, right, of the system of interest, but that I'll do in a second. So now we'll take the sum of the forces in the x direction should equal the mass of the object in question, or the system in question multiplied by the acceleration in that same direction. So here we have a tensional force, okay, and that's positive, minus then the 728, because that's in the negative x direction. The mass now of the system, remember, I've just taken the boat and the trailer into account, so that's 700, and the acceleration was the same, positive 0.550. So now multiply that together, then add the 728 on over 728, and we should get the tensional force to be, let's see, 700 times 0.55 plus 728, and look at that. We get a value of 1.11 times 10 raised to the third newtons. And again, like I said, it should be greater than the 728, which it is. All right, so that does make sense. All right, so what I'm going to do next is I'm just going to detail the second method, okay, just in case for those of you who might be curious. You can follow along with that. If not, feel free to shut the video off at this particular point, but just remember to subscribe. Okay, in any case, second method here would be same thing in terms of the boat and the trailer. Okay, the boat and the trailer here, when I draw my free body diagram, we still have the 728 Newton force, okay, pointing to the left, and we then still have a force of tension, okay, pointing to the right. Fine. Then we also now are going to detail the car separately, okay? So what's going on with the car here? Well, remember, the car is applying a 1900 Newton force to the road. And then therefore that road is imparting a 1900 Newton force on the car. And which way is that pointing? It's pointing in the same direction we had before, right? Right here, 1900 newtons, okay? So it's going to be pointing to the right. So this is 1900 newtons, all right? And now here's the thing. You might say, okay, that's great, that's all. But it's not. Because there also is a tensional force pointing back towards the boat and the trailer. You might say, well, wait a minute, why is that? Why am I going to draw that in? Remember Newton's third law, right? The car is pulling, the car here, let me go back to my picture, guys. The car here is pulling, tugging on the trailer, right? But that's only half the story. The boat and trailer are also tugging on the car, right? Newton's third law, okay? So what that means is I have these two tensional forces. It's not really two, but they're the same tensional force, but it looks like there are two, okay? So now remember, this overall system both, well, not overall, I'm looking at them individually. So remember that this system experiences an acceleration. So we have that this is this is acceleration is equal to 0.550, and same thing here, a is equal to 0.550. So now, and that's both in the same direction, right? Whoops, sorry. So now that's both in the same direction. Now here's the thing. Let's create both equations for both systems, all right? So I'll detail this one as, what am I doing? Some of the forces, in the x direction, let's say, of the boat and trailer, I'll just call it B, okay, is equal to the mass of the boat and trailer times the acceleration of the boat and the trailer, right? So what does this formula work out to be? So it's simply T, that's positive because it's pointing to the right, minus 728 is equal to 700 times AB, right? Or I should say A sub B. Okay, so that's for the boat and the trailer. Next, I would have, let me detail then for the car. So the sum of the forces in the x direction for the car is equal to the mass of the car times the acceleration of the car, right? So what are these forces now for the car? Remember, this is the car and this is the boat and the trailer. So we have 1900, which is positive, minus T now, all right, is going to be equal to then the mass of that car, which was, where was it, 1100, times the acceleration, right, which we know to be, 0.55, okay? But what I'm going to do here is I'm just going to leave it as a C for now, all right? The reason being is because what I realize here is I have two equations. I don't have two unknowns, but I do know that these two things are equal to one another. The acceleration of the boat, the acceleration of the car. So what can you do? Well, you can solve one of these two equations for the acceleration. So for example, if I were to solve the bottom one for the acceleration, it would be something like this. I'm just going to call it A now, all right, because they're both the same. So this would be 1900 minus T divided by 1100. And then what you can do, right? You can solve this one also. You know, it might be even easier. Well, no, it doesn't really matter. So let's just take this value and plug it into the acceleration here. Okay, I'll give you the overall equation and then you'll do the math. All right, but it will come out to be the same. All right, just so I can move on to the next video for you guys. So my handwriting is a little sloppy there at the bottom. I apologize. All right, so here's the equation. So I'm going to rewrite this one. All right, so we got, where should I put it? I'll put it right above. I'll put it in red. So we have t minus 728 equals 700 times now, instead of the a sub b, we're going to substitute this whole thing in, 1900 minus t over 1100. And now if you solve for t, guess what you're going to get? You're going to get the same value of 1.11 times 10 to the third newtons. Okay? Should come out exactly the same. If it's off by a slight little margin, it's because of the rounding somewhere. All right? But it should all work out the same. So practice that on your own, guys. But you should be aware of both cases. Again, it's almost a different problem depending upon if we frame it, meaning if we frame it just in terms of the boat or the boat and the car, right? If your professor wants you to detail both systems and try to create an equation detailing both, you're going to have to do it that way. But obviously, this particular method right here is a lot easier. It's a lot shorter. Number 30, letter A. Find the magnitudes of the forces F1 and F2 that add to give the total force F subtotal, shown in figure 4.34. This may be done either graphically or by using trigonometry. So here I'm going to use trig. All right. So basically what we need to do, here is our triangle. It's a right triangle, therefore we can use SOHCAHTOA. And the hypotenuse of the triangle has a value of 20 newtons, it says. We know this angle, and what we're looking to do is find these two sides. All right, so let's first start with F1. So again, knowing the hypotenuse, knowing this angle, and if I'm looking for the side adjacent to that angle, what trigonometric function should we be using? If you said cosine, you would be correct. So let's do cosine of theta will equal the adjacent side over the hypotenuse. So the cosine of that angle, 35, will be equal to the adjacent side, which was F1, divided by the hypotenuse value of 20. All right, and now all we need to simply do here is basically cross-multiply, right? This is really over 1. So I can just cross-multiply these values there to get my answer. Okay, so F1 will be equal to, take out the calculator, cosine of 35 times 20, and we get about 16.38, right? And looks like I got to have two sig figs here, so I have to round down to 16. All right, so this will be 16 newtons. Okay, so that takes care of F1. Now let's take a look at F2. F2 is over here. Same procedure, all right? I'm going to use the hypotenuse again of 20. I know this angle. I'm looking for the side opposite of that angle. Therefore, we're going to use sine. Okay, so sine of theta is equal to the opposite side over the hypotenuse. So the sine of that angle, 35, will equal F2, now over 20. And again, same thing, just cross-multiply. So the value of F2 is sine of 35 times 20, 11.47. All right, but again, we got to round to two sig figs, so it rounds it down to 11. All right, so, okay. So now, actually, what I'm going to do down here, let me just put the actual value, well, not the actual values, but let me put down a value that's a little more accurate because I see where the question's going, and if I use these rounded numbers, it's not going to work out to be so nice. So 16.38, this was 16.38. Although, like I said, considering significant figures, these two would be your answers. All right, let's move on to part B. So part B now says, show graphically that the same total force is obtained independent of the order of addition of F1 and F2. Okay, so basically, take a look at the graph up on the right-hand side. What I'm going to do here is I'm going to draw a coordinate system, all right, and my origin, I'm trying my best here, but it keeps moving. Actually, you know what, can I do this? No. So the origin here, let me use my there we go. Okay, so the origin is going to lie right here, Okay, so basically what they did, they put down F1 first, right? They started at the origin, they put F1, and let me do a different color. They started at the origin, they put down F1 here, and then they added F2 to it. Now, instead of going in that order, okay, instead of doing F1 and then F2, they want to see if we would get the same hypotenuse if we did it the other way, meaning if we did F2 first and then F1. So what would it look like if I drew F2 first? Well, it just would look like this. I would just go up. And it would be the same height, so that would be F2. And then, starting at the tip of F2, I put the tail of F1, and F1 looks just like this, and guess what? It would be exactly the same, right? I would get exactly the same hypotenuse, okay? So that's basically what letter B is asking in terms of graphically. So it should make sense. Letter C. Okay, so it says find the direction, all right, find the direction and magnitude of some other pair of vectors that add to give the total. Okay, so let me first draw for this letter. So this was part A. I did part B up here. And now let me do part C. Okay, so let me just draw a right triangle. Okay, so now here, if the hypotenuse is 20 and this angle is 35, then there's only one pair of vectors that work. All right, it would be exactly what we calculated over here. All right, this side, right, F2 would have to be 11, and F1 would have had to have been about 16. Okay, no other combination, no other value here or here would work. All right, if this angle here is 35. But what we could have done, and we saw that before, we could have switched those two vectors. So I could have placed vector F1 over here of 16, okay, and then vector F2 over here. But the difference now is this isn't 35 degrees anymore, right? What angle do you think that would actually be? It would actually be 90 minus 35 degrees, right? It would actually be 90 minus 35 degrees. So if we were to do that, what would that work out to be? So 90 minus 35, well, actually, this angle up here would be 35, right? You might notice that. And the reason why it's 90 minus 35 is because that's still a right angle in here. Remember, all the angles inside of the triangle then add up to 180. So I'm missing, right, that angle in there. So the angle would be 55, okay? But again, this doesn't give me a new pair. It just gives me a reorganized pair of 16 and 11. So basically, what am I saying? I'm basically trying to show you that the angle, in order to have a value of 20 and have a different pair, like an x and a y here, this angle would have to be not 35, and it could not be 55. It would have to be some other value other than those two. It doesn't even matter which, any other number that's acute, right? So make it up. I don't know. Let's make it 20. Right, let's make it 20. And if I make that angle 20, right, and if I want to solve now for my x, what do? Well, guess what? It goes back to the same procedure we did for part A, right? To solve for this x, I know the hypotenuse, I know this angle, I'm looking for the side adjacent, therefore I'm going to use cosine. Right, so cosine of theta is equal to the adjacent side over the hypotenuse. Cosine of 20 now will equal, what do we got? X over 20. All right, so then x would therefore be, just plug it in, cosine of 20 times 20. So this is about 18.79, so about 19. Okay, great. And then I would do the same thing for y. Let me just choose a different color. All right, so y here, how would I solve for that? Again, I know the hypotenuse, I know this angle, I'm looking for the side opposite of that angle. That sounds a lot like sine to me. So that's opposite over hypotenuse. So then therefore the sine of 20 will now equal y, all right, over 20. And y will then equal sine of 20 times 20. So 6.84. Again, I got to round to 2 sig figs, so 6.8. All right, 6.8. And this now, oops, these now would be a new set of, or a new pair of vectors. Okay, so this pair gives the same total, right? But the only difference is that the angle is now different, right? And the angle is not 35, it's not 55, it's some other value. All right? So, and you could have chosen any other angle, like I said, not 35, not 55, and you would have been fine. Number 31. Two children pull a third child on a snow saucer sled, exerting forces F1 and F2, as shown from above in figure 4.35. The figure's on the right, though. So find the acceleration of the 49 kilogram sled and child system. Okay, so just take a look at the photo picture over here, guys, on the right-hand side. So here we have two children. One is detailed as F1, and the other is detailed as F2. F1 is pulling at an angle of 45 degrees north of east with a resultant vector value of 10. F2 is pulling at an angle of 30 degrees right south of east and has a resultant vector value of 8 newtons. And I detailed that here in my free body diagram. Okay, they also told us the frictional force here, right? And that frictional force, it's not mentioned to us in which way it is directed, because remember, the frictional force will always just oppose the motion. So in order to really figure out what direction the frictional force is pointing in, we'd have to figure out what's the direction of the overall resultant vector of these, right? Two vectors. Now, just from the picture, you can probably tell it should lie somewhere in here, right? But we actually should calculate it. We don't necessarily need to know the angle, but it probably would be a good thing to do anyway. So in order to calculate the resultant vector of these two, remember, we can add the vectors together and then find the resultant from there, right? So I'm just going to set up my component table here. All right. Anytime I know I'm finding a resultant vector from component vectors, I know I'm always going to use this method. So let me use this as my F1, okay, and this color for my F2. So first let's look at F1, and I'm going to use the vector in red here. So remember, it has an X and Y component. Here's the X component, right? Here's the Y component, straight up. Okay, they're both positive. All right, so in order to find the X component, right, we're going to be using cosine. Why? Because I know the hypotenuse, I know this angle, and I'm looking for the side adjacent to that angle. So cosine of theta will equal opposite over hypotenuse. Okay, cosine of 45 will equal I'll call it F1 of x, all over the hypotenuse value of 10. So F1 of x now should simply equal, take cosine of 45 and multiply it by 10. And we get a value of 7.1. It's 7.1, and that's in newtons. So take that value, plug it into your table. 7.1. Great. Next, let's do a y. Obviously, now that's going to be just the sine. That's opposite over hypotenuse. So the sine of 45 will now equal F1 sub y, okay, for the force of 1 in the y direction, multiplied by the hypotenuse of 10. So when I do that math, it simply comes out to be the same, right, because it's a 45-degree angle, 7.1 newtons. So plug that in, 7.1. Good. Now, moving on to the vector in yellow here. Remember, this has both an x and y component as well. Here's the x component, it's positive, and here's the y component, it's negative. Keep that in mind, okay? So to find the x component there, we're going to use cosine again. Sorry. So we're going to use cosine again. Cosine of theta is equal to adjacent over hypotenuse. So cosine of 30 is equal to F2 sub x all over 8. So F2 sub x will equal, take cosine of 30 and multiply it by 8. And we get 6.9. So this is 6.9 newtons. Plug that into your table. So 6.9. Now let's do the y value. Okay, so y would be sine. Sine of theta is equal to the opposite side of the hypotenuse. So sine of 30 is going to equal, now here's the thing, remember we said that the y component here was pointing in the negative direction, and what that means is that we're going to have a negative, right? F2 sub y all over 8. Okay, so negative F2 sub y Cosine of 30 is half, so therefore this should be 4, right? 4.0. Now simply just distribute the negative sign on over to the left. I'm going to do that by erasing it and just putting it on over here. And that's in terms of newtons. So now add that to your table. So negative 4.0. Now go to the component table, and remember, when you add up these components now, both x and y individually, we do find the components of our resultant vector. Okay, so take 7.1 and add it to 6.9. What do we get? We get a value of 14. And now just do the subtraction here, right? 7.1 minus 4.0 should be 3.1. Perfect. Now what does this look like? Well, why don't we draw a coordinate system? Okay, let's go out 14 units on the x-axis. 14. Let's then, at the tip of that vector, let's draw the tail of the y. Let's go up 3.1 units. And now the resultant here is simply going to be, right, the hypotenuse of this triangle from the start to the end. All right. So how do we solve for this? Obviously, it's a right triangle, so we can use Pythagorean's theorem. All right. What this resultant formula is basically a reworked Pythagorean's theorem. Okay, sum of all the x's squared plus the sum of all the y's squared. So I already summed them all up. Right, so square root of 14.0 squared plus 3.1 squared. All right, great. So plug that into your calculator. So square root of 14 squared plus 3.1 squared. And we should get a value of 14.3. So 14.3. And that is in terms of newtons. So that is the resultant force. Okay? So that's the net force that, when I combine these two vectors, that is the net force on the snow saucer sled. So, and that vector, right, would be like right in here again, right? Isn't it? That's basically what we said before. It should be somewhere in there. Now, we don't need to, but why don't we just calculate the angle quickly, okay? So, the angle of the resultant vector. So, we would do that by doing tan of theta, right, is equal to the y value over the x. So, the tan of my resultant angle is simply 3.1 over 14.0. So, do that division. Okay, 3.1 divided by 14. And then do the inverse tan, or second tan of 0.22. And what do we get? We get about 12, right? So this works out to be 12 degrees. Great. So that's the value on in here. 12, that's the value, 12 degrees, 1, 2. And that should be, again, if you go back to the main free body diagram, that looks like 12 degrees in there, right? So it all makes sense. Okay, now, so the whole picture looks like this now. Let me draw the resultant vector at 12 degrees, north of east. So this is 12. Okay, and the value of this resultant vector we found to be 14.3. Now, this is the net movement, meaning the sled. If you go up to the upper right-hand corner with the picture, the sled is experiencing a net force in this direction, right? Okay. So, if this saucer is moving in this direction, where's friction pointing? In the exact opposite direction. It's pointing that way, right? Does that make sense? So in terms of my free body diagram down here, I have a force of friction pointing here. Right? And it looks like a little bit of an angle. I don't know if I'm going to get it perfect, but that's reasonable. So it's pointing here, okay? It's not to scale, right? It's smaller. So I also got to make it straight and a little smaller. That's good enough. So here it told us it has a value of 7.5. So this is 7.5. Now what's the angle? What's this angle in here? It's going to be the same, right? That's going to be 12 degrees. The same as the angle over here, right? Alternate interior angles or whatever the heck the theorem is. Okay. So that's fair. All right. Now, do I really need to know this angle in order to solve the problem? No. We don't need to take into account x and y components of the force of friction or the frictional forces and whatnot. The reason why is because the frictional force always just opposes the motion directly. So, in other words, I only care about the linear values here, okay? Because I know it's going to move net this way. and therefore the force of friction is net this way. So in other words, I can kind of just rotate the system a little bit, right? I mean, if I wanted to just make it a little nicer for myself, I can just simply put now the 14.3 on this x-axis, right here. This is 14.3. And then put the force of friction on the x, on the negative x, right? Over that way. And that would be then the 7.5. And now this problem looks nice and easy, right? So remember, it says that we have to find the acceleration. So it appears that we should be accelerating to the right, correct? So we have this, okay? And we're looking for the A here, right? And we do know the mass. They told us it was 49.00 kilograms. So I have everything I need. Let's start using the sum of the forces equals ma. So the sum of the forces in the x direction should equal max. So we have 14.3 minus 7.5, because those are the two forces, is equal to 49.00. Sorry, I ran out of space, times a. Okay, actually, let me just try to sneak in the a right over here. So just divide out the 49 from both sides, right? 49.00. So my a value now will be, and as you can see, it's going to work out to be positive, which it should be, minus 7.5, and divide that whole thing by 49. So we get 0.14. So 0.14 meters per second squared. So that is the acceleration. Okay, that's the magnitude. And again, they might now find the acceleration. Yeah, acceleration is a vector, right? So technically speaking now, I can simplify it how I did here. Okay, I can kind of put it right on the x-axis, but if you have to give a direction now for that acceleration, you really have to, take it into account. You have to take the directions over here into account, right? You have to take the directional component of the net force. All right, so technically speaking, this simplifies it, all right? But if you now have to give a direction to it, please do not say in the positive x-axis or, due east or whatever, because it's not. Remember, according to the picture up here, we're going to have a net force in that direction, okay? So completing this, assuming we have to give an angle and whatnot, we would say that, this snow saucer sled, I can't say that fast. I have to pause when I say that. Snow saucer sled has an acceleration. No, that's an O. Has an acceleration of 0.14 meters per second squared at 12 degrees north of east. Okay, that would be a complete description of the acceleration. Number 32. Suppose your car was mirrored deeply in the mud and you wanted to use the method illustrated in figure 4.36 to pull it out. Letter A. What force would you have to exert perpendicular to the center of the rope to produce a force of 12,000 newtons on the car if the angle is 2 degrees? All right. So the picture on the right-hand side here shows what's going on, right? Now what I really need to do is although they're talking specifically about the car, I really should look at this whole thing in terms of an entire system, meaning the car and the tree. Okay, so what I'm going to do is in my axis here, I'm going to basically draw 2. Okay, so this particular point here will represent the car. So let's detail the force vectors there. Okay, so it looks like we have this tensional force. Right? I know that looks like a 45-degree angle or so, but it's 2 degrees, all right? And they said 2.00, but that's fine, 2 degrees. And then there's another force here in the picture right on the tree trunk, pointing in the exact same and opposite direction. Well, not exactly the opposite direction, but the x's will cancel here. Okay, so it's pointing like that. Yeah, I'll just extend a little bit and make it look a little more similar. I'm really getting bad at this. Okay. That's as good as it's going to get today, ladies and gentlemen. So 2 degrees. Okay. Now this, there is some force here, right? It's called T in the problem, right? But do we know what it is? Well, we kind of do, right? Because it says, if you read it carefully, it says, what force must you exert perpendicular to the center of the rope to produce a force of 12,000 newtons on the car? So this T value here is actually 12,000. Okay, so I do know that. So instead of calling it T, I'm going to call it 12,000. And if there's a 12,000, right, Newton force here, then there must be an equal but opposite force on the tree trunk of 12,000. Okay, so now they're asking us to find the F perpendicular. So first, before we connect the two, all right, let's just try to focus in on this particular picture and break each of them up into their own components. All right, because basically what I'm looking to do is I'm trying to find the resultant vector. And actually, I mean, if you think about it, I kind of answered the question already. The resultant vector is going to look something like this, right? And guess what that resultant vector is in my picture at the top right? Yeah, it's the F perpendicular, right? So that's how they're connected. So let's find the components. We'll create a component table, okay? Component table, my X and my Y's. And let's take a look at each of them. We'll call F1, right? F2, and then we'll sum them all up to be the resultant, all right? So let's take a look at this as the first one. It doesn't really matter. So if I had to break that up into components, there is an X component here, and then a Y component straight down, right? So how do I find... First, am I really even concerned about the X components? We can probably even speed this up, right? If you think the X component of the first vector on the left-hand side is pointing in this direction, and then the X component of the tree trunk's force is pointing in the exact opposite direction. And they're literally going to have the same magnitude because both triangles here, right, will have the same hypotenuse and the same angle. They're just going to differ in sign. All right, so just to speed this up, this whole column will cancel. And that'll just be 0, which we expected it to be because we said the net resultant force should be straight down. Okay, so now why don't we detail just the Y's? Okay, so what I want to do here is, I want to try to find one of them here. All right, and then if I find one, I will know the other because they're both the same, right? Okay, so let's do that. So I'm going to use sine because I know the hypotenuse, I know this angle, right? I'm looking for the side opposite of that angle. So therefore, let's use sine. So sine of theta is equal to the opposite side over the hypotenuse. Sine of 2 degrees, right, is going to equal the opposite side, which remember is negative y, right? It's going to be a negative y, so I'll just call it negative y, divided by the hypotenuse of 12,000. Right, so my negative y value will be 12,000 sine of 2. Right, so just do the math and then distribute the negative on over. So 12,000 times sine of 2. And it comes out to 418.7. So let's round to 419, okay? So we get 419. And that's in newtons, and it's negative. So let's say we found that one, right, that I just circled. So if I plug that into the table, it would be negative 419 up here, right? And then what would it be for this vector right there? It'd be literally the same thing, so I'm not even going to bother calculating it again, because it'd be 419. And then what would the total be here? Well, just add them up, right? Just add them together. So we would get 830, what is that? 838. Let me just make sure. Yeah, 838. So it'd be a negative 838. Okay, great. Now just remember, right? So this is the answer, okay? So remember that this resultant vector is the, back to the picture, it is the force parallel that is applied, okay? So to sum it, to answer the question, then the force parallel that must be applied would be equal to, and we can probably make it even positive here, because the negative just tells us the direction. Really what we could do is say 838, right, newtons due south or something. Due south, if we had to give a direction to it, all right? But the negative is correct because it should be pointing down. All right, so that works out, so that's great. So that takes care of that. Now let's move on to letter B. So real ropes stretch under such forces. What force would be exerted on the car if the angle increases to 7 degrees and you still apply the same force found in part A to its center? So what they're basically trying to say here, all right, is that this same force of 838 newtons will still be applied. Okay, so in terms of a picture now, let's try to represent this. Let me change the color. Okay, so let's represent this. So now what I'm going to be doing here, so I'm looking now for the force applied to the car. Okay, so that means I actually don't know the T now. That's what I'm looking for. And it says that this angle here is increased to, what was it, 7 degrees now, right? But we still want to apply the same force. Okay, so remember that if this coordinate system is the is the car, then we would still have to do the same thing for the tree here, right? And notice that when I draw in the vector here, right, I'd have another T value, right? That's T, and this is 7 degrees, okay? So now if I had to detail both Y components here, right, there's a Y component there, and there's a Y component there, okay? What are the value, or what is the value of both of them individually? The value of both of them individually, remember, should be half of the 838 because the 838 was the total of both of them, right? So it just goes back to the 419 that we found before. So each of these will be 419 newtons, okay? Okay, so that's great. So now if I know that, can I just solve for the tension now? Does it really even matter which side I do first? No, it really doesn't matter, right? I can just look at this triangle, or I could try to take them all together. It really doesn't matter. All right. So let's just look at this particular picture. All right. So I'm looking for the hypotenuse, right? I know the side opposite of the angle. So let's use sine here. So sine of theta is equal to opposite over hypotenuse. Okay. Sine of 7 degrees will now equal negative 4.19 all over my hypotenuse value, right? So now hypotenuse will be, and we really don't even need the negative sign necessarily because the hypotenuse, it won't be necessarily negative. It'll have a certain angle to it, but I'll plug it in anyway like that. So we get sine of 7. Actually, I apologize. So we get negative 4.19 divided by that sine of 7, right? And that works out to be now, that's a negative value, a negative 3.44 or so? Yeah, 3.44 times 10 to the third newtons, okay? In terms of, though, answering the question, I would leave out the negative sign just because they're saying, what force would you exert? Now, again, it's not really this. If I had to give a, I would be using really the angle here to give the direction of this tension force, because the tension force is not in a pure X or a pure Y dimension there. All right, so in any case, the answer here would be for part B, it would be 3.44 times 10 to the third newtons. That would be the force that the vehicle would experience. Number 33. What force is exerted on the tooth in figure 4.37 if the tension in the wire is 25 newtons? Note that, okay, so here's the picture on the right-hand side. All right, so what we're trying to do is we're trying to find the force applied to this particular tooth right here if we know the tension in this wire. Okay, now here's the thing. You might say, oh, okay, great. I think I can figure this out. I got a T here, right, and a T here. So they tell me the tension in the wire is 25. So since I have two T's, I guess I should divide by 2 to find each one individually. That would be incorrect, okay? Each of these T's, each of these tensions are 25. Now, why is that the case? Well, if we think about it, the tension they told us in the wire, okay, is 25 newtons. So let's pick this particular point right here. I'm just choosing this point, okay? If the tension in the wire right here at that particular point is 25 newtons, that means the force pulling this way is equal to the force pulling that way, right? So the metal isn't moving, right? It's not breaking of any sort, so these forces have to be balanced. So what that means is that the tension at this particular point is the same as 25 newtons pointing both directions. opposite directions, that is. Okay, so we're not really going to look to divide out or divide t by 2 for that particular reason. So now this problem is actually very, very straightforward. Okay, so this tension here in terms of the hypotenuse of the triangle that's created is 25. Okay, but you do have two triangles that you do have to take into account. Really what I'm looking to do is try to solve this particular y value right there and that one as well. Right, I'm going to do one of them and then just multiply it by 2. It should be fairly straightforward. So for all you dentists out there, let's give it a go. So we're going to use sine here, right? So sine of theta is equal to opposite over hypotenuse. So the sine of 15 will be equal to the y value. Now technically, right, that's negative, divided by the value of the hypotenuse, which was 25. So negative y should be equal to now sine of 15 times 25. Right, so hold on one second, calculator. Sine of 15 times 25. So we get 6.47. So 6.47. Distribute the negative sign to the other side. So this is just telling you, remember, the direction of it. That's one of the y's. Now we have two y's up there. So literally just multiply it by 2. And I think you already see what answer we're going to come up with, right? So we get 6 point... Did I say 49? How did I copy that down wrong? My apologies. Looking at it, that should be a 7. Okay, so 6.47, 47 times 2, we get a value of 12.9, right? So y is equal to, and I know it would be negative here, but that's just giving us the direction. So actually, let me put it down, 12.4 newtons. So the answer, though, would be, we'll just answer it in the positive term. So the force here is going to be 12.4 newtons. And you could say something like, due south or into the mouth or something like that if you had to give the direction. Number 34. Figure 4.38 shows superhero and trusty sidekick hanging motionless from a rope. Superhero's mass is 90 kilograms while trusty sidekick's is 55 kilograms. And the mass of the rope is negligible. Draw a free body diagram of the situation showing all forces acting on superhero, trusty sidekick, and the rope. All right, so there's really 3 main points of interest here. Okay, the first point would be where the rope, I guess, connects to the ceiling. Okay, the second point would be the point at which the superhero is attached to the rope, and the third point would be the point at which trusty sidekick is attached. All right. So now, let's see. Okay, so let's detail all 3. All right, so I'll call this 1, 2, and 3. So let's draw them separately. So here's what the situation looks like at point number 1. So from point number 1's perspective, right, there is a weight, right, pulling down on point 1. Okay, so let me draw that. Right, what's pulling down from point 1? Meaning what's below point 1? Looks like the superhero and the trusty sidekick, right? So this right here, this arrow will represent the weight of the superhero and the weight of trusty sidekick. Okay, that's what's going on there. Now the rope is hanging motionless, okay, so therefore there must be an opposite force pointing up, and that's what the ceiling is doing. All right, so this would be the same thing, but let me just leave that alone for right now. Okay, so this, by the way, this red vector here, right, would be called a basic tension. Okay, I'll call that T1. Now let's take a look at number 2. Okay, from the superhero's perspective. So the point in the middle is going to represent the situation from the superhero. Okay, now what's pointing straight down from the superhero's perspective? Well, his weight, right, is pulling down at that point. And what else? And trusty sidekicks, right? So it's actually, it looks like the same thing here, right? It basically looks like the same thing. So that should make sense because this T1 and this T1 are the same. All right, so this is the weight of the superhero plus the weight of trusty sidekick, right? And that should equal then let me change the color, that should equal then the force pulling back up at that particular point, and that's just T1 that I called before. Okay? Great, and now let's look at it from the third point. All right, so the third point here, another axis. And now, what's pulling down at point 3? Remember, we're just talking about the trusty sidekick, so just his weight, right, is pulling down at point 3. So this is just the weight of trusty sidekick. And then what would be pulling up at that particular point? Well, just the tension, right? Just the tension here. So remember that this particular tension right here, okay, I'll call it, let's say, T2. Okay, there's a certain tension there in the rope. All right, so now we detailed all the components. Now it says, find the tension in the rope above. So letter B says, find the tension in the rope above the superhero. So we're talking about this, right? So they want us to find the tension above the superhero. Okay, so it looks like we have everything we need, right? We have our free body diagram. Let's just go about and calculate it. So the sum of the forces in the y direction will equal the mass of the object or system of interest multiplied by the acceleration of that object. So we have a positive T1, and we got two other forces, right, pulling down, the weight of the superhero and the weight of the trusty sidekick. That should equal then the total masses of the system. So we're dealing with the sidekick and the superhero. So this should be 90 plus 55 times the acceleration. But guess what that is? Big ol' 0. So that gets knocked out, right? So just reorganizing this, we can see that the tension in the rope above the superhero should simply be equal to the weight of the superhero plus the weight of the trusty sidekick. Okay, so this should be easy. How do we calculate weight? Take the mass, multiply it by gravity. So what's the mass of the superhero? It was 90. Right, multiply that by 9.80. Plus then the mass of the trusty sidekick was 55. Multiply that by 9.80. And I know these both should have 3 significant figures, but I'm just taking a shortcut here, I guess. So 90 times 9.8 plus 55 times 9.8. Okay, great. So here we have a value of approximately, what is this, 1.42 times 10 to the third. And that's in terms of newtons. Okay, perfect. So that's the tension above. That takes care of letter B. Now let's take a look at letter C. Find the tension in the rope between superhero and trusty sidekick. So that is my now T2 over here. All right, so what I need to do now is solve it for T2. So I'm really just looking at it from the perspective of Mr. Trusty Sidekick. So we can pretty much solve it right away. So the sum of the force in the y direction should equal the mass of the system of interest multiplied by the acceleration of that system in that same direction. So here we have T2, right, minus just the weight of Trusty Sidekick should equal the mass of Trusty Sidekick, which is 55, multiplied by the acceleration of Trusty Sidekick, but he ain't going nowhere. So we just cancel that. So then therefore, just reworking this a little bit, this would just be T2 is equal to just the weight of literally Trusty Sidekick. So T2 will equal his mass of 55 multiplied by 9.80. And T2 will equal, remember 3 sig figs? All right, so 55 times 9.8, 539. So this works out to be 539 newtons. Number 35. A nurse pushes a cart by exerting a force on the handle at a downward angle 35 degrees below the horizontal. The loaded cart has a mass of 28 kilograms and the force of friction is 60 newtons. Letter A. Draw a free body diagram for the system of interest. All right, so let's take a look at the picture. Here we have a beautiful nurse, and here is a loaded cart. And it seems to be that this nurse is pushing the cart, right? And it's at a downward angle of 35 degrees. So the point of interest here is going to be this particular location where the nurse is pushing the cart, okay, where she's touching the handle. So let's take that part and let's detail it, all right? Let's draw a coordinate system. I'll draw it in black. All right, so we have that here. Now, the force she is applying to the cart, all right, so meaning the force on the cart is going to be applied by the nurse at an angle of 35 degrees below the horizontal. So that should look something like this. Okay, so here's the force. We don't know what it is. I'll just detail it as F sub A meaning the force applied, and the angle here was 35 degrees, right? 35.0 degrees. Cool. And now it says that the cart and that the force of friction is 60 newtons. So we can just assume, right, if she's pushing the cart to the right-hand side, right, that means that there must be a frictional force opposing that motion to the left. Okay? So in terms of my free body diagram, I'm assuming it's moving to the right, and therefore my force of friction now will be pointing to the left. Now it's pointing exactly to the left, meaning it's not in the X or Y plane. Excuse me, it's not in the X and Y plane, it's purely in the X plane. All right, and negative is going to have a value of 60 newtons. I'm not going to put a negative sign here just because I do have the direction in terms of the vector. All right, but I will have to when I consider the math. So now what we need to, so this is the free body diagram. I mean, this is it for letter A. Okay, these are the only forces acting on the object. Remember that the mass of the object in the middle is going to be 28 kilograms. So easy peasy. So letter B now. What force must the nurse exert to move at a constant velocity? So just think, guys, we're doing forces. Is velocity involved directly in the force formulas we've been using? No, right? But it is related. How so? Well, through acceleration, right? Because we have our F is equal to ma forces. All right? F is equal to ma formula. So what does constant velocity mean in terms of acceleration? Means zero, right? So constant velocity is zero acceleration. Keep that in mind. Okay? So now let's try to pick apart this particular picture. Now here's the thing. Okay? I know my force applied vector has a y component and an x component to it. But the thing is, the only thing I really care about is the x component, because that's the only component of the force that's going to move the cart forward. All right? So that's really the only part of that vector I really care about. So what I'm going to do here is I'm going to draw the x component. All right, I'll put that as an arrow. Where are we here? Okay. So let me just call this would be force applied in the x direction. Okay? Now, let's take a look at the formula. So sum of the forces in the x direction, right, should equal the mass of the object multiplied by the acceleration of that object. So we're talking about pushing the cart at a constant velocity. So what does that mean in terms of your acceleration value? It means it's zero. What then happens to that whole side? That goes to zero. So we're trying to find the sum of the forces when they exactly balance and they exactly equal zero. Now, what are the forces in the x direction of this problem? There are two. We have a positive force applied in the x direction, okay, minus then the 60 Newtonal frictional force. And that will equal 0, 60.0, okay? So simply this is this. For the force applied in the x direction is equal to 60 newtons. Okay, now but that's not the answer, all right? Because we're getting close to the answer, but this is the force applied in the pure x direction. Think about, but how is the nurse applying the force? She's applying it at an angle, right? She's applying this force. So this is the force we need to find, because that's the applied force that she is applying at 35 degrees below the horizontal. So how do we connect now what we just found here to that? Remember, you just found this side of the triangle, right? We're going to be doing, I think that's what I heard, if I could hear you through the computer. I think you said we're going to use cosine, right? So that would be great. And yes, we will. So we're going to have cosine of theta is equal to the adjacent side over the hypotenuse. Right, so cosine of 35 will equal the adjacent side, which was the force applied in the x direction, which is the same thing as the 60 newtons, right? That gets plugged in now, all over my hypotenuse value of the force applied. Okay, simply switch these two variables to solve this for force applied. So that would be 60 all over cosine of 35. So simple now, just literally plug that into your calculator. So it's got 60 divided by cosine of 35. and it comes out to be 73.2. So we got 73.2 newtons. Okay, that would be the force that the nurse would have to apply at an angle of 35 degrees below the horizontal on the cart so that it overcomes the force of friction and is able to move at a constant velocity. Number 36. Construct your own problem. Consider the tension in an elevator cable during the time the elevator starts from rest and accelerates its load upward to some cruising velocity. Taking the elevator and its load to be the system of interest, draw a free body diagram. Right, then calculate the tension in the cable. Among the things to consider, the mass of the elevator and its load, the final velocity, and time taken to reach that velocity. So here's a little problem. Okay, I have an elevator here. Let's just say it has a mass of 800 kilograms in total with all the occupants and the elevator itself. It's, let's say, going to start at rest, and it's going to have a positive acceleration on upward at 0.5 meters per second squared. All right, so let's do a couple of things. I'll frame a couple of problems given this information, and we'll just solve it quickly, okay? So the first question is, if the elevator is at rest, okay, so at rest, what's the tension in the cable? What's T? What's T? I'm just going to leave it like that. At rest, what's T? So first we need a free body diagram, okay? So here is the particular point of the elevator, all right? We're going to have a force pointing downward, correct? And what would that be? That would be the weight, right, of the elevator, okay? So there's the weight of the elevator. Great. And then what's the force pointing up? Well, remember, there's a cable there, okay? So if it's at rest and it's not moving at all, no acceleration, that must mean that we have an equal but opposite force there, right? And that we'll call the tensional force, okay? So we can simply now take a look at the formulas, all right? So we got some of the forces in the y direction is equal to the mass of the object in interest multiplied by the acceleration of that object in that same direction. So we have tension, which is positive, minus the weight of the elevator, should equal the mass of that elevator, 800, multiplied by acceleration, but it's not moving. So that whole thing cancels. Simply then add the weight of the elevator on over to the right-hand side, and we get that the tension is equal to the weight of the elevator. Now that should make sense, right? That's what we kind of expected it to be. And the weight of the elevator, remember, is found by taking the mass of that elevator and multiplying it by gravity. All right, and when we do that, let's just see what we get. 800 times 9.8, 7.84. So this is 7.84 times 10 to the third newtons. Great. Now, once the elevator starts accelerating upward, what do you think is going to happen to the tension in the cable? Do you think it's going to go up or go down, and why? All right, so think about that and let me know, well, let yourself know how you did. All right, so let's now take a look at when it's accelerating. So let's draw now a free body diagram. Actually, first let me say when A is equal to 0.5 meters per second squared, what's T? The tension in the cable now. Okay, so again, free body diagram. Okay, what's the force pointing downward? Well, it's always just the mass of the object. Excuse me, it's the weight of the object, not the mass. Okay, it's the weight of the elevator. And then we're going to be met by some tension, right? There's going to be some tension in the rope pulling it up. We don't know what it is at the moment, so let's just call it T. But now we do know that there is an acceleration of this elevator on upward. Okay, and that acceleration is equal to 0.5 meters per second squared. Great. Now let's frame our our force problem. Okay, so some of the forces in the y direction will equal the mass of the object in question multiplied by the acceleration of that object in that direction. So what are the forces in the y? So we got a positive tension minus the weight of the elevator is equal to the mass of that elevator, which is 800 kilograms. Now we have an acceleration, so it's 0.5. Okay, so why don't we... what's the weight of the elevator? I mean, we just found it before, right? That's the same as the old tension. Okay, so basically what we're looking to do here is we'll add the weight of the elevator on over to the right-hand side, correct? So that will have tension is equal to 800 times 0.5, right? Then plus the weight of the elevator, which was 7.84 times 10 to the third. And now the new tension would be, and notice we're actually adding the weight to it, right? So it's actually going to be going up. So those of you who thought it might be going up were correct. And the math works out to be here 8.4. So we got 8.24, right? 8.24. 8.24 times 10 to the third. And that's in terms of newtons. So the tension did go up. And that should make sense, right? If you're trying to accelerate the object on upward, it's like you're pulling even harder, right, on the elevator. The chain is pulling even harder. The cable's pulling even harder. And therefore, the tension in that cable should be going up, right? So that kind of makes sense. Now, I can ask you anything I want as far as, velocities, final velocities, times, this and that. It depends on how I want to frame the question. So let me now ask, I don't know. Why don't we say, what's the final velocity after a 10-second ride? Okay, so what do we know? We know the elevator is starting out initially. We know the acceleration of the elevator is 0.5, right? What else do we know? We know the time now, right? I said 10 seconds. We don't know the final velocity, and we don't know the distance it would cover. So we have to think of a formula that relates these four things together. And if you remember back to the prior chapter, chapter 3, we have the final velocity equaling the initial velocity plus the acceleration times time. So the final velocity will be equal to 0 plus the acceleration of 0.5 multiplied by the time, 10 seconds. So the final velocity here would be 5, right? 5.0 if we want, whatever, meters per second. That's the final velocity. Easy peasy, all right? I can then also ask you for the displacement of the object, at a certain point in time, all right? Even consider it in 10 seconds. How far is it going to go? 10 seconds. What formula are you going to use? We're going to use this formula, right? Change in displacement is equal to, there's two equals, sorry, is equal to the initial velocity multiplied by time plus 1/2 at squared. So change in displacement, that whole thing goes to 0 because the initial velocity is 0. So I go 1/2 times 0.5 times 10 squared. Times 10 squared, right? 10 squared is 100, half of 100 is 50, half of 50 is 25. So it looks like the change in height, or I used X, but I really should have probably used Y because it's in the Y direction, but it doesn't affect, the final answer. It's still going to be 25 meters no matter what, but remember, this is really in the Y direction. Number 37, construct your own problem. Consider two people pushing a toboggan with 4 children on it up a snow-covered slope. Construct a problem in which you calculate the acceleration of the toboggan and its load. Include a free body diagram of the appropriate system of interest as the base of your analysis. Show vector forces and their components and explain blah, 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 blah. All right, so I'm taking a slightly different route. I'm giving you actually the mass of the toboggan, and I'm asking you for what force is necessary to accelerate the toboggan up the hill at 1.5 meters per second squared. Assume no friction. You'll be doing problems like this, though, in the next chapter. So I'm just trying to simplify it here. I don't want to get too complicated. So in any case, I'm really only looking at the toboggan here with the 4 children on it, and I'm mentioning that it weighs 100 kilograms. Okay, so now what we need to do is we have to try to figure out how to create a free body diagram that diagrams this toboggan effectively. Now, what's different about this as opposed to other problems is that we have an angle here. All right, so let's think about that. All right, let me do this. What I'm going to do is I'm going to draw my axes at a 30-degree angle, okay? So what I'll do here, let me do this, ready? Let's draw a set of axes, okay? Then what I'm going to do, a little magic, I'm going to take this and rotate it 30 degrees. And let's say that's about 30 degrees. right? That might be about 30 degrees or so. Okay. So now all I did was I just rotated my axis. All right, now here, this point represents the point of the toboggan, let's say right here. Okay. Now, where is the weight of this toboggan pointing? It always points, remember, directly down. Like if you had a plumb line, from this point, it always points directly down. Okay, it doesn't point in this direction. It points down. Well, that's not down. It points down. Okay. So from this free body diagram, I will draw the weight of the toboggan. No, that doesn't look straight down. Draw the toboggan weight straight down. So this vector represents the weight of the toboggan. So weight sub t, W sub t. Okay. Now what we have is we need to then apply some force, right? We're looking for what force is necessary to accelerate the toboggan up the hill. So there must be some force pushing it up the hill, right? I don't know what it is, but that's what we're trying to find. So now in this diagram, I want to find a force, and we're going to assume that we're pushing the cart, or the cart is being pushed, exactly at the same angle of the slope. It doesn't have to be, but we're trying to keep this simple here, guys. All right. So now this value is FA. We'll call it F applied. Okay. So, all right, so things are looking good so far. And now, all right, so it looks like we have a free body diagram. It's a little funky because it's at an angle, but no big deal. All right. If I'm trying to find the acceleration, right, you have to ask yourself acceleration in what direction? Well, we're accelerating in the x direction, right? It's going up the hill. I decided to rotate my axes so that the movement of this toboggan is on the same plane as the acceleration. All right. So the acceleration is purely in the x direction given my, rotated axes. So what does that mean? That means this. That means that I can use the sum of the forces in the x direction formula to help me solve. The mass of the object times then the acceleration of that object in the x direction. So the problem here that I made gave us the acceleration, right? And we do know the mass was 100. Okay, so we know half of it. Right, so the sum of the forces in the x direction is equal to 100 multiplied by 1.5. Okay, so that's fine. So let's just keep going along those lines. So this is just 150. Right? Now here's the thing. Sum of the forces in the x direction. So what vectors are in the x direction? Well, purely the force applied is in the x direction. It exactly lies on the x-axis. But does the weight of the toboggan lie in the x-axis? Directly? No. Does any of it, though, lie in the x-axis? There's the key. Yeah, actually a little bit of it does, right? If you look at this as just a regular old vector, doesn't that have both an x and y component to it? Yeah, it does, right? Guess what this part is right here at the bottom? I'm going to draw it in right here at the bottom. Guess what that is? Let me draw it a little straight. Guess what that is? That's the x component of the weight. Okay, so this, and look where it's pointing back. Doesn't that kind of make sense, right? If you had this toboggan on the hill, isn't it going to want to slide back down? Why? Well, because of this fact. The angle here that's created is actually a 30-degree angle. It's exactly the same as this angle. Remember, I rotated the axis 30 degrees. That's why it's the same. So now if I'm looking to find this side, here's the thing. This is why I never always say, oh, if you want to find x, use cosine. I hate that. I always go through the trig, okay? Because here is where one of those cases you're not going to use cosine to solve for x. But if I'm always looking at it from a trigonometric perspective, I can't go wrong, all right? So the x component here can be found by using sine because this is the hypotenuse, this is the angle, and I'm looking for the side opposite of that angle. So here I could create an equation that deals with sine of theta is equal to the opposite side of the hypotenuse. The sine then of 30, right, will be equal to the opposite side, which I'll call the toboggan's weight in the x direction, all over, and that's negative, by the way, because it's pointing to the left, divided by then the weight of the toboggan itself. So in other words, the weight of the toboggan in the x direction, remember that's negative, right, because it's negative over there, but I'm just going to transfer that sign right away, okay, is equal to negative the weight of the toboggan itself multiplied by the sine of 30. Okay, so this is the value of the x component. Guess what now, guys? I can now use this in my formula because it's an x component. All right, so the force applied, that's positive in the x direction, minus then the weight of the toboggan multiplied by the sine of 30 will be equal to 150. And I forgot the 0 here. I don't know what happened. I probably wrote it, but the pen didn't pick it up. In any case, so now how do we solve for this? It's easy, right? Just add this term on over, okay? But remember, we do know the weight of the toboggan. It's 100, right? So let me just develop this a little more. 100 times the sine of 30, okay, is equal to 150. And now simply just add this, calculate it, and then add it on over, okay? Add it on over. So what do we get? We get 150 plus 100 times the sine of 30. So we get 200. Look at that. So the force here, hold on one second. I call this Fx. I meant to call it F sub A. Okay, I just noticed that. Sorry, this should be F sub A, right? Because that's the force applied. That's the one force in the x direction. All right. So the force applied here will be equal to simply 200 newtons. All right, and that should kind of make sense. Not only do we have to overcome its mass with this acceleration, all right, but we also have to overcome some of the weight that's pointing back on us. So that's why it should be greater than 150. Number 38, unreasonable results. Letter A, repeat exercise 4.29, but assume an acceleration of 1.2 meters per second squared is produced. B, what is unreasonable about this result, and C, which premise is unreasonable and why. All right, so 29 over here on the right, just recall, you can take a look back at the video too, but just remember that we had an 1,100 kilogram car, so here's the 1,100 kilogram car. It's pulling a 700 kilogram in total boat with its trailer, and it was accelerating at a value of 0.550 meters per second squared. So now what they're saying is that, oh, and by the way, the force that this car had placed on the ground, it told us was 1,900 newtons. All right. So let me draw a free body diagram that represents this entire system. Okay. So here are my coordinates. Right. It said that in the problem here, if you look back to here, that there is a 1,900 Newton force that's produced by the front car. So that's pushing the car forward. All right, so that's 1,900. So 1,900 newtons exist here. And they also told us that there is a, they asked us for what force resists the motion. All right, that's right, I forgot. So there is some force that's going to resist the motion here. That actually won't be important though in this problem. All right, just pretend that we don't know it. All right, well, don't pretend. I mean, we don't know it. So what I can now do is I can now see, all right, let me just look at the information that they gave us, okay, that we have an acceleration here of 1.20 meters per second. And I do know the total mass, right? The combined mass of this whole system would be 1,800 kilograms because 1,100 plus the 700. Let me just see what math works out, all right? So let's say I have the sum of the forces in the x direction should be equal to max, right? And just remember also, guys, that this was assuming to have an acceleration in the right-handed direction before, okay? And they tell us that that acceleration is now 1.20 meters per second. All right, so let's see. Sum of the forces in the x direction then will equal the mass, the combined mass of the whole system, which is 1,800, right, multiplied by that acceleration of 1.20. So the sum of the forces in the x direction will equal, so 1,800 times 1.2, all right, so it's 2160. So 2,160 newtons. So already we can see a problem, right? Just think about this for a second, guys. The total force that's needed, okay, to accelerate this system to the right at an acceleration of 1.2 meters per second is this value of 1,160 newtons, okay? But what is the force that the car applies? It only applies 1,900 newtons. So wait a minute. In order to reach this acceleration for this mass, I need 2,000, a little over 2,000 newtons. But the car is going to produce only 1,900 newtons. So how in the world are we going to get to 100 newtons or a little over 2,000 newtons. There's nothing missing in the problem. It's just not possible. That's why it says it's an unreasonable result. All right? So there's no way we can achieve this required force when the only force that's applied in the problem is from the car itself, and it tells us 1,900 newtons. All right? So that's what's unreasonable. And it says, I'm telling you what's unreasonable, so that answers letter B. And then C, it says, what premise is unreasonable? I don't know. There could be a couple of premises. Maybe they measured the acceleration wrong. Maybe it's not 1.20 meters per second. Or maybe the car actually produces more, right, than 1,900 newtons. Maybe the acceleration is right. They are. But then when they measured the force that the car is producing, maybe that was wrong. There could be a couple of things. Number 39, unreasonable results. Letter A. What is the initial acceleration of a rocket that has a mass of 1.5 times 10 to the 6 kilograms at takeoff, the engines of which produce a thrust of 2 times 10 to the 6 newtons? Do not neglect gravity. And then what is unreasonable about the result? Okay, so first thing is, it sounds a little ambiguous, but it says here, the engines of which produce a thrust. So do they mean a total thrust, meaning all the engines produce this Newton value, 2 times 10 to the 6 in total? Or is it really saying that each engine produces this 2 times 10 to the 6 newtons? The way I interpret it, the way it sounds like, this would be the total, but I'm honestly not 100% sure. Regardless, though, of that fact, we would still achieve this, not the same answer exactly, but the same result. Okay, you'll see what I mean in a second. So I'm going to assume, though, that all the engines produce that in total. All right, so here's our free body diagram. We have then the force of the rocket, the weight of the rocket, I should say, pulling down on it, right? So the weight of the rocket. And then we have this thrust force pointing up, right? We got this thrust. So it says the thrust is equal, the total, I'm assuming, right, is 2 times 10 to the 6th newtons. The weight of the rocket, remember the rocket, it told us the mass of it is 1.5 times 10 to the 6th. And that's in terms of kilograms, and then multiplied by 9.81, or 0, I think the text uses here. So 1.5 second e to the 6 times 9.8. And we get a value of 1.47 times 10 to the, is that the 7th? Yes, to the 7th. Okay, that's in terms of newtons. All right. So now, why don't we take a look at our free body diagram here? No, sorry. Well, we already did the free body diagram. Let's take a look now at the F equals ma formula. So the sum of the forces in the y direction will equal the mass of the system of interest multiplied by the acceleration of that particular system. So why don't we do this? Let's assume let's assume this acceleration we don't know, okay, because we don't. So why don't we start plugging in some values, okay? And let's see what happens. So the thrust is in the positive y direction, so that's 2.00 times 10 to the 6th, minus then the 1.47 times 10 to the 7th. That will equal now the total mass, right? And it's just a rocket, so it's 1.50 times 10 to the 6th, multiplied then by the acceleration. Okay, so to find this, just divide out the 1.50 times 10 to the 6th from both sides, right? 1.50 times 10 to the 6th. And we get the acceleration in the y direction will be equal to 2 times 10 to the 6th minus 1.47 times 10 to the 7th. And then we will take that value and divide it by 1.5 times 10 to the 6th. So it looks like it comes out to about negative 8.47, okay? Negative 8.47 meters per second squared. Why is that a problem, guys? Well, look at the sign. What does the sign tell you for the acceleration here? Where is it going? It's going down, right? Now, it's going, so the net acceleration is downward. That doesn't mean that the actual rocket is traveling down, okay? Because I'm assuming it's at takeoff, so it's resting, okay? But the acceleration here is pointing down. What that means is that it ain't taken off, right? It would have to have a positive acceleration for it to take off. So that's a problem, all right? But here's the thing. So this is what I was talking about before. Let's say you didn't assume this to be the total, but instead you thought that this was the, thrust per engine. So if you go back to number 6 and 7 of this chapter, you'll see the rocket has 4 engines. So you would just have to take 4 and multiply this result by it. But if you do that, which is fine, and then you subtract this value from it and do all the math, guess what happens? You still come up with a negative value. The magnitude of the acceleration changes, right? But the sign will not. So, that being the case, like I said, the answer won't be identical, but the conclusion's the same. It ain't going nowhere, all right? So, what's unreasonable? I don't know. What could be unreasonable? Maybe the weight, right? The weight might be too much, or meaning they misweighed the rocket or something like that. I don't know. Or the thrust wasn't enough, meaning they mismeasured the thrust or whatever the case is. Or the engines aren't burning appropriately, or right, there's a malfunction somewhere. Anyway, that would basically be discussing that part. Number 40. A flea jumps by exerting a force of 1.2 times 10 to the minus 5 newtons straight down on the ground. A breeze blowing on the flea parallel to the ground exerts a force of 0.5 times 10 to the minus 6 newtons on the flea. Find the direction and magnitude of the acceleration of the flea if its mass is 6 times 10 to the minus 7 kilograms. Do not neglect the gravitational force. All right, so first part here, let's draw a free body diagram. Right? The center of this diagram will represent the flea. Okay, so first thing, where does this 1.2 times 10 to the minus 5 Newton force show up? Well, you might read it and you might say, well, straight down, because that's where it's pointing. That's what it's telling me, so we draw it straight down. That would be incorrect. Why? It almost sounds like it, how, right? The reason why is because we are concerned, what are we concerned with in this problem? We are concerned with finding the magnitude and direction of the acceleration of the flea, okay? So if I'm concerned with finding the magnitude of the acceleration and the direction of the flea, I better know the forces on the flea, okay? That's the key. So the flea exerts a force on the ground, right? Right? But that's a force produced by the flea. That's not on the flea, right? So according to Newton's third law, when the flea pushes down on the ground with a force of 1.2 times 10 to the minus 5 newtons, the ground pushes back up on that flea with the same magnitude but opposite in direction. And that's the direction we're concerned with, because we're concerned with forces acting on the flea. So the earth or the ground pushing up on the flea is what's important. Okay, so 1.2 times 10 to the minus 5 newtons. Now, there also is in the problem, it says there's a nice, beautiful cross breeze, a parallel breeze to the ground that exerts a force of 0.5 times 10 to the minus 6 newtons. Now, it depends on where you want to draw that. Either to the left, to the right, doesn't matter, but once you choose, it will affect the direction of your resultant vector. So why don't we just assume it's going to the right? And that force is 0.500 times 10 to the minus 6. And how are we looking so far, guys? Are we ready to continue? Meaning, can we find the resultant? Not quite. There's one force that's missing. Right? It said, do not neglect the gravitational force. So guess what? We also have to take into account the mass of the flea. Okay, almost in all problems involving y dimensions, you do not want to forget about the gravitational force. Okay, so there is another vector pointing down, and it represents then the weight of the flea, which can be easily found by taking its mass that was given, right, 6.00 times 10 to the minus 7, multiplying it by 9.80 by the gravitational acceleration value, right? So 6 times 10 to the minus 7 times 9.8. And I punched something in wrong in the calculator. 6 times 10 to the, because I got 5 times 10 to the 38. It's a big weight. So anyway, 6 times 10 to the minus 7 times 9.8. That sounds a lot better. So the weight of the flea is going to be equal to 5.88 times 10 to the minus 6. So that value represents this vector. Okay? Now, we should have everything we need, okay, to try to draw the resultant vector. So what we can do here, why don't we use, since we got 3 vectors, let's use a component table method, okay? You don't have to. You can do it, you can take this value, subtract it from this because it's smaller, and then just make a little triangle out of that result with the force over here, right? I mean, you could do that, but I'm just going to make a component table. I like it a little better. It's a little more organized. Okay. So here's, let's say this is the force that the flea exerts on the ground, and therefore the ground exerts on the flea. So we have that value right here, and it's a pure y value, correct? There's no x component to it, and it's only a pure y in the positive y dimension, and therefore it's going to be 1.2 times 10 to the minus 5 in the y. Next, I have this little breeze, right? So I'll say the force of the breeze, okay? That's going to be a pure x component. I made it in the positive x. You may have made it in the negative x. That's not a problem. It'll just be a slightly different answer in terms of direction, but not in terms of magnitude. So this should be 0.500 times 10 to the minus 6. And this vector right here has no x component, no y component to it, therefore that's 0. Now we have the third vector to take care of, and that's the weight of the flea, right? And that we found was a pure y value, no x component to it, therefore that's 0. And now careful, this one has to be plugged in as negative, 5.88 times 10 to the minus 6. Now when I add up all the components, guess what I get, ladies and gentlemen? I get the resultant vector, and the resultant vector is the net force vector. Okay, so let's add it all up. This column should be fairly simple. 0.500 times 10 to the minus 6. And then we'll add up the y value, so 1.2 times 10 to the minus 5 minus 5.88 times 10 to the minus 6. I have a, looks like a, I thought I put the minus sign there. Yeah, it has to be minus 6. So this value, works out to be 6.12 times 10 to the minus 6. Okay, so guess what now? We can now find the resultant vector. How? Remember, by using this wonderful formula, the resultant vector is equal to the square root of the sum of all the x values squared plus the sum of all the y values squared. Okay? So my resultant vector is going to be equal to the square root of 0.500 times 10 to the minus 6, a lot of zeros here, squared, plus, I'm going to write the next number underneath, 6.12 times 10 to the minus 6, and that is also squared. Remember, you got to square everything there and then square root it all. So the resultant vector here should be second. So square root 0.5 times 10 to the minus 6 squared. That looks good. Plus then 6.12 times 10 to the minus 6, and that's squared. And we get a value of 6.14 times 10 to the minus 6. And that is in terms of, yeah, that looks good. And that's newtons, okay? That is the net force, okay? So now, if I had to sketch this in a coordinate, right? Let's do it over here on the left-hand side. You have an x value, instead of 0.5 times 10 to the minus 6, which is positive. Therefore, it looks like it's coming out over here, right? This is the 0.500 times 10 to the minus 6. Then we had a y component here, which is also positive, right? It's a little greater than the x component, so it should be a little higher. So it looks like we have, that was 6.12 times 10 to the minus 6. And then what's the resultant? The resultant is from the start to the end point, right? So this is the resultant vector. That has a value of the, as we just found, that has a value of 6.14 times 10 to the minus 6. Okay? Now, let's just calculate the degree in here. Why do I need to do that? Well, because it asks me for the direction and the magnitude of the acceleration. But you might say, well, why do I need to know the direction of then the net force? Well, because whatever direction the net force is pointing in will be the same as the direction that the acceleration is pointing in. Right? That's always the case. So I'm just going to find it here. So to find that, we do tangent of theta is equal to the, remember, the opposite side over the adjacent side, right? So in this problem, it's going to be 6.12 times 10 to the minus 6 all over 0.500 times 10 to the minus 6. Theta will then equal, so if we do the calculation, 6.12 times 10 to the minus 6 divided by 0.5 times 10 to the minus 6. And then do the inverse tan of, it looks like 12. Do the inverse tan of 12.2. It comes out to 85.3. Okay, great. So we get a value of 85.3 degrees. That is the theta value. Now that does make sense, okay? considering the breeze wasn't that strong and most of the force came from the flea pushing off the ground. So that's great. So not only is that degree, again, not only is that degree measure for the net force, but it's also the same as the acceleration, because net force and acceleration point in the same way. All right, so we're almost done. Now we just have to find the acceleration. All right, so one more coordinate system and then we're done here. So here's the net force, right? It's up there somewhere. I'm not going to put in the value. I'm just going to write net force. This angle here is 85.3. And then the acceleration now is literally pointing in the same direction. Okay, so there's my A. And that's what we're looking for. Okay, now you might say, well, which formula am I going to use, Andrew? Am I going to use F, some of the force in the X, or some of the force in the Y? Because this isn't in either of their frames, right? Exclusively, it's in the X and the Y frame. Well, guess what? It doesn't matter at this point. Okay, you don't need the subscripts of X and Y because you know that the force is pointing at an angle of 85.3 degrees north of east, and therefore the acceleration is pointing in the same way. So as long as you have those two vectors lined up, it doesn't matter. So instead, what I'm going to do is I'm just going to leave out the subscripts, okay, so we don't get too confused. Now, what the sum of the forces, the net force that is, what is the net force? We just found it, right? It's 6.14 times 10 to the minus 6. That's equal to the mass of the object, which we're talking about a flea. So that they gave it to us as 6 times 10 to the minus 7 multiplied by A. And guess what? All we got to do is divide this on out now, right? 10 to the minus 7. Minus 7 there. Divide this by 6.00 times 10 to the minus 7. And now, lo and behold, we're going to get an acceleration. So 6.14 times 10 to the minus 6 divided by 6 times 10 to the minus 7. 10.2. So 10.2 meters per second squared. And that is, ladies and gentlemen, the acceleration. All right? So, and that's the acceleration. They wanted the direction. I said it 15 times, but let me put it with the answer, right? So at 85.3 degrees, given the way I drew it, north of east. Number 41. Two muscles in the back of the leg pull upward on the Achilles tendon, as shown in figure 4.39. These muscles are called the medial and lateral heads of the gastrocnemius muscle, which, by the way, lies superficially to the soleus muscle and is biarticular, whereas the soleus muscle is uniarticular. But if you want to learn more about that, check out our question series on the Anatomy and Physiology OpenStax textbook. Anyway, find the magnitude and direction of the total force on the Achilles tendon. So what type of movement could be caused? So here I have drawn out a free body diagram that details exactly what's going on here in the picture on the upper right. Okay, we got two forces. Each medial and lateral head is pulling with 200 newtons worth of force at an angle 20 degrees relative to the y-axis. All right, so that's the picture right here. So what we need to do is find the magnitude and direction of the total force, aka the resultant. So guess what we have to do? Just find the components of each of these two vectors and add them together and find the resultant. All right? So component table, let's look at that. So component table X, Y. All right, I'll call this one force 1. Let's just say that's force 1. And then this one's force 2. Okay? And when I add those two components together, I'll get my net force or the resultant force. All right? So let's draw, and if you notice there's symmetry here, so that might help us in terms of we probably won't have to do too many calculations. So here, I'll do one of them, okay? So here's going to be the force in the x direction of number 1, all right? And then this will represent the y component of 1. Okay, now remember that the x here is going to be negative and the y is still positive. All right, so now I drew the triangle here, so I don't have an angle inside of that triangle. I could call this 20 up there, but let me just work off of the x-axis. So remember, it forms a 90-degree angle. If I know that this is 20, then the remainder has to be 70, right? So this is a 70-degree angle in there. So let me look to find x first. I'm going to use cosine because I know the hypotenuse. I know this angle. I'm looking for the side adjacent to that angle. So cosine of theta will be equal to the adjacent side over the hypotenuse. So cosine of 70 will equal negative F1 in the x direction multiplied by 200. So negative F1 in the x direction will be equal to, simply do cosine of 70 times 200, and we get a value of 68.4, right? 68.4. Simply then just move the negative on over to the other side. I'll just erase that over here. 1 second. There we go. And we'll put the negative there. Okay? So write that into your table. So this is a negative 68.4. Great. Let's solve for the y now. Okay? So the y component here, we know the hypotenuse, we know this angle, we're looking for the side opposite of that angle. So that sounds to me like sine. So sine of theta is equal to opposite over hypotenuse. The sine of 70 will then be equal to the force of the first vector in the y direction divided by 200. Right? So simply do your cross multiplication here to find that component. So sine of 70 times 200. Great. And we get 188 considering sig figs. 188. Let me draw that a little neater. 188, and that's in terms of newtons, right? These are all in newtons. Okay, great. Plug that into your table, and it's positive, right? 188. Great. Now let's draw the vectors for number 2, for force vector number 2. It would be an x pointing in that direction, and this would be f2x, right? And then a y pointing up. Okay, easy peasy. So this is f2. Now y. Now we're not going to calculate it because remember this angle would still be 70. All the values, this is still 200. So they're all going to be the same. But the x now is in opposite direction, right? So that would be a plus now, 68.4. And then the y is still pointing in the same direction of 2 as it was in 1. So therefore that would be a positive 188. Okay. Add these together now. That becomes a 0, which definitely makes sense. And then we just have to take this now and add these two together. So what do we get there? 188 times 2 and 376. Great. So 376. That's newtons. So these are the components of my resultant vector. So let's draw it. There's no x component, and it's pure y. And what way is it pointing? It's pointing directly up. And that should kind of make sense, right? Based on the, let me center it a little better. Based on the picture, right? Two equal forces pulling at equal angles, right? There's symmetry. So that should make sense. So here, this is the net force pulling up. It's a positive 376 newtons. That would be the answer to that question. And the direction it pulls up, so this would be up or north or whatever you want to call it. That's fine, right? And then, so basically now all we have to think about, it says what type of movement. So the last part, let me get to the highlighter. Okay, so it says what type of movement could be caused by this force. So, I mean, in terms of anatomical movement, it causes plantar flexion. All right, what does that mean? It means you go on your tippy toes, right? So it's the same motion as if you were trying to reach something trying to reach a cup at the top of your cupboard. You couldn't reach it. What are you going to do? You're going to go on your tippy toes. That's called plantar flexion. All right, so that's what the gastrocnemius and the soleus do on the Achilles heel. It kind of pulls it up. All right. In any case, thank you guys so very much. Did I say Achilles heel? I meant Achilles tendon. It's the calcaneus. That's the heel. Number 42. A 76 kilogram person is being pulled away from a burning building as shown in figure 4.40. Calculate the tension in the two ropes if the person is momentarily motionless. Include a free body diagram in your solution. All right. So first, just take a look at this picture on the right-hand side. So I have to take this picture and create a free body diagram out of that. So in order to do so, right, we first create an axis, or a set of axes, I should say, a y and an x. And the next thing we have to ask ourselves is where is the center, or what is the center, let's just say, of this problem going to be? All right. And I would say we'll choose this particular point right here as the center. All right, that's where all the vectors will be emanating from. So let's now turn our attention to our free body diagram over here. So we have this person being essentially pulled away from a burning building, right? And it looks like she's just hanging there and she's temporarily motionless. So her weight is just going to be pulling straight down, right? So there's the force of her weight. So we'll say W, the weight of the woman, all right? And then there are these two forces now, these two tensional forces, one pointing to the right-handed direction at an angle of 10 degrees, and then the other pointing slightly in the left-handed direction at an angle of what? Well, it's 15 degrees at the top, right? But remember, that would be the same thing as 15 degrees here, alternate interior angles, okay? So that's great. So now we have our picture, okay? So what does it mean that she's motionless? All right, what is that? What's the significance of that? Well, that means that any of the formulas I use, meaning some of the x, right, some of the force in the x direction is equal to ma, or some of the forces in the y direction is equal to may, right? There's no acceleration, so this whole thing goes to 0. So that means that the sum of both forces, both in the x and both in the y, equals 0. Okay, that's an important fact. Now, what I'd like to do is, in order for me to find the tensional forces here, right, the T and the T, probably what's a good idea is to break this problem up into their components, right? Because we know the sum, meaning the resultant forces in both directions, should be 0 because there's no acceleration. She's motionless. So why don't we first just construct a simple component table? All right, table. We have the x components, then we have the y components, and we have 3 vectors here, right? I'll call this, here's T1, and then this vector here will be T2, right? T2, and then we have the weight, right, of the woman. So we have then the weight of the woman. All right, and when we sum all of those together, remember that we just found that their sums equal the resultant vector, but they're all going to be 0 because there is no acceleration in the problem. So let's simply find the pieces of each. So first let's look at the components of T1. So T1 would have an x component here, right? This would be T1x, and then it also has a y component to it, correct? And that would just be straight up, and that would be T1y. Now remember, the x1 is negative, so that would be negative. All right. Now, just thinking. How shall we now create an equation that involves Tix and Tiy? Well, from the triangle I created, right, we would need to know this angle in here. And we can easily find that, right? We know this angle, 15 degrees, and we know that it forms a right angle there. So therefore, right, the remainder here would be 75. So that's 75 degrees, okay? So to create an equation that details the Tix, all we would need to do is this. So we would be using cosine, right? So cosine of theta is equal to the adjacent side over the hypotenuse. So cosine of 75 would be equal to negative T1x all over T1, okay? So negative T1x would equal T1 cosine of 75. Now just bring the negative sign on over, okay? So I'm just going to erase that over here. And we just bring it on over there. All right, so plug that into your component table. So for T1, I really didn't leave myself much room here, huh? That's okay. I'm just going to do a little magic, hopefully. Oh, I didn't get the plus sign in it. There we go. So just going to move this over here. And now I should have enough room. So here now, T1, it's negative, right? T1 cosine of 75. Okay, how about now for T1y? Well, we would be using sine in that case, right? So sine of theta is equal to the opposite side over the hypotenuse. So the sine of 75 will equal T1y all over T1. Okay, great. So now we have T1y is equal to T1 sine of 75. Okay, so let's take that and plug it into our y component now. So this is, and it's positive because it's pointing up. So T1 sine of 75. Great. Let's do the same thing now for T2. So the components here for T2, right? This one is going to be T2 in the x direction, and then we have T2 in the y direction right there. All right, so this is T2 in the y direction. So same thing, guys. Cosine for the x here, cosine theta, is equal to the adjacent side over the hypotenuse. Cosine now of 10 degrees will equal T2x all over T2. And just solving for T2x, because that's the x component, that's what I can plug into the table, will now be equal to T2 cosine of 10. Okay, so let's plug that in, and it's positive, right? Because it's pointing in the positive x direction. Same thing now with the T2y, right? So T2y, hold on one second. I'm sorry, I'm going to use sine here. I don't know why. A little bit of a brain freeze. Opposite over hypotenuse. So the sine of 10 will be equal to T2y all over 10. So now here we have T2y equal 10 times the sine of 10 degrees. Great, and we'll plug that into our table. So this is 10. Where did I get 10 from, guy? I have no idea where I got that from. I'm sorry. Oh boy. Hopefully I'm not confusing you more than I'm helping. All right, so this should be, sorry. That's where the mistake was. The mistake was so silly right here. This is just T2. Sorry about that. And we have T2 in here. Okay. So now let's fix that. So this is just T2 sine of 10. Okay. Wonderful. And now we have the weight of the woman. Now there is no x component to that weight, so I plug in 0 for that. And the weight of the woman, they told us she's 76 kilograms. So then we take the 76, multiply it by 9.80, right, to find the weight. I'm just following the formula over here on the right-hand side, that the weight is equal to the mass multiplied by the gravitational acceleration. So 76 times 9.8, 145. No, so I'm really dying today with this. I don't know what's going on. 745. Oh, man. And that's in newtons. All right, it's pointing straight down, therefore it's negative. Okay, so I'm going to plug that into the table, negative 745. So now I have, right, two equations here. Okay, I'm going to sum all of this to equal 0, and then sum all of this, and that equals 0. All right, let's see what we got. So where should I write it? Let me write it. I'll write it down here on the lower right-hand side. So we have T2 cosine of 10 minus T1 cosine of 75. That should equal 0, right? I can bring this term on over to the left-hand side. That might be helpful. So now then I'd have T2 cosine of 10 equals T1 cosine of 75. Okay, we'll just hold off now. Well, that's a nice equation. Now we can do the same thing for the second case, right? So I have T1 sine of 75 plus T2 sine of 10 minus 745 is all equal to 0. All right, so we got two equations. Guys, how many unknowns do we have? We have 2, right? We don't know T2 and we don't know T1. And we have 2 unknowns and 2 equations. So how do we solve that? That's a system of equations problem, right? Solve one of them. Solve, let's say, this equation for, I don't know, T1. And then plug in the resulting value into T1 in the second equation. All right, so that's what we're going to do. So let's solve this guy for T1. What that would look, I'm going to go to the upper left-hand corner. That would look like this. That would look like T2 cosine of 10 all over cosine of 75, right? That's equal to T1. Now, take this value and plug it in for T1 in your second equation, okay? So watch what we're going to do. I'm going to rewrite the second equation on top. So the second equation was T1 sine of 75, right, plus T2 sine of 10 minus 745 is equal to 0. So now just take this and plug it in for T1, okay? So all we have to do is, actually, you know what I'm going to do? Just to save a little space, I'm just going to erase that now and just plug it in right away, okay? Shouldn't be too confusing. So I'm just going to need more room. So we got here T2 cosine of 10 all over cos of 75. Okay, so let's start cleaning this up. I'm going to combine the cosine 10, 75, and sine of 75, right, just by multiplying. So cosine of 10 times sine of 75 divided by cosine of 75. So that all works out to be 3.67. So we got 3.67 T2 plus, find the number for sine of 10 now. Sine of 10 is 0.174. So 0.174 T2 minus then the minus the 745. But why don't we just add that on over right away now, just so we can save a step. So that will be equal to now positive 745. Combine your like terms here. Okay, so take the 3.67, add it to the 0.174, 3.84. So now we got 3.84 T2 is equal to 745, and then just divide out now the 384. Divide out the 384. And the T2 value now is 745 over 3.84, 194 newtons. So this is 194 newtons. That is T2. So we found one of them. Now what do we have to do? We just got to find T1, right? Because we have to find both of them. So that's easy though. Take this value now and plug it back in to this equation because you already have that thing solved for T1. Right? So now it becomes 194 times cosine of 10 all over cosine of 75. And that was equal to T1. So let's calculate it. I'm going to write it right here. T1 is equal to 194 times cosine of 10 divided by cosine of 75. 738 newtons. Oh my goodness, thank goodness, right? Now this should kind of make sense. Even if you just look at the diagram, look at T1, right? And T1's vector component is aligned better. It has more y component to it, so this T1 should be handling more of the weight than this T2 should be because that has more x component to it. So answers sound reasonable. Number 43, integrated concepts. A 35 kilogram dolphin decelerates from 12 to 7.5 meters per second in 2.3 seconds to join another dolphin in play. What average force was exerted to slow him down if he was moving horizontally? All right, so first let's depict a dolphin here. So here we have a dolphin, and looks more like an airplane. But pretend it's a dolphin. So we have a dolphin, right? It's starting with some initial velocity. It told us that it is 12.0 meters per second. It's going to slow down, and its final velocity then will be 7.50 meters per second. It also told us that the time it takes to go from the initial to the final velocity is 2.3 seconds, 2.30 seconds, right? And we know that it's going to have some deceleration, so we should be looking for a negative acceleration, okay? And they also told us the mass, right? So the mass of the dolphin is 35.0 kilograms. All right, so this assumes that the dolphin is heading or moving, let's assume it has a velocity forward, and therefore the acceleration would be a deceleration. In other words, it's a negative acceleration, and that will be pointing in the negative x direction, okay? So we should expect to get a negative value for this. All right, so in order to calculate, it asks us for force, but in order to calculate force, look on the right-hand side, guys. In order to calculate force, whichever dimension we're in, I mean, this time we're in the x, all right, we're in the x-plane, so we need to know an acceleration. So really the first thing is to first find the acceleration, right, so that I can then plug that acceleration into this equation so I can then find the force necessary, okay? So taking these four variables into account, what's the relationship between those four? Think back to your kinematics chapter. All right, we should have something that looks like this. The final velocity is equal to the initial velocity plus the acceleration times time. The final velocity is 7.50. The initial is 12.0. The acceleration is what we're looking for, and the time is 2.30 seconds. So now just do some math. So subtract 12 from both sides. I added an extra 0 there. Right, so now we get, so 7.5 minus 12, right? What do we get? Negative 4.5, negative 4.5. And that is equal to 2.30 times the acceleration. So now just divide out the 2.30, divide out the 2.30, and now my acceleration value is, and look at that, it's going to be negative 4.5 divided by 2.30, get a value of negative 1.96, negative 1.96, and that is meters per second squared. So that's the acceleration, okay? Now, and like I said, it should be negative, which it is. So that's great. So let's just plug that in up here. So negative 1.96 meters per second squared. Now here's the thing. Let's draw a force diagram, okay, a free body diagram. So in the middle, that represents the dolphin. Remember that there is an acceleration to the left-hand side, okay? So that acceleration is the same as this, right? So that acceleration was negative 1.96 meters per second squared. And if that acceleration is pointing to the left, guess where the net force is pointing? It's also pointing to the left, right? So we should expect a backwards force. That should make sense. That's what's slowing the dolphin down. There's some force pointing backwards, okay? So I'll just call this the F that I want to find. And this basically is the net force, okay? There are no other forces on the dolphin. I mean, it told us that the gravitational force is balanced by the buoyant force, okay? And we're just looking at the problem horizontally anyway. So now I really have everything I need, okay? So the sum of the forces in the x direction should equal max. So this is what I'm looking for, my F. The mass of the dolphin was 35.0 kilograms. My acceleration was negative 1.96 meters per second squared. So now my force should be negative, right? It's pointing to the left. So 35 times negative 1.96. And we get negative 68.6. So negative 68.6. And that is in newtons. Okay, so that would be the force. What does it say? Average force was exerted. So this would be the force that needs to be exerted in order to slow the dolphin down from 12 meters per second to 7.5. All right. You could probably even give the answer as a positive value. All right, just give the, not even positive value, I shouldn't say, you could just give the magnitude of it, all right, because it doesn't say, what direction, and it kind of depends, right? If I chose the dolphin to be moving to the left, then my answer would have come out to be positive, excuse me. All right, so that's probably good enough, just give the absolute value. And guys, thanks for tuning in. I really hope this helped. Please do remember to subscribe, that would be awesome. Number 44, integrated concepts. When starting a foot race, a 70-kilogram sprinter exerts an average force of 650 newtons backward on the ground for 0.8 seconds. What is his final speed? All right, let's first start with a free body diagram. So here's the diagram. The dot here will represent the runner, and let's assume that the runner will be moving and accelerating to the right. Okay, you could choose to the left, it doesn't matter. Your values, though, should be the same magnitude, but it probably will have opposite signs. In any case, so now it says he exerts an average force of 650 newtons backward on the ground. Okay, fine. So you might be tempted, remember, to draw the vector in this way, but that's not the way to draw it, assuming that I am talking about an acceleration moving to the right-hand direction. All right. So the thing is, though, that's the force, 650 newtons. That's the force exerted by the sprinter on the ground. That's not what I care about. What I care about are the forces acting on the sprinter, not by the sprinter. So if the sprinter pushes backward on the ground at a value of 650 newtons, guess what the ground does? The ground pushes back on that sprinter with the same magnitude in the opposite direction. Newton's third law. Okay? So therefore, and that's the vector I'm interested in, because that's the force that's going to be propelling him forward, right? He's pushing back on the ground, but the ground's pushing forward on him. Okay? So this is the 650 Newton force. All right, wonderful. It says that there is we don't see anything. I should label that A, right? It also it doesn't say anything about there's some drag forces, air resistance, frictional forces, nothing. So this is the only force I really know. So that's what I have to work off of. Okay. So now, why don't we try to find the acceleration? Why am I doing that? Well, look, they're asking for a final speed, right? And they're giving me a time. So I'm thinking to myself, well, where can I go from here, right? I basically just know the force, okay, and the mass. So I'm like, oh, yeah, right. If I do some of the forces in the x direction equals max, and I plug in 650 for the sum of the forces, because those are the only forces in the problem, or that is the only force in the problem. The mass of the sprinter is 70 kilograms. Look what I can do. I can solve for the acceleration. All right, so divide out the 70 from both sides. Divide out the 70 from both sides. So the acceleration then in the x direction, and look, it is positive. That's what we expected it to be, given how I framed the problem. It's 9.29. So 9.29 meters per second squared. That's the acceleration. Now that's wonderful. They tell us that this occurs for 8 seconds. Well, that has nothing to do with this part of the problem. But it has everything to do with speed, because if you're accelerating at 9.29 meters per second, well, then your velocity will depend on how long you're accelerating at that rate for. Okay? So there's the acceleration. We do know the time, so what I'll do here is I'll start changing the colors. All right, so we do know the time. That was 0.800 seconds. We do know that this sprinter started a race, right? So the initial velocity, we have to assume, is 0. Okay? And what else? We're looking for the final speed. So here's how they connect. Look what I'm going to do. I'm going to box these in. How are these variables related? What's the kinematics equation? Well, it's this. Final velocity is equal to the initial velocity plus acceleration times time. So the final velocity is what we're looking for. The initial velocity was 0. The acceleration was was 9.29 meters per second squared, and the time was 0.800. So easy enough. Easy peasy here. So 9.29 times 0.8. So this is great, 7.43. So we get 7.43, and that is meters per second. Wunderbar, right? Now what we can do, so we found the final velocity. That's his final speed. Now what's the next part? He says, how far does he travel? That's not hard at all, right? This is just all kinematics now. So now I'm going to look for time. How can I do that? Well, you can choose a couple of formulas here. I would try to shy away from one with the final velocity in it because, you know what? Maybe you calculated it wrong. And now if this is wrong, you don't want the error to propagate now into your time. Okay? But you could have calculated this wrong, right? And that'll propagate. But again, I'm lowering the probability. I have two calculations here. The probability that I get both of them wrong really depends on if I get this one wrong, right? Because this influenced now my calculation here. All right? So it really all harps on this. So I actually would go back and double check that. But I'm positive that that's the answer. So, all right. So how far does he travel? Not to lament this anymore. I don't know why I wrote time down here. That is not that we do know. So I got carried away. What we are looking for is the displacement, right, in terms of x. So now we just got to think of a formula that we need that relates to known variables. So we can choose this one, right? The change in displacement is equal to the initial velocity times time plus 1/2 of the acceleration times time squared. So the displacement will be equal to, this whole thing goes to 0 because the initial velocity is 0. So therefore it's 1/2 of the acceleration of 9.29 meters per second squared multiplied by the time of 0.800 squared. So this is easy, just plug it into the calculator. So 0.5 times 9.29 times 0.8 squared. And would you look at that? 2.97, and that is meters. And that is how far. All right? Not too bad, guys. Easy peasy. What else is easy peasy? Is hitting that subscribe button. Number 45, integrated concepts. A large rocket has a mass of 2 times 10 to the 6 kilograms at takeoff, and its engines produce a thrust of 3.5 times 10 to the 7 newtons. Letter A, find its initial acceleration if it takes off vertically. All right, so let's just work with that first. Free body diagram, x and y axes. The point in the middle here will represent the rocket ship. There are two forces acting on the rocket ship, right? If we're talking about vertical, forces, we have to realize that there is a thrust being produced, and that is propelling the rocket upward. So we have a force pointing up. That's the thrust. That's the force of thrust, and that is 3.50 times 10 to the 7 newtons. Great. Now, there is also a vertical force of gravity, right? So the weight of this rocket, okay, the weight of the rocket is equal to the mass of that rocket, which was 2 times 10 to the 6, multiplied by 9, I'll do it underneath just to save a little horizontal space, times 9.80, right, because that's the gravitational acceleration. So what do we get here? 2 times 10 to the 6 times 9.8. So we get a value of that the weight is equal to 1.96 times 10 raised to, is that the 7th? 3? Yes, 7. And again, that's in newtons, all right? I'm just leaving out the units. And let me just fix that because I cut off the 7. Okay, now these are the forces. That's it. So all we now need to do, we can use these forces to help us figure out the acceleration, right? We already can see that the force upward is greater than the force downward, so there should be a net acceleration up. So we should expect our answer to be positive, right? So let's detail it. So the sum of the forces in the y direction is equal to the mass times the acceleration in the y. So the sum of the forces, so we have a positive because it's pointing up, 3.50 times 10 to the 7th, minus then, because it's pointing down, 1.96 times 10 to the 7th, and that should equal the mass of the rocket, which is 2.00 times 10 to the 6th multiplied by the acceleration. So easy to solve this, right? Just divide out the 2.00 times 10 to the 6th, right, from both sides. Divide out the 2.00 times 10 to the 6th. Whoa. Times 10 to the 6th. Okay, so my acceleration here will be 3.5 times 10 to the 7th minus 1.96 times 10 to the 7th. And that will be divided by 2 times 10 to the 6th. So we get a value of 7.7. So 7.7 and probably 3 sig figs, so that's 0 meters per second squared. That's the acceleration. All right, great. So that takes care of letter A. Let's take a look at letter B. So how long does it take to reach a velocity of 120 kilometers per hour? If assuming constant mass and thrust. So first thing is, I hate that the units are in kilometers per hour. So I'm just going to convert them into meters per second right away because that's my acceleration value. All right, so we'll do that down here. So 120 kilometers per 1 hour. Get rid of the kilometers, they go on the bottom, meters on the top. There's 1,000 meters in 1 kilometer. Great, so they're gone. I want to get rid of hours. Now, since they start in the denominator, I need to put them in the numerator. And I know the relationship between hours and minutes, namely that there are 60 minutes in 1 hour. Okay, so that would mean the hours cancel. And now I got to get rid of minutes, so I got to do the same thing. Minutes in the numerator and seconds in the denominator. There's 60 seconds in a minute. Great, so I did that. Okay, so now take 120 times 1,000. 120 times 1,000. And then divide it by essentially 3,600. So it's 33.3. So 33.3 meters per second. That is the final velocity, right? And that's, so now what we have to do, that's the final velocity, right? The initial velocity, it's starting from rest, so that's 0. Okay, let me just make that a little neater. That's 0. They're asking us for the time, right? It says how long does it take, right? So we're looking for the time. Okay, so the t is unknown here. And we do know, though, the acceleration. So what we got to do is we got to think, what's the kinematic formula that relates these three things, right? It's simple. It's this one. Final velocity is equal to the initial velocity plus the acceleration times time. So the final velocity, we calculated it to be 33.3 after our conversion. The initial was 0. The acceleration is 7.70 meters per second. And the time now is going to be found in seconds. So simply divide out this side by 7.70 and this side also by 7.70. So time will be 33.3 divided by 7.7. So we get a value of 4.33, right? So we get 4.33 seconds. Okay, that is the time that it takes to reach the final velocity here of, what was it? You want to do physics? Okay, buddy. Hold on one second. I'm almost done with the problem. So, all right, so that's the time. That's how long it would take, right? And then letter C, it just says, really quick, guys, it just says what would happen if the, right, how the mass would decrease and whatnot because the fuel is consumed. So obviously less mass, same amount of thrust. We would actually have a higher acceleration. Number 46, integrated concepts. A basketball player jumps straight up for a ball. To do this, he lowers his body 0.3 meters and then accelerates through this distance by forcefully straightening his legs. This player leaves the floor with a vertical velocity sufficient to carry him 0.9 meters above the floor. Letter A. Calculate his velocity when he leaves the floor. All right, so let's just create a simple picture here. Here we have our basketball player. All right, let's call him Hakeem Olajuwon. There we go. That sounds good. And he leaves the floor, right, with a certain initial velocity that we don't know what it is, and that's what we're asked to find. Okay, so that's a question mark. It does, though, tell us how high he jumps. Right? So he jumps, it tells us 0.9 meters. So that's his change in displacement, 0.900 meters. And when he reaches the top of his motion up here, what do we know about the velocity? Remember, anytime any object reaches its highest point in the y direction, the velocity in that y direction is 0. So in terms of the frame of my problem, the final velocity here in the y direction will be equal to 0. All right, we'll call it meters per second. Great. Now, remember, Mr. Olajuwon is in free fall once he leaves the floor. So what else do we know about free fall? Maybe some forces acting on it or some accelerations, right? Remember, the acceleration due to gravity is acting on Mr. Olajuwon, and that is negative 9.80 meters per second squared, the acceleration due to gravity. So now let's take a step back and see, do we know an equation that relates these four variables together, in which case we can solve for the initial? Yes, right? If you recall, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by that displacement. So here is 0 squared, right? The initial velocity is what we're looking for. That's our variable. 2 times the acceleration due to gravity, 9.80, and our y displacement is positive 0.900. So I just have 0 is equal to initial velocity squared. Now minus, let's just do the math. So we get, let's see, 2 times 9.8, it's negative though, times 0.9. So we get negative 17.6. 17.6, add this on over. Add this on over, 17.6. And now we have 17.6 is equal to the initial velocity squared. And to get just the initial velocity, we have to square root both sides, right, to get rid of the square. And remember, anytime you take a square root of a number, you're always going to positive and negative answer. So second square root of 17.6. And we get 1.4, well, 1.2, what am I talking about? 4.20. Okay, that's in meters per second. And which answer would we accept, positive or negative? If you said negative, you would be, unfortunately, incorrect. Right? It would be positive. Why? Because look at the direction of his motion. Right? He is going upward here, positive y. Okay, so that's the initial velocity. That's the velocity he leaves the floor with. So that's simple. This was letter A. Okay, let's jump back now to see letter B. Calculate his acceleration while he is straightening his legs. So now, in terms of that picture, right, let me draw that out quickly. So basically what's going to happen, let me just represent it as a point now. Okay, it tells us in the beginning of the problem to accelerate himself. He lowers his body 0.3 meters and then accelerates through this distance by forcefully straightening his legs. So we can assume that Mr. Olajuwon will start at this particular point where his initial velocity at this point is 0 meters per second. He's then going to accelerate some value by straightening his legs. Okay, the distance that he straightens his legs by, they told us here, was going to be 0.3 meters. So now that's my new change in displacement value, so 0.300 meters. All right. We also know now once he leaves the floor, right here at the point at which he takes off, his velocity, right, which we would consider final for this part of the problem, would be 4.20 meters per second squared. Now, what am I talking about? Not squared, just meters per second. That's just what we found over here on the right-hand side or in the center of the page. And what else do we know here? We don't know really, I mean, as far as the acceleration due to gravity, is he in free fall? No, he's not in free fall yet, right? He's bending his legs and he's straightening them, so he's not in the air yet. So therefore, we actually don't know the acceleration he is experiencing. And guess what the question is asking us? It's asking us to find that acceleration. Okay? Do we know anything else about this problem? Not really. Right? So what we need to now do is think about a formula that relates these four variables. And again, it's going to be the same equation, right, that we used for letter A. So let me write now for letter B, same equation. The final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by the displacement. So the final velocity is 4.20. That'll be squared. The initial 0, so that's easy, plus 2 times the acceleration, which is what I'm looking for, multiplied by the displacement of 0.300. All right, so let's just clean this up now. So let's do 4.2 squared. And we get 17.6, right? Same value as before. 17.6 is equal to 2a times 0.3, which would be 0.600a. So then just divide it by 0.600 from both sides. And a now is simply the acceleration here is now 17.6 divided by 0.6. And we get a value of 29.3. So 29.3 meters per second squared. Okay, so that's the acceleration. So that takes care of part B. Now let's see, what does it ask us to do for part C? Okay, so it says calculate the force he exerts on the floor to do this, given that his mass is 110 kilograms. So now for letter C, let's do it over here. I'll start it at the bottom. Oops. I'll start it at the bottom. So here's letter C. Okay, let's start by drawing a free body diagram. All right, so there it is. So free body diagram here. So when we're thinking about the forces acting on Mr. Elijah as he is beginning his jump, right, we have to consider two things, right? Since he's moving in the y direction, in terms of forces, there's a gravitational force on Hakeem, right? And that is pointing down. So the weight is a force, right? And remember, weight is equal to mg. I have the formula over here on the right-hand side. So what's his mass? It tells us 110 kilograms, and that's always multiplied by g of the acceleration due to gravity, right? 9.80. So the weight here, let's find the value. So 110 times 9.8. And we need 3 sig figs, so let's do 1,080. Okay, because I got a round there, no decimal. So that would be the weight, his weight in newtons, 1,080. All right. Now we are looking for the force that he exerts on the floor. So you might be tempted to draw the vector down because we're looking for that, force. But remember, that's a force Mr. Elijah is imparting to the floor. But what we're concerned about is what force the floor is imparting to him, right? We're concerned about the forces on Hakeem, not by Hakeem. So therefore, it's going to be pointing straight up here. This is the force the floor exerts on Hakeem, which is equal but opposite to the force that he exerts on the floor, according to Newton's third law. So this is the unknown. All right. So now let's see. I think we have everything we need. Also remember, his acceleration that we just found in the prior part is telling us what direction and where the net force should be. And it's pointing up, right? Because we found it to be positive, and it was positive 29.3. All right. So I'll just write it here that his acceleration is equal to 29.3 meters per second squared. And now we have everything we need, right? So let's use the y, sum of the forces formula. So sum of the forces in the y direction is equal to the mass of the object in question multiplied by the acceleration of that object in that axis. So here we have the sum of the forces. So we have the F unknown force, which is positive, minus the weight, which is negative because it's pointing down, is equal to the mass of Mr. Elijah, which was 110 kilograms, multiplied by the acceleration, which we found in the prior part, so 29.3. So this is fairly straightforward, right? To find F, right? Just add the 1,080 to both sides. That cancels, leaving us with the force being equal to 110 times 29.7. 29, no. Can't read my own handwriting. That's a 3 there, ladies and gentlemen. I wouldn't have even known it myself. So 110 times 29.3, and then add that to 1,080. So it looks like we get a value of 4,300. And that would be in terms of newtons. So that would be the force that the Earth, according to my diagram, that the ground exerts on Hakeem, but then, right, that would be equal but opposite to the force he imparts to the floor, so therefore the answer to the question would be exactly the same, 4,300 newtons. Guys, thank you for tuning in. Really appreciate it. Hope this problem helped. Again, this is a good problem to do because it's now integrating, as it says in the question, it's integrating a bunch of concepts together. Number 47, integrated concepts. A 2.5 kilogram firework shell is fired straight up from a mortar and reaches a height of 110 meters. Letter A, neglecting air resistance, a poor assumption, but we will make it for this example. Calculate the shell's velocity when it leaves the mortar. All right, so let's first focus on that part. So let's say that this dot will represent the firework, and it's fired straight up, right? Okay, wonderful. And it's going to reach an overall height, it tells us, of 110 meters. So let's just say it reaches this overall height here, and the change in its height would be delta y of 110 meters. Okay. It leaves the mortar, it tells us, with some initial velocity. Right? We don't know what it is. That's what we're looking to find. That's the question. All right. What happens now? That's fine. What happens when it reaches its highest point up here? It's going to go up, 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 and then it's going to come back down, right? So what happens when it reaches the highest point here? What's its velocity in the y direction? It's 0, right? So here we go. Oh, the ice cream man is here. Oh. Do you mind holding on, guys? No, I'm kidding. All right. So the final velocity here in the y direction will be equal to 0. Remember that whenever an object reaches its highest point in the y direction, the velocity in that y direction will always be 0. Okay, so that's always something you have to remember. It's not going to be given, but you just got to think about the physics of the problem. Another thing is also, something else isn't given here, but it's assumed that you have to know it. This is essentially a free fall problem, meaning that the object is freely suspended in the air. And guess what force is pulling on that object? Gravity, right? So therefore, this firework is experiencing an acceleration due to gravity, all right, of negative 9.8 meters per second. So that's also something else that we will know that isn't given, but you have to consider the physics. So here's the question. If I want to find the initial velocity, and I know these three things, what formula do I choose? All right, I didn't put them on the side because I need you guys to start remembering this. So it would be this one, right? The final velocity squared is equal to the initial velocity squared plus 2 multiplied by the acceleration times the displacement in the y. All right, so what's the final velocity in the y direction? Right, these are all sub y's. That's 0. Easy. The initial velocity in the y direction squared. I don't know what it is, so that's my unknown. Plus 2 times the acceleration of negative 9.80 multiplied by the height, 110. Right? So this is just 0 is equal to the initial velocity in the y squared minus, now just calculate it. So it'd be 2 times 9.8 times 110. I know I didn't say the negative, but I didn't forget it. I already put it in there. So this is going to be 2,160. Considering sig figs. So add the 2160 on over to the left-hand side, 2160. That cancels, so then it's 2160 is equal to the initial velocity in the y direction squared. To get rid of the square, we got to take the square root, so just plug that into the calculator, and then we get initial velocity in the y direction is equal to, remember, when you take the square root, you get a plus and a minus. Okay. Okay, so second square root of 2160. So we get a value of 46.5. 46.5 meters per second. Now, which value is it? Positive or negative? Consider the motion. Where is it pointing? It's pointing up, right? Therefore, it has to be positive. So that is the initial velocity in the y direction. That's the velocity that the firework is leaving the mortar with. Okay? So that takes care of that. Letter B. The mortar itself is a tube, 0.45 meters long. Calculate the average acceleration of the shell in the tube as it goes from 0 to the velocity found in part A. All right, so to detail now a little picture for that, let me just call this A, and now we'll work on B. We'll do B over here. So what do we got? Okay, so let's say here's where the firework starts, right? It's in this mortar-looking thing. I don't even know what that is, but I'm assuming this is what it is. The height or the length of the mortar they told us is 0.45, right? So this is essentially a delta y, 0.450 meters. What else do we have here? We know the initial velocity, right, of the object. At this particular location, they told us is 0. So I'll call that 0, right? What else do we know? We do know the final velocity, right? Once it's going to be accelerated out of the tube here. Okay, and once it reaches the end of the mortar, it then leaves the tube with the velocity we found here in part A, it told us. So that's really, for the frame of this problem, that's actually the final velocity now, right? So remember, these are just relative terms. So the initial of the first frame is now the final of the second. That's no problem. They're all relative frames. So 46.5 meters per second. And what we're doing is we're looking for the acceleration, right? That's what we're trying to calculate. So what's the acceleration when it travels this distance and it goes from 0 to 46.5 meters per second? How do we find it? Well, guess what? Same equation as letter A, right? So let me do that over here. So letter B is... So the final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration in that y multiplied by the displacement in the y direction. So the final velocity was 46.5, right? That's squared. All right, that'll equal the initial, which was 0, 2 times the acceleration, which is what we are looking for, and the change in the displacement in the y direction was 0.450 meters. All right, so let's just... plug it in. So when we square 46.5, considering significant figures, it should be 2160. All right, this is 0. And now this will be plus 2 times 0.45. So that should be 0.900A. And now just divide out this side by 0.900, right? 0.900. So letter A. Oh, the ice cream man is back, ladies and gentlemen. He's really tempting me. I could go for an ice cream right now. Anyway. 2,400 it's going to be, wow, that's crazy, meters per second squared. Okay, so that's the acceleration. All right, so that was letter B, and now let's take a look at letter C. So what is the average force? What is the average force in the shell of the mortar? Okay, so when we think about this, when we consider the forces acting on the object, what we have to do, first, let's draw a free body diagram. So where am I going to do that? Let's do C on down here. I'll draw the picture for C over here. All right, and let's do it right down here. All right, so when we're talking about the forces acting on the shell, okay, there's going to be 2 forces, right? So I'm really talking about it at this particular point right there. All right, follow me on the bottom left, guys. Right here, I'm talking about it at this point right there. All right, there is a force due to gravity. There's always a force due to gravity, right? Assuming you're on Earth somewhere, not out in space or whatnot. So there's a force due to gravity. Okay, so how is that represented? Well, it's a force that acts straight down on an object. Okay, and what is that? That's the weight. That's known as the weight of the object. What's the formula for weight? Right-hand side, guys. Weight is equal to mg. So what's the mass of this firework? Well, it told us 2.50 kilograms, right? That's up at the top here. And that's multiplied by g, which is 9.80. So I can find the weight, right? Simply just plug this in now. 2.5 times 9.8 and 24.5. So we get 24.5, and that is in newtons. Okay, good. Remember, it's pointing down. Now, there's going to be some net force pointing up, right? How do I know that? Well, the firework is being shot up. So there has to be some force pointing up to propel it upwards. I also know, based on the physics of the problem, that there is a net acceleration in the positive y direction. What is that? Well, that's what we just found over here. That's the 24,000, right? So acceleration here is going to be, not 24,000, excuse me, 2,400 meters per second squared. Okay, so now, do we have everything we need? Yeah, we do, right? We can now do the sum of the forces in the y formula, okay? So let me do that over here. Sum of the forces in the y is equal to the mass of the object that's accelerating multiplied by its acceleration in the y. So I have a positive F minus the weight, because it's pointing down here, minus 24.5 is equal to the mass of the firework of 2.50 kilograms, multiplied by its acceleration of 2,400. Okay, so all I have to simply do is add the 24.5 on over 24.5, and I got my answer. Right, so the force is equal to here 2.5 times 2400 plus 24.5. And what do we get here? So we're going to get, let's do 3 significant figures. So it looks like it's going to be something like 6.02 times 10 raised to the third times 10 raised to the third newtons. And that would be the force. All right, let me just make, what is the average force on the shell? Just make sure I calculate that right. What is the average force on the shell? Yeah, that makes sense. Number 48, integrated concepts. Repeat exercise 4.47 for a shell fired at an angle 10 degrees from the vertical. So number 47 is over here on the right-hand side. So I just, in the prior video, you can check that out, all right? That analyzed the problem fully. So I'm just going to read it quickly. I already set up a diagram, all right? So 2.5 kilogram firework shell is fired, not straight up anymore, right? So let me actually change the color. This is not straight up anymore. This is going to be at a 10-degree angle from vertical, okay? And it still reaches the same height, so it's still going to reach a height of 110 meters. So letter A, neglecting air resistance, blah, 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 calculate the shell's velocity when it leaves the mortar. So here's the picture over here on the left-hand side, guys. All right. Here's the angle at which the shell is being fired. It's 10 degrees from the vertical. The velocity here is what we're looking to find. So this is basically like a resultant velocity. I'll call that the initial. Okay. And so that's great. The height of which the firework reaches, it's still 110 meters from the ground. And when it reaches its highest point, what do we know about the velocity at that point? Remember, whenever it reaches its highest point, the velocity in the y direction, all right, would be 0. In terms of my frame, it's going to be the final velocity here. So that's 0 meters per second squared. Why do I keep doing that? But it's meters per second. Acceleration is meters per second squared. And speaking about acceleration, it's a free fall problem, basically, right at this point. So therefore, I know the acceleration is the acceleration due to gravity. So that's negative 9.80 meters per second squared. Okay. So it looks like I have enough information. Also remember that this value right there that I circled is equal to the displacement, right? Change in y. So I need a formula that relates all 4 of those variables and allows me to solve for my initial, right? Now, the only thing though, am I actually solving for the initial here, meaning the resultant? No, right? I would be solving because all of these values are in the y dimension, right? I would be solving for the y component of this vector. All right, so that's actually really important. So this vector that I just drew, and this is the VIY, and that's actually what we're looking to solve for. Why? Because that is all these given values are pure y components. The height is pure y, the acceleration is pure y, the final velocity is pure y. So therefore we find pure y initial. So the formula that we need in order to solve this is going to be one of the equations from kinematics, right? The final velocity in the y direction squared is equal to the initial velocity in the y direction squared plus 2 times the acceleration in the y direction multiplied by the displacement in the y direction. So final velocity we said was 0, right? So that's squared. The initial velocity in the y direction, that's what we're looking for. The acceleration is 2. It's 2 times the acceleration of negative 9.80. I don't know what I'm thinking about today. Times the change in displacement of 110. So simply just plug this into the calculator. And let's clean this up. So it's going to be 2 right, times 9.8 times 110. Remember, it's negative, so I put in the negative sign already. So it becomes 2160 when I consider significant figures. Add that on over to the left-hand side, 2160. That cancels. So now I'm left with 2160 is equal to the initial velocity in the y direction squared. Take the square root of both sides. Remember, when you take the square root, you always get the positive and negative answer. So second square root of 2160. And we get 46.5. So 46.5 meters per second. What value is it? Positive or negative? Consider the direction. It's up, right? So therefore it's just the positive one. Okay? So that would be the initial velocity in the y direction. So we just found that piece. Now here's the thing. They don't want to know the initial velocity in the y direction. They just want to know the initial overall velocity. So how do we do that now? Well, we basically have a triangle here, right? If I just close this triangle up over here, right, then we have a nice right angle here, and now we can use all kinds of trigonometric functions, sine, cosine, tangent, all that stuff. All right. So basically, what do we know? We know an angle, right? We also now know the side adjacent to that angle, and we're looking for the hypotenuse of the triangle. So it sounds like I'm going to use cosine here. Right, so cosine of theta is equal to the adjacent side over the hypotenuse. Cosine of 10 degrees will be equal to the adjacent value, which was the initial velocity in the y, which is just what we found over here, so 46.5, all over the hypotenuse, which is the initial velocity that we're looking for. So to solve, just simply switch those two variables, so the initial velocity is equal to 46.5 all over cosine of 10. And then easy peasy, now just plug it into your calculator. So 46.5 divided by cosine of 10, 47.2. Okay, great. So I get a value of 47.2 meters per second. So that is the initial overall resultant velocity. Okay. So that answers finally now letter A. All right. So that takes care of letter A. Now, why don't we move on to letter B? So now it says the mortar itself is a 2.45 meters long. Calculate the average acceleration in the shell when it goes from 0 velocity to the velocity we just found of 47.2. So I'm going to draw a quick picture here. All right, so let's label this as part B. And now let's say we have, I don't know if this is going to work. Yeah, there we go. So now the mortar is angled. Here's the firework in the mortar. Okay, it's going to be accelerated in that direction. All right, once it reaches the end of the mortar here, its velocity, which would be now considered a final velocity, would be 47.2 meters per second. The reason why it's final is because it's just relative, right? All my calculations for part A over here were dealing with the velocity when it just is released from the mortar. So I framed it as that's the initial point of my prior part, and now it's just the final part here. Doesn't matter, it's all relative. The initial value here will be 0. All right, the acceleration is what we are looking for. And they tell us the displacement of this tube, it's going to be 0.450 meters. Great, so it sounds like we have everything we need, right? Now you might be asking, well, wait a minute, do I have to take the angle into account and whatever the case is? And not exactly here, right? The reason being is because everything is lined up on this particular plane. I know the velocity in this particular direction. I know the initial velocity in that same direction. I know the displacement in that direction, and therefore my acceleration will be in this direction. Okay, so I don't have to do anything with x's and y's here. I can simply solve. So let me do that. So same formula, right? If I think about how do I relate those four variables together, the final velocity squared is equal to the initial velocity squared plus 2 times the acceleration multiplied by that displacement. So the final velocity now is 47.2, that's squared. The initial was 0, so that's easy, plus 2 times the acceleration, which I'm trying to find, times the displacement of 0.450. All right, so when I square 47.2, right, we just get the same value we did in the prior part, so 2160. That's equal to 0, right, plus 0.900a. How do I solve this? Just divide out, and I ran out of space, but just divide the 0.9, not the a, divide the 0.9 from both sides. All right, so I'll just write the answer over here. So a will be equal to, what you plug into your calculator is 2160 divided by 0.9. And we get a value of 2400, right? 2400 meters per second squared. That's the acceleration. Cool. So that takes care of part B. All right, so far it looks like part A, the initial velocity did the initial velocity. Oh, did I make a mistake? Yes. I made a mistake here, guys. I am so sorry. I see that because I'm looking at it. I'm like, wait a minute, the acceleration stayed the same as the prior problem. It shouldn't have. What did I mess up? This, right? Well, let me highlight what I'm erasing right here. This is what I screwed up. I just erased the 2. The 2 was there. Okay, I screwed up. I looked back over here, and that was a stupid mistake. See, that's what happens when you sometimes go a little too quickly and you don't plug it in. I should have plugged it in. 47.2 squared we get a value of, considering significant figures, it'd be 2,230. Okay, so let me write that in. So 2,230. So now this has to be erased. Sorry about that. For those who caught me, good job. For those who didn't, don't worry. I almost didn't even catch it. So now we take 2230 divided by 0.9. So we get a value here of A is equal to, so I now get 2,480 meters per second squared. So that makes sense now. It should be a little larger than it was before. And that's the thing, right? We all make mistakes, but what I'm trying to do, and I still may make some, they might get past me, but what I try to do is I try to think, is everything reasonable given what I've been doing and whatnot? And whenever something doesn't make sense, I go back and see if I made a mistake. All right, so always keep that in the back of your mind. Make sure the calculations make sense. Make sure the answers are reasonable, related to stuff you might have already calculated. And if you do so, that'll be the difference between, getting, let's say, 100 or a 90, 8 versus maybe a 92, something like that. Or it might be the difference between passing and failing, right, which is even more serious. So in any case, just always keep that in mind. Now, we finished part B. Let's move on to now part C. Okay. So back to reading. So what is the average force on the shell in the mortar? All right. So first thing when we're dealing with forces, we want to create a free body diagram, right? So let's do letter C up here. So let's draw our free body diagram. Now, here's the thing. Actually, first let me just draw the picture again. All right. Before we draw the free body, does it really? Yeah. Let me draw the figure again. Okay. So this is where it is going to matter the angle again. So here's the firework. It's being shot up at this angle, right? Now, if I were to think about this, if I were to draw a coordinate system, right? I would draw a coordinate system like this. Down, oops, whoa, what happened there? Down, and then across, right? All right, so here is my coordinate system, all right? What I'm going to do though, and this is fine, but what I'm going to do with my coordinate system here is I'm going to look to line up the direction of the net force here that's applied to the mortar in the y-axis up here. All right, so just watch what I'm going to do. So let me just take this. I think I can do this. Hold on one second. So resize. Watch what I'm going to do with this axis. I'm going to rotate it. Okay, I'm going to rotate it just like this. And then I'm going to just move it slightly so it's centered. Okay, so all I did was I rotated the axis. Now, how many degrees did I rotate it? I started here, right? And I just rotated it this way. How many degrees? 10, right? Why 10? It might look like more than 10. My drawing's not to scale, but why 10? Well, because that's what it said, that it's fired 10 degrees from the vertical. All right? So this is now my axis. Okay, so what I'm going to do here, watch, I'm just going to drag this down now so I can draw nicely on it. Okay? So if we think about this now, we have a net force, right? The mortar itself applying the force to the firework in this direction. That arrow is the same. Let me make it a little straighter. Okay, one more time, Andrew. There. Oh, I was so excited. That's good enough. So we have a net force pointing in that direction, correct? Let's call that F. I don't know what it is. That's actually what they're asking us to find. Now, here's the thing. Remember that this firework, I centered the axis right here. Okay? Now consider, what's the other forces acting on this firework right here? Gravity, right? And where does gravity always point? It always points straight down. So here it's pointing straight down, right? So therefore, it's also pointing straight down here. Does that make sense? All right, so this is the weight of the object. It's literally pointing straight down, okay? So what is the value of this? Well, it's the simple weight formula, right? Is equal to the mass times gravity. So this W in red here is represented by 2.50 kilograms, because that's the weight of the firework, multiplied by 9.80. Okay, so just simply plug that into the calculator. So now we have 2.5 times 9.8. So we get 24.5. So that's the weight, 24.5. Great, and that's in newtons. But hold on. So we're good there. But can I now start plugging stuff in? Not exactly, right? Why? Because I know my acceleration is in this same direction as the net force. So the problem here, and the acceleration is what we just found down here. Let me just plug that in. So the acceleration there is going to be 2,480 newtons. Okay. So the problem here is that this vector, I don't have any part of that. I mean, there is part of it, but I haven't detailed it. I haven't detailed the pure y component of that vector. Right? I have to be consistent. Like if you look at these formulas up here, they have x and y components to them. Okay? And this vector of the weight is in both the x and the negative y plane. So I need to just get the negative y component to it because I have to find the force that directly opposes the net force or the applied force and the acceleration. All right? So I have to find this component. I'm going to put it in, let me do it in black. All right? So I have to find this. Right? This is now the negative, what do I want to call it? The y component of the weight, right? And if you notice, this thing makes a nice little triangle here, right? Here's the right angle, right in there, okay? And now, what do you think this angle is? Right here, guys. What's this angle right in here? What do you think? Remember how much I rotated my plane by, meaning my axes. How much did I rotate them before? I rotate them 10 degrees, right? So guess what this is? It looks like it should be the same, right? That is. It's 10 degrees. Okay? That's the angle in there. So now here's the thing. Remember, the hypotenuse value right here, I know I just found it to be 24.5. I know the angle, and I'm looking for this side, which is adjacent to that angle. Therefore, how can I find it? Cosine, right? So let's do a little cos. Cos. So cosine of theta is equal to adjacent over hypotenuse. So cosine of 10 is going to be equal to the negative weight in the y direction divided by the hypotenuse, which we found to be 24.5. So the negative weight in the y direction will be equal to, simply do cosine of 10 times 24.5. So we get 24.1. So this is 24.1, and that's newtons. Now I'd have to divide by the 1, but just bring the negative, divide by negative 1, but just bring the negative sign on over, okay? So I'm just going to erase it from here and plug it in right there. Because it should be negative. It's pointing down, right in the negative y-axis. Now we have everything we need to solve the problem. Now, finally, I can use this sum of the force in the y direction is equal to mass times the acceleration in the y. Because I have all the y forces now. All right? So here we go. Sum of the forces in the y direction, should equal the mass of the object that's accelerating multiplied by the acceleration in that same direction. So sum of the forces, I have a positive F force that I don't know. I have a negative then, right? This force right here, 24.1 is equal to the mass of the firework, which was 2.50, multiplied by its acceleration, which we found in the prior part of the problem. So this was 2,480. And here we go, right? Just add the 24.1 on over, 24.1. And now all we have to do is just do a little math. So 2.5 times 2,480, then plus 24.1. So we get 6,000, lo and behold, 6,220. Okay, 6,220 newtons, or 6.22 times 10 to the third. Doesn't matter. But that is, ladies and gentlemen, the average force on the shell in the mortar. Number 49, integrated concepts. An elevator filled with passengers has a mass of 1,700 kilograms. Letter A. The elevator accelerates upward from rest at a rate of 1.2 meters per second squared for 1.5 seconds. Calculate the tension in the cable supporting the elevator. All right, so let's just stop there and let's take a look at that question. So here is letter A. Let's just draw a little picture. So here's the elevator, right? It weighs 1,700 kilograms, and it is accelerating upward, right? So we have a net acceleration pointing up. And what was its value? It told us that the acceleration here was 1.20 meters per second squared. All right. Now there's two things acting on this elevator. right? There's the weight of the elevator, which is influenced by the mass. Okay, where does that force point? It always points down, right? Towards the ground or towards the earth. Okay, so the weight of this elevator is equal to the mass multiplied by the gravitational acceleration. So the weight is equal to 1700 here. I'll just calculate it right now. 1700 times 9.80. So the weight here will be equal to, plug it into the calculator, 1700 times 9.8. So we get 1.67 times 10 to the, it looks like 4, right? Yes, and that's in newtons. All right, great. So that's the weight. And we have now a tension, right? There's a cable here, right? Cable all the way up. And there's a tension that's in the cable, right? Because something's got to be pulling the elevator up. If it's accelerating upwards and there's a weight pointing down, well, there's something missing up here, right? Something's got to be pulling it up. There has to be an applied force upward. So that is the tension, okay? Or you could say force applied. It really doesn't matter. But right now, this is a full detailed picture. So from here now, I can use my sum of the forces in the y direction. Remember, anytime you have a problem in the y direction and you're talking about forces, don't forget the force of gravity, meaning in terms of the weight. All right, don't forget the weight. So now we have sum of the forces in the y direction is equal to the mass times the acceleration in the y direction. So now the sum of the forces in the y, we have a positive tension minus the weight of the object, which was 1.67 times 10 to the fourth, is equal to the mass, which was 1700, multiplied by its acceleration in that particular direction, which was 1.2. Okay? So simply just add this on over, 67 times 10 to the fourth, and that should make sense, right? We're adding the weight since it is accelerating upward, right? So this value will be positive, and then we're adding now the weight. So we get so it should make intuitive sense here. So now the tension will be equal to, simply do 1700 times 1.2, and then add 1.67 times 10 to the fourth. And we get a value of 1.87 times 10 to the fourth. Right? And did I? Yes, 3/4. And that's in terms of newtons. So that is the tension. That's letter A. All right? Let's move on to letter B. The elevator continues upward at a constant velocity for 8.5 seconds. What is the tension in the cable during this time? All right, so let's draw another picture for letter B. All right. So now here, okay. So let me do letter B. Here's now the elevator. Its mass hasn't changed, right? It's still 1,700 kilograms. And the weight of this elevator hasn't changed, correct? It's still the same value that we found prior, 1.67 times 10 to the fourth. And it doesn't change direction, right? If you're moving up or down, your weight is still the same. Gravity's still pulling, assuming your height didn't change that much, right? I mean, even if it changed by a little bit, it still changes, but we're assuming that it stays constant here. Okay, great. Now, what is the acceleration? Because that's what's important in terms of force. It says that it continues upward here at a constant velocity. Constant velocity implies what acceleration? It implies zero acceleration. Okay, that's fine. Now again, the elevator, it's still traveling upwards though. There is no acceleration upwards, but it is still traveling upwards, and it's still on a cable, right? So if I didn't put any force up here, what that means is that it should be traveling down, right? But we know it's not traveling down for two reasons. I mean, it's telling us it's moving upwards, and there is zero acceleration. So there has to be a balancing force up there, okay? Let's call that T. So we have everything we need now, right? Sum of the forces in the y direction should equal the mass of the object times the acceleration in the y. So I have a positive tension minus my weight, 1.67. Well, I hope I don't weigh that much, Jesus. 1.67 times 10 to the fourth. I meant the elevator's weight, not my weight. Of course, I'm much skinnier than that. Multiplied, probably not, but anyway. Multiplied by the mass, right, which was 1,700, and the acceleration, remember, was 0. So this whole side just goes to 0, so that's equal to 0. And now I think you can see how this connects. 1.67 times 10 to the fourth. Add it to both sides. Times 10 to the fourth. Right? That cancels. So T is going to be equal to 1.67 times 10 to the fourth newtons. Notice how it's lower than this problem, than the part prior. It should make sense. It's not accelerating anymore, right? If you're accelerating the elevator upwards, you're pulling harder, right? Or the rope is pulling harder, or the cable is pulling harder in this case. All right, so that takes care of that. Let's move on to letter C. So the elevator decelerates at a rate of 0.6 meters per second squared for 3 seconds. What is the tension in the cable during the deceleration? So again, another picture. So let's go to here. So this is letter C. Same thing, draw the elevator. Okay, we got 1,700 kilograms in here. Did the weight change? No, right? The weight is still the same. It's still pointing down. So let's just write that in. So I got the weight here is equal to 1.67 times 10 to the 4th newtons. Okay. There is a deceleration. So what does that mean? It means it's negative, right? And if it's a deceleration, and if it was traveling upward before, it might still be traveling upward, right? But the acceleration is in the opposite direction now because it's decelerating. So if this is moving upward, and there is a deceleration, that tells you that there is an acceleration down. All right, so here I'm going to draw on the side, I'm just going to draw an arrow down. And this represents now the acceleration. It's not a force, it's an acceleration, okay? So the value here of this acceleration, they told us, was going to be 0.600 meters per second squared. All right. Now, I don't necessarily have to put a negative sign in here right now because I'm giving the direction, but when I plug it into my formulas, I will have to give the mathematical direction of 0. Okay. And now, last but not least, there is this elevator still connected to a cable. I don't think it's in free fall, meaning that there is still some applied force on upward and some tension in the cable. So I'm going to label that as my unknown, T. Again, I have everything now that I need so I can finally solve, right? So sum of the forces in the y direction should equal the mass of the object times the acceleration in the y. Careful with your signs here. Positive tension minus the negative weight because it's pointing down, 1.67 times 10 to the 4th, equals the mass of the object, which is 1,700. That hasn't changed, multiplied by the acceleration, which is now negative 0.600. Okay, that's the mathematical direction, negative. That's important. You don't put that in, it's wrong. So now add 1.67 times 10 to the 4th. And now add 1.67 times 10 to the 4th. Now notice this value in the numerator, this value here is going to be negative, and now I'm adding a value to it, so essentially I'm doing a subtraction. Whereas in the part prior, we were doing a pure addition here. Okay, so it should start to make sense. If it's decelerating downward, right, or if it's just decelerating, there should be less tension in the cable. So the math is working out appropriately. So 1,700 times negative 0.6, all right, then add to that 1.67 times 10 to the 4th. And we get a value of 1.57 times 10 to the 4th newtons. And look, this answer does make sense compared to all the two other answers, right? When it was accelerating upward, the tension was the greatest. When there was no acceleration, the tension was the second greatest. And then when there was a deceleration downward, the tension in the cable was the least. Should make intuitive sense. All right. Last but not least, letter D. How high has the elevator moved above its original starting point, and what is its final velocity? So look, in order to do letter D, we got to do this in parts. All right. So this is going to be a pain, but it is what it is. So so for letter D, I'm going to do part A's. Let's talk about part A's. How could this be the fastest? Do they give me time? Yeah, they do give me time for everything. So let's find the total distance first, or meaning how high, and then I could probably find the final velocity, I hope relatively easily. I think so. Shouldn't be bad. So, okay, so for letter A, how far did it go? So what do we know? We know the elevator filled with passengers, the elevator accelerates upward from rest. So we know for part A, the elevator is starting initially at rest, so it's 0. It's going to reach some final velocity. It doesn't tell us though, right? So that's a question mark. It accelerates at a rate of 1.20 meters per second squared, okay? And it does it for how long? 1.5 1.50 seconds, right? Okay, does it tell us anything else? No. So from this information, can we find the y value? I think we can. What formula can we use? Think back to kinematics. We can use I'll put the formula over here, change in y is equal to initial velocity in the y direction times time plus 1/2 acceleration times time squared, right? That's the formula. So let's plug it in. So change in y, which is what I'm looking for, is going to equal the initial velocity, which is 0. So this whole term just drops out. That goes to 0. Plus then 1/2 times the acceleration they told us of 1.20 times the time, 1.50, and that's squared. So just plug this into the calculator. So this would be the displacement for part A. So 0.5 times 1.2 times 1.5 squared. All right. So here, wait, no, I get a value of 15,000. Is that what you guys got? No, I hope not. So did something wrong in the calculator. So 0.5 times 1.2 times 1.5 squared. All right, that makes a little more sense. So we get a value of 1.35, right? 1.35, and that's in meters. Okay, so that's the distance for part A. Now let's take a look for part B. Okay, go back to reading. So it says the elevator continues upward at a constant velocity for 8.5 seconds. All right, so it's still going up, right? So we can, since it's constant velocity, we can easily use our velocity equation. Velocity is equal to distance or displacement over time, right? So the velocity here is, we got to find the velocity at the end of the second part. Oh, man. We don't know the velocity, right, guys? So what I have to do here first, I got to find the final velocity. Oh, man, this is such a long problem. So, is there any? No, I don't think there's a faster way. There might be, but all right. Anyway, so now what I need to do here is, in order to do part B, I got to find the final velocity of part A. Okay, how do we do that? So the final velocity of part A, I think I'm going to use, let me just look at what I'm given. Yeah, I'm going to use this formula. Final velocity of part A is equal to the initial velocity of part A plus the acceleration of part A times time of part A. All right, so the final velocity of part A will simply be equal to, that was 0, the acceleration was 1.20, and the time was 1.50. So the final velocity of part A is going to be equal to 1.2 times 1.5, so 1.8. So there's 1.8 meters per second. Okay, now I can use this in this simple equation. Now the average velocity is equal to the displacement over time. Why can I use it? Because it tells me that the velocity is now constant. Well, it's constant from what point? Well, it's constant from the end of part A. All right, so that's why I needed to find the final velocity of part A. So now it's 1.8 is equal to the distance over the time. What's the time for part B? It told us 8.5 seconds, right? So now simply just cross multiply, and I'm just gonna, let me change the D to a Y, okay? Just because I want to keep everything fairly consistent. I should have probably done that in the beginning, but what are you gonna do? So 1.8 times 8.5. And we get 15.3. Okay, so 115.3, and that's in terms of meters. So that's the part for part B. And now let's do it for part C. Okay, so what do we got here? So for part C, it says the elevator decelerates at a rate of 0.6 meters per second squared for 3 seconds. All right, so what do we know? Well, we know the initial velocity for part C should be equal to the velocity at the end of part B, right? And since the velocity was constant for part B, it was the same as the final velocity for part A. So I hope you followed that. But I'm just running out of time here. This problem is a little nuts. So it's going to be 1.8 meters per second. All right. The final velocity we don't know. It is decelerating, so we don't know what it is. Okay. The acceleration we do know. I just said deceleration, so it's negative 0.600 meters per second squared. I'm going to leave out the units, just running out of space. What else do we know? We do know the time it's decelerating, right? It's 3 seconds, 3.00. And we are looking for the y, right? That's what we're most interested in. So, okay, so now how do we find y? Well, what do we know? We know the initial velocity, we know the acceleration, we know the time, so why don't we use the same formula we did over here in the first part of part A? Okay, So we have the change in y is equal to the initial velocity, which is 1.8, multiplied by the time of 3, plus 1/2 times the acceleration, which is negative 0.6, right, times the time. I ran out of room, so I'm just going to write it underneath, times time squared. Okay, so the y value here, okay, is 1.8 times 3. Great, I get a value of 5.4, right? Now do 0.5 times negative 0.6 times 3 squared. All right, and simply add the two together. So it's negative 2.7 plus 5.4, and we get a value of 2.7, right, or 2.70 meters. And that's the end of part C. So how high did the elevator go? What do? Add it all up. Upper left-hand corner, guys. So the change in y total should be equal to the y height of A plus the height of B plus the height of C. So change in y total here is going to be 1.35 plus 15.3 plus 2.70. So change in y, the total height here, let's just plug it in. 1.35 plus 15.3 plus 2.7. 19.4, considering rounding and sig figs. So 19.4 meters. That is the total height. And now we got to find its final velocity. So what I could do is I could add up all the times, find the total time because I found the total height, and then I can do it that way, or I can just stick with part C and just try to find the final velocity at the end of part C. All right, so I think I'm going to do it that way. Just find the final velocity at the end of part C. So I'm focusing on all of C's values here. So how do I find that? Looks like I'm going to be using, which one should I use? Yeah, why don't we use the simple one? The final velocity is equal to, I'm on the upper right-hand side. Final velocity is equal to the initial velocity plus the acceleration times time. This is all for part C. All right, so the final velocity of part C will be equal to the initial velocity of part C, which was 1.8, plus the acceleration, which was negative 0.6, times the time, which was, where's the time? 3 seconds, right? So simply just plug that into the calculator, and we get 1.8 plus negative 0.6 times 3, and a big old fat 0 meters per second. So it has stopped. It started at rest initially, and it stopped at rest. All right? Oh, thank you guys for tuning in. I hope you were able to make it to the end. I almost wasn't, but we made it together. And for that, I thank you very much. Please do subscribe. I would also thank you very much if you were able to just hit that button. It would definitely help us out tremendously. If we have helped you at all, that'd be a small way to send your thanks and love back to us. We would appreciate it very, very much. And yeah. Number 50. Unreasonable results. Letter A. What is the final velocity of a car originally traveling at 50 kilometers per hour that decelerates at a rate of 0.4 meters per second squared for 50 seconds? All right, so let's just, it says one is unreasonable, but why don't we just find some stuff? So the first thing is it tells me the initial velocity of the car is 50.0 kilometers per hour. I hate that because I got to convert, right? I mean, we're given the acceleration in meters per second squared, so let's just turn kilometers per hour into meters per second. Remember, we do this, plug kilometers on the bottom, meters on the top, figure out a relationship. There's 1,000 meters in 1 kilometer. Kilometers cancel, right? So I got meters on the top. Now I'm going to turn my attention to the denominator. I got to get rid of hours, so hours will go in the numerator. All right. And then I know the relationship between hours and minutes. I'm trying to get smaller in the denominator. Therefore, I know 60 minutes in an hour. So the hours cancel, right? Now I got minutes, but I don't want to know meters per minute. I want to know meters per second. So I got to get rid of the minutes. So the minutes go on the top, seconds on the bottom. I do know the relationship, 60 seconds for every 1 minute, so I can cancel the minutes. And lo and behold, 50 times 1,000 divided by 3,600. So we get 13.9. All right, 13.9 meters per second. Okay, that's the initial velocity. Now it says it decelerates at a rate of 0.4. What does deceleration mean? It means, it doesn't necessarily mean negative acceleration, but it'll mean the opposite sign to the direction of travel. So I'm just going to assume, right, that this car is going, looks like a wheelbarrow. But I'm going to assume that this car slash wheelbarrow is moving to the right. Therefore, the deceleration would be opposing that or going to the left, and I would have to show that by giving a negative sign to it, okay? So the acceleration here would be negative 0.400 meters per second squared. And it says that the time that this acceleration is occurring over is 50.0 seconds, all right? And it says, what is the final velocity? So I want to try to find the final velocity here. So that's a question mark, right? So all we have to do, this is purely kinematics. I mean, just think back to, kinematics. How do I need a formula that relates for these variables and allows me to solve for the VF. Which one might it be? It's the easy one, right? The one we all like to work with. Final velocity is equal to the initial velocity plus the acceleration times time. Final velocity is the unknown. The initial velocity we found to be 13.9. The acceleration here was negative 0.400 multiplied by the time value of 50 seconds. So all we got to do is plug it into the calculator. So what do we get here? So 13.9 times negative 0.4 times 50. Whoa. Is that even right? No. I got negative 278. It's a little off. The plus sign turned into a multiplication sign somehow. But again, I'm always checking to make sure the answers are reasonable because I realize when I get a value like that, something went wrong somewhere. So it's 13.9 minus 0.4 times 50. Good value. That sounds a lot better. Negative 6.10 meters per second. So why is that value unreasonable? Well, what does the negative sign tell you? Negative sign in terms of velocity tells you direction, correct? So what that means is that according to my car wheelbarrow here, it was traveling to the right. It had a positive initial velocity, right? Notice that this value here is positive, okay? And it kept traveling, and then it stopped, and then somehow it started to go back, right? Because my final velocity is now negative. I mean, I don't know about you, but when I decelerate my car, I generally come to a stop. I don't know how to go from, drive to reverse without, continuously, let's say. All right. So I think it's a little unreasonable that the final velocity here would be negative 6.10. Unless the car maybe was going up a hill, right? I mean, that's possible, right? We have a hill here. Here's my Tesla. Okay. I don't have a Tesla. I'm just saying that this looks like, well, it doesn't at all. Anyway, it's something, some vehicle with two wheels, a bicycle. That's square. So it's traveling up the hill, and let's just pretend that I throw it in neutral, all right? And its initial velocity were to be 13.9. Then what would happen is, it would travel up. It would come to a high point and then travel back down because it's in neutral, all right? But I don't know. Maybe that's how the problem is created. I don't know. It doesn't give me enough information, but that would be what's unreasonable about it. What premise is unreasonable? I don't know. Maybe the initial velocity wasn't measured right, or maybe the time is too long. Could be a whole bunch of things. Number 51, unreasonable results. A 75-kilogram man stands on a bathroom scale in an elevator that accelerates from rest to 30 meters per second in 2 seconds. Letter A, calculate the scale reading in newtons and compare it with his weight. Okay, so here I have a little picture. Man is in an elevator over here. He weighs 75 kilograms, and we have a scale down here on the bottom. All right. So first thing is this elevator, it says will be accelerating upward, right? It doesn't say upward, but I am assuming they're talking about upward. All right. So the A is something. Now, in order to find A, they don't tell us, but they do give us enough information in order to do that. So why don't we do that first? Right. It says that the elevator initially is starting at rest of 0, right, meters per second. It's getting to a velocity of 30. I assume that's the final, right? 30 meters per second. It takes the elevator to go from 0 to 30 in 2 seconds. Okay. From this information, then, can I calculate my acceleration? Sure. Think back to the formulas of kinematics. Vf is equal to Vi plus At. Right? So the final velocity was 30. The initial was 0. The acceleration is what I'm looking for, and the time was 2 seconds. So simply divide out the right-hand side by 2 and the left-hand side by 2, and we find that the acceleration here is 15.0 meters per second squared. All right, so that is the A, and it's positive. So I can get rid of this question mark right now, and let's plug in 15.0 meters per second squared. Okay, that's a pretty large acceleration. Now, in order to try to figure out the forces that are acting in this problem, because we have to figure out what the scale reads, and the scale is detecting newtons, which are units of force, and we have to detail the free body diagram. So first, let's detail, since it is a problem in the y direction, we have to detail the weight first of the man, right? So the weight always points straight down, so that's equal to mg. So his weight will be equal to his mass, which was 75.0 kilograms multiplied by the gravitational acceleration of 9.80. So the weight is going to be 75 times 9.8, 735, right? So the value is 735, and that's in terms of newtons. Great. And that'll be negative when I plug it into the formulas. Now, since there is a net acceleration in the positive y direction, I know that there has to be some force pulling up, right, on this elevator. All right, I'm just going to call it something like F applied, or you could call it tension. You can call it whatever you want. But I think force applied might make the most sense. So what I'm going to do here is I'm actually going to calculate that force applied, and then we'll see how we can relate that to what the scale may read. All right, so we have everything we need to know. We can use this equation on the right-hand side. Some of the forces in the y direction should equal the mass of the object that's accelerating multiplied by the acceleration of that object in the y direction. So some of the forces. We have the applied force, which we don't know what it is. We have the weight of the man, right, which we found was negative, should be negative, right, 735. The mass was 75 kilograms, and his acceleration is 15.0 meters per second on upward. So to solve this, just simply add the 735 right to both sides. 735. So that cancels. My force applied then should be fairly straightforward. 75 times 15 and then plus 735. So we get a value of about 1860, right? Or 1860 newtons. Okay, almost looks like a theta there. 1860 newtons. Right, so that's the force that's applied. Okay, great. So now let's think about what the scale should read. Okay, so you might say, well, wait a minute. Okay, so if this is the force that's being applied, then that's great. What I'm going to do is I'm going to think about taking Newton's third law, and if this is the force that's being applied on upward, I'm going to write the vector, that same vector, on downward. So I'm going to add it to his weight. All right. Well, the problem with that is, though, then your summations are becoming too large. Okay, because then you would be adding the 1860 with the 735. All right. So if you think about what the net force is acting on this system, okay, that might be a little easier. Just simply solve this equation, but don't break up the sum of the forces. Right, so you can say sum of the forces in the y direction is equal to the mass, which was 75.0, multiplied by the acceleration of 15.0. So the sum of all the forces in the y direction will be equal to 75 plus 15. 75 times 15. 1125, right? I'll just say 1130 for sig figs. 1130 newtons. This is the net force. This is net. This is not the force applied. So this is what you're really thinking about if you are considering adding something to the weight here on the scale. Okay? For example, here's the picture again. Okay? There's an individual in here, right, standing on a scale. Okay? We know that the scale here, all right, will detect the forces present. So it will detect his weight, which is pointing down. So that weight was 735 newtons. Okay? Now, what else is it going to detect? Well, it's going to detect the additional force above his weight. Right? In other words, if I had another vector pointing straight up, and let's say that was 735 newtons. Okay? Tell me, what's the sum of the forces in this problem? 0, right? And what then does that mean the acceleration should be? 0, right? If you look at the sum of the forces equals ma, If this side is 0, then this side has to be 0. The only way this side is going to be 0 is if the acceleration is 0. So when the force is exactly balanced, you get 0 acceleration. Okay, and the scale would read exactly this amount, 735. But there is an acceleration in this problem, right? The acceleration is 15 meters per second, and in order for this person to experience a 15 meter per second squared, 15 meter per second squared acceleration, the force that's applied has to be, we just calculated, 1860 newtons. All right, but this is not the total force that's being then added to his weight. It's the difference, right? Because remember, the 735 Newton force that would have been pointing up is just to cancel out his weight pointing down. That would have been under no acceleration circumstances, right? So in order to find the additional amount here, we would just subtract the two. Okay, that would give us the net force of 1130 or so, right? I know the math works out a little differently. I'm rounding because of sig figs. And then this is the force that you would then essentially add to his weight, the 1130, okay? But then if you add that right to the 735, guess what you get? You get the 1860 again, all right? But that's how it kind of arises. That's a little more detailed picture. So this is what the scale would read, 1860 newtons. Now, what does it say? How does this compare with his weight? He's taking a nap. I don't know if you can tell, but that's nap time. So we have, what we do is a simple ratio. So we do 1860 all over his initial weight of 735. We just get a quick ratio here, okay? So we get 1860 over 735, and we get 2.53. 2.53, so the scale would read 2.53 times, or 2.5 times greater than what his weight would actually be. So now it says, well, what is unreasonable about this? Blah, blah, blah. I mean, unless this is some kind of, I don't know, ride at Six Flags or whatever the case is, this is way too much. This is way too high of a final velocity to achieve in this time frame. It's unreasonable. 30 meters per second, right? That would be like, if you just think back to the prior problem, remember 50 kilometers per hour was equal to about, what was it, 14 meters per second? So this is double that. So this is almost like 110, somewhere around there. 110 kilometers per hour. It's a little nuts, right? That'd be some elevator. And you're reaching that speed in 2 seconds, right? That would be a fun ride, but you wouldn't find that in your office building. All right. So anyway, that's one of the parts that's unreasonable. What makes it unreasonable? I don't know. It could be a whole bunch of things. The time that was measured, or maybe the final velocity was measured incorrectly, something like that. Number 52, letter A. What is the strength of the weak nuclear force relative to the strong nuclear force? Let's take a look at that. So here's a table right from the textbook. So let's identify the weak nuclear force. Here's the value. The strong nuclear force. Here's the value. And now what they want us to do is they want us to relate the weak nuclear force to the strong nuclear force. All right, so in order to create the right ratio, we're going to do the force of the weak relative to the force of the strong. Okay? Whatever you're relating it to always goes in the denominator. So the weak nuclear force is 10 to the minus 13. The strong is 1. Right? These are relative strains, so therefore, that's it, right? Dividing it by 1 is the same as itself. So this would be the relative strength of the weak nuclear force relative to the strong. So that takes care of letter A. Let's turn our attention to letter B. So what is the strength of the weak nuclear force relative to the electromagnetic force? All right, so what's in the denominator this time? The electromagnetic force, right? So here's part B. So now we're comparing the strength of the weak nuclear force to the to the electromagnetic force. So say F sub E. So the weak nuclear force, again, it's 10 to the minus 13. And then the electromagnetic is 10 to the minus 2. 10 to the minus 2. So when we do the division here, it comes out to be 10 to the minus 11. Right, to 1, basically. So the weak nuclear force is 10 to the 11 times weaker than the electromagnetic force. And that would take care of letter B. And then the rest of the problem just goes on to explain something, but you can read that on your own if you like. Number 53, letter A. What is the ratio of the strength of the gravitational force to that of the strong nuclear force? All right, so let's just take a look at that. So here we have letter A. So we're comparing the gravitational force to the strong nuclear force. All right, so just look it up in the table, right? This table is right from the textbook. So the gravitational force, it says, is 10 to the minus 38. So 10 to the minus 38. And the strong nuclear force is 1. So this is simply 10 to the minus 38. So what this means is that the gravitational force is 10 to the minus 38 times weaker, right, than the strong nuclear force. All right, let's take a look at letter B. So I'll go back to the question. It says, what is the ratio of the strength of the gravitational force to that of the weak nuclear force, right? The weak nuclear force now. So for letter B, now we're comparing the gravitational force to this strength of the weak nuclear force. So again, just look up the table, look up the numbers in the table. The gravitational is 10 to the minus 38. And then the weak nuclear force is 10 to the minus 13. Okay, so just simply do the division. You can basically just subtract the exponents here. So 38 minus a negative 13. Well, not negative 38 minus a negative 13. Should be a negative 25, right? So this is going to be 10 to the negative 25 to 1. So this is how much weaker the gravitational force is when compared to the weak nuclear force. So 10 to the minus 25. Great, and now letter C, last but not least. So what is the ratio of the strength of the gravitational force to that of the electromagnetic force? So same procedure here, letter C, the force of gravity over the electromagnetic force. Force of gravity in the table is 10 to the minus 38. The electromagnetic force is 10 to the minus 2. So simply just subtract basically the exponents. So you're going to add the 2 to negative 38. So that becomes 10 to the negative 36. And that's how many times weaker the gravitational force is than the electromagnetic force. And then it says, what do your answers imply about the influence of gravitational force on atomic nuclei? I would say it's pretty negligible. What do you guys think? I'm glad you agree. Number 54. What is the ratio of the strength of the strong nuclear force to that of the electromagnetic force? All right, so let's just take a look at the table. So we're comparing the nuclear to the electromagnetic. Therefore, our ratio is the force of the strong nuclear to that of the force of the electromagnetic. So here, just look up the numbers in this table right from your textbook. So it's strong nuclear is 1, has a value of 1 in terms of relative strength. The electromagnetic is 10 to the minus 2. And therefore, when I do the division, this becomes 10 to the positive 2. All right? So basically, the strong nuclear force is 100 times stronger than the electromagnetic force. All right? But if you notice the range here, right, the range of this strong nuclear force, it acts at very, very small differences. But meanwhile, the range of the electromagnetic force is essentially infinite. So that may play a role in terms of distances, in terms of where distances are involved that are, in between those two values. So, and then it goes on based on this ratio. You might expect that the strong nuclear force dominates the nucleus, blah, blah, blah. You can feel free to read that on your own, guys. It's not really anything major there.
Hey, you made it. Excellent work. I'm really proud of you. Great job. I really do hope the video helped. And for the next video in the series, please click this button right over here. And if you wouldn't mind giving us a hand, if you really found the video helpful, why don't you subscribe, smash that like button, and tell your friends. All right, we really appreciate it so much, and we really look forward to helping you with more problems. We'll see you soon. Bye.